Hello, welcome to this Introduction to R course. In this course, we will help you lay solid foundation for using the R programming language for data science. You may be a data scientist looking for insights from your data, a researcher looking to quickly analyze your experimental data and validate your scientific hypothesis, a software developer looking to step up to a new career as data scientist, or a new graduate seeking to establish a solid skill set to score a job in data analytics or data science. Regardless of your goals, you may wonder which programming language to choose. And is R the right choice? Yes, it is. R is one of the most widely used language for data analytics and data science, especially for statistical computing. So what makes R so good? First, R is an open source language, which means you can review the source code for free and even modify it. Being open source, you can leverage and integrate cutting-edge researches into your analytics, such as latest AI algorithms. Second, R has rich data science libraries that include everything you need to do data processing, data visualization, and modeling to facilitate your own research and development. Third, R is simple and easy to understand. Its simple syntax allows you to learn it very quickly. And finally, R has an extensive and rich community of support, so you can very easily find answers to your questions online. R has been a very popular language since 2014. According to the TIOB index, which is an indicator of the popularity of programming languages, R ranked the 8th in 2020. This is a very high rank out of hundreds of programming languages available today. So get ready to learn the powerful and popular R language for your data science endeavors. To learn effectively and efficiently from this course, view every video, check your learning by taking each quiz, and connect to your peers in the discussion forums. Finally, consolidate your coding skills by completing all the hands-on labs and the final project. Now, equip yourself with your new R skills and take the next step along an exciting journey that leads to the world of data. Good luck!
Welcome to Introduction to the R programming language. After watching this video, you will be able to explain the purpose of the R language and describe its main features. R is an interpreted language. Interpreted languages such as R, Python, and JavaScript are a type of programming language that is interpreted and executed directly by an interpreter without first compiling it into the target machine instructions. You typically access these languages through a command line interpreter. The initial version of R was developed at Bell Laboratories and released in 1994. The main reason to use the R language is to perform very comprehensive statistical computation tasks. For example, you can use R to obtain a summary of descriptive statistics for data such as the mean, variance, median, or quantile. Suppose you have a variable called num_tested, for example, that represents the total number of patients tested. You can use R to quickly return its median and max values. You can also use R to perform data sampling to obtain a representative data subset. You can also use R to analyze if variables are correlated. For example, R can compute and visualize a correlation matrix among 4 different variables to see if they are correlated. Another way to use R is to perform hypothesis testing, such as testing if the mean values of 2 groups are statistically different. Finally, you can use R to infer the properties of unknown distributions, such as inferring an unknown mean value of a population from its samples. R is also widely used for data visualization. You can use the many R visualization packages to visualize data, perform interactive and visual analytics, or build a dashboard for end users. For example, to analyze the zip-related data on an interactive map. R is also a powerful tool in predictive analyses, such as machine learning and AI tasks. You can use R to predict pandemic trends, for example, or to understand human languages in various forms, such as documents and speeches. For example, you can analyze the sentiments of a user review to determine if it is positive or negative. Or you can even use R to recognize visual objects, such as dog breeds. In this video, you learned some of the ways that you can use the R programming language to perform statistical computation, data visualization, and predictive analysis. Welcome to Basic Data Types. After watching this video, you will be able to describe the basic data types in the R language and explain data type conversion. No matter how simple or complex a program is, its core function is always to define and process data. Data has many types, like numbers, factors, text, and dates. Each type must be defined and processed properly by programming languages to achieve the correct result. Thus, before you learn how to process data using R, it is fundamental that you understand its common data types. The integer type in R is a similar concept as whole numbers without a decimal. The integer type includes 0, positive counting numbers such as 1, 2, and 3, and negative counting numbers such as -1, -2, and -3. In R, integer numbers are written with an uppercase L suffix, for example, 0L or 1L. If you use an R function called class on an integer like 1L, R will return its data type as integer. You can also use the is.integer function to check if 1L is an integer. The is.integer function returns a Boolean value true for the value 1L, meaning it is an integer. Another more generic number data type is called numeric. The numeric data type includes the integer and all numbers in between the integers. Consider the numbers between 0 and 1. You can select numbers in between them. Their type is also numeric. Similarly, consider the numbers between 0.1 and 0.2. They are also numeric, and you can continue the selection infinitely. In R, numeric data is written with only numbers without the suffix L. If you use the class function on the number 1, it returns its type as numeric. As with integer, you can use is.numeric to check if 1 is a numeric type. Textual data is another common data type. In R, textual data is defined as the character type. For example, a single character A with single quotes, the sentence, "I like the R language," and an email address with double quotes are all the character type. Like the numeric or integer types, you can use the class function to check the data type, or use the is.character function to check if any data belongs to the character type. Another common data type is Boolean, which is typically used to represent the result of logical operations. For example, you could use it to compare two values or check if a statement is true or false. In R, Boolean data is represented as the logical type and has two values, true and false. You can already see one logical operation in previous slides when we used the is.numeric or is.character functions to check if a data value is of the numeric or character type. Similarly, you can use the class and is.logical functions to check if a data value belongs to the logical type. In R, you can convert data from one type to a different type. This conversion is also called casting. Let's look at some common conversion or casting scenarios. you can easily convert an integer to a numeric using the as.numeric function, or a numeric to an integer using the as.integer function. The as.integer function reduces the precision of numeric data by removing its decimal part. You can also convert a numeric to its character form by using the as.character function, or convert a number stored as a character to a numeric by using as.numeric. However, if you try to convert a non-numeric character into numeric, R will raise an error indicating that the conversion is not allowed. Interestingly, you could convert logical data into numeric or character, or vice versa. If you use the as.logical function to convert a non-zero number, such as 1, it returns true as a logical result. Or you could convert a character false to a logical false. You can also convert a logical value false into 0 as a numeric value. There are two advanced data types that you may not use as often as the other types. They are complex data types, representing complex data, and raw data types, representing binary or byte data. In this video, you learned about the most common data types in R. You also learned about the ways that you can determine the type of data and how to convert data from one type to another.
Hello, and welcome. In this video, we will show you how to perform basic mathematical operations in R, how to assign values to variables, and how to create strings. Here we have some data that contains a set of movies, along with some relevant information. As an example, let's check whether or not we have time to watch Fight Club and Star Wars in 4 hours. Based on the chart, the respective lengths are 139 and 121 minutes. To figure out the total time, all we need to do is write 139 plus 121, and we see that the answer is 260 minutes. But we need to know how many hours this will take. So we'll use the / to divide 260 minutes by 60 minutes per hour. As you can see, these two movies take a little longer than 4 hours. Besides addition and division, R provides operators for subtraction, multiplication, and exponentiation. You can see the operator symbols in the chart here. If you'd like to save a calculation and use it later, you can store a value in a variable. So let's add the runtimes again, but this time we'll store the result in a variable called x. You can see how that works in the code snippet here. If we then take a look at our new variable x, we see that the value 260 has indeed been stored. From now on, we can perform mathematical operations on the variable x. So let's divide it by 60 and store the result in a variable called y. As you can see, we get the same answer as before. One important note is that the equals sign can also be used to assign values to variables, although it's not quite as common. You can also reassign variables that you've already used. So again, let's assign a value to x by adding 139 and 121. If we look at the output, we'll see the value 260 from before. Overwriting x is very simple. All we need to do is use the variable assignment operator again, and if we look at the output, we see that the original value has been replaced. Since variables take up memory, it's good practice to clean them up when you no longer need them. To do this, you can use the rm command while passing in the variable that you want to remove. Whenever you write code, it's important to use meaningful variable names. The variable name x from before isn't very descriptive and may be hard to understand. So when computing the total time, we can instead use a variable name like total, which is more descriptive of the variable's value. When computing the total hours, we can use another variable name with _HR appended, so that the variable can be differentiated. It's important to know the order of operations, since some operators have a higher precedence. In our previous examples, we've been performing the addition and division operations in different statements, which gives us the result we'd expect. But we can combine them into a single statement. Notice, however, that we've added the parentheses around the addition portion. This is because the division operator has a higher precedence than the addition operator. Without the parentheses, R would first divide 121 by 60 and then add the result to 139. The parentheses ensure that we get the correct answer. In R, a string is simply a sequence of one or more characters. To create a string, simply enclose the characters within matching single quotes or matching double quotes. Like numbers, strings can also be assigned to variables. By now, you should understand the basic mathematical operations provided by R, as well as how to work with variables and create strings. Thank you for watching this video.
Welcome to the R environment. After watching this video, you will be able to explain R environment-related concepts, such as the R console, R script files, and workspaces, and describe two popular R development tools, R Studio and Jupyter Notebook. When you first start programming with R, you will typically type your first line of code into a shell interface called the R console. You write and execute R code in the R console interactively and see the results immediately. As you get more familiar with R, you will need to organize multiple lines of R code into logical code snippets to complete more complex tasks. For example, finding the top-rated movies to watch. To do so, you put your R code snippets into one or more script files, which end with a .r extension, and then run the script files in batch mode. Regardless of whether your R code is written in the console or in script files, the R interpreter parses them and translates them into many types of objects in memory. Objects can be variables, data, or functions. In case you are not familiar with functions, a function is an object that includes an R code snippet created to perform a task. These R objects will be eventually translated to instructions that can be executed by the CPU. R combines all such objects into an image called a workspace, which works like a workbench in your garage. At the end of your R session, you can save the current workspace to a file with the extension rdata. When you want to resume your work, load the rdata file to open the workspace and continue your work. As mentioned in the previous slide, the workspace contains all created objects in memory. If you want to get a full list of those objects, you can simply use the ls function to list them. For example, here we have a function object and three variables called sum, x, and y in our workspace. In addition to managing objects that exist in memory, or RAM, the R workspace also needs a root directory from which to manage files. This is your current working directory. You can use the getwd function to return your current working directory. If you are not happy with the location of the working directory, you can use setwd to change it to a new directory. To save a workspace into an rdata file in the current working directory, simply call the save.image function with a name like myworkspace.rdata. The next time you want to resume the workspace, you can call the load function to load the saved workspace. When working with R code, you will need to use a tool such as an IDE or notebook to facilitate development and experiments. Two popular R tools are RStudio and Jupyter Notebook. RStudio is probably the most popular integrated development environment specifically for R. RStudio provides many features to help you with R development, such as syntax highlighting, command history, workspace management, and direct code execution. The Jupyter Notebook is an interactive web-based code editor that you can use to combine code, data, experimental results, and narration together in a single notebook instance. Jupyter Notebook is very efficient for experiments and prototyping, as well as for educational purposes. You will have more opportunities to learn and practice with these tools in later videos and labs. In this video, you learned about the relationship between the R console, R script files, and workspaces, and their role in developing R code. You also learned techniques for managing work directories and workspaces, and two important tools for working with R code, RStudio and Jupyter. Welcome to Introduction to RStudio. After watching this video, you will be able to explain the advantages of using RStudio for your R development and identify its main user interface components. In the following lab, you will be writing your first R code snippet in RStudio. Like other modern integrated development environments, or IDEs, the first advantage of RStudio is to facilitate code writing, which is enabled by two main features. The first feature is called syntax highlighting. The RStudio file editor color codes different R keywords to increase the readability of your code and make it easier to find your target variables. The second feature is called code auto-completion, or syntax suggestion. When you start to type R code, RStudio will try to guess what you want to type next and suggest options, such as function names or help documentation you can use to complete your code. By selecting the suggested syntax, you can save many keystrokes and increase your code syntax accuracy. The core concept of the R working environment is the workspace. Recall that you can use the is function to list all objects in a workspace. To make this even easier, RStudio visualizes all objects, like data, variables, and functions in the workspace, so you can conveniently check the object names and values, and even clean them to free up memory. Sometimes an R project contains different types of files, such as scripts, data, or plots. RStudio provides an intuitive file explorer to help you manage them. You can see your project structure in RStudio and click a file to check its contents. For example, to check the data in a CSV file called addresses.csv, simply double-click the file name and it will open in the file editor. Now that you know the advantages of using RStudio, you can utilize its features together in the main screen of RStudio. In the File Editor panel, you can write your R code or other text files with the help of syntax highlighting and auto-completion. In the Console panel, you can quickly try some R commands and see the results immediately. You can review the created objects in the Workspace panel. And you can manage your files and other assets, such as plots or packages, in the File Explorer panel. In this video, you learned about some of the features of RStudio that make writing R code easier, like syntax highlighting and auto-code completion, and the location of the main components of RStudio, including the File Editor, Console, Workspace, and File, Plots, and Packages Explorer. Welcome to Writing and Running Code in Jupyter Notebook. After watching this video, you will be able to describe the basic features of Jupyter Notebook and the advantages of using it to write your R code. In the following lab, you will practice what you have learned so far using Jupyter Notebook. A Jupyter Notebook is made up of a series of cells that you can use to write, run, and interact with your code. A cell in Jupyter Notebook is a multi-line text input field where you can enter many types of text, including programming code, markdown files, or raw text that you can later convert into other formats. Lines, depending on their type, can be executed with different outcomes. If the lines are code, its execution results are called cell output. For example, you can print the character string, "Hello Jupiter," and it will be shown in the cell output below the cell. If you execute cells in a specific sequence, the cells can access all objects and outputs generated in all previous cells. For example, you can define a variable x, cell 1, with a value of 1, and execute it first, and then you can access variable x in cell 3. When creating a Jupyter notebook, you must specify its kernel, and then the notebook keeps one interactive session connected to that kernel. Through this interactive session, you can send your code to the kernel to be executed and get results back from the kernel. In this course, the kernel will always be R, but Jupyter Notebook supports many popular kernels, such as R, Python, and Julia, covering almost all popular programming languages. One of the main benefits of Jupyter Notebook is that it contains almost everything you might need for a coding task or experiment. For example, it includes narration, which you can use to provide instructions or context to the cells that follow, code, which is the actual logical implementation of your task, the data that needs to be processed in a task, and any plots, images, or videos that provide visual insights about the data. This all-in-one style makes notebook sharing and reproduction extremely easy. Also, including narration in a notebook makes it a great tool for teaching and learning because instructors can provide detailed step-by-step instructions along with code and data for learners all in one place. Another advantage of Jupyter Notebooks is that it enables you to interact with your code and data. For example, you could explore your data from different angles using different cells. You can jump back and forth among the cells to update your code while using the other cell's output as context. For example, in one cell, you could load some data related to COVID cases in Canada from a CSV file and print a snippet of code with the column names. Then, by looking at the column names, you may want to return the max value of confirmed cases, called numconf, in the next cell. By keeping the max confirmed cases in the previous cell output, you can now get its mean or min value and then compare it with the max value. A Jupyter Notebook can be easily converted into other popular document formats, such as PDF, HTML, or LaTeX, which makes it very convenient to present or demo your code and experiment results. In this video, you learned that a Jupyter Notebook is made up of cells that can contain code, markdown files, or raw text. And an all-in-one notebook contains narration, code, data, and plots, images, or videos. You also learned that each notebook maintains an interactive session with a kernel, like R, that enables you to interact with its code and data.
Hello and welcome. In this video, we will show you how to create vectors and factors in the R programming language. A vector is a one-dimensional array of objects, and it's a simple tool to store your data. In R, there is no restriction on the type or number of elements that a vector can contain. Let's create a vector that contains the runtimes of Toy Story and Akira. To do this, we simply use the C command, and inside the parentheses, we'll write the two values that we want to include in our vector. For purposes of illustration, we'll also divide the vector by 60. This division operation will be applied to each element individually. We can also assign a vector to a variable, which will give us the same result. It's easy to create a vector that contains a sequence of elements. So let's say you wanted a vector that contains the numbers from 1 to 10 in order. You could type all the values out, or you could simply write 1, then a colon, then 10. The result will be the same. If you want the numbers in decreasing order, simply switch the 1 and the 10. And you can see how that would look. As a quick note, take a look at the pound sign to the right of the C command. In R, this symbol is used to write comments in your code. Everything to the right of the symbol is for the programmer only and will not be interpreted. So we just saw that we can create vectors that hold numerical data, like a set of years. But we can also create a character vector if we want to store a list of strings. For example, we can create a vector that holds titles, which would look like this. One additional vector type we'll touch on is the logical vector. Logical data is simply a true or false, typically created via a comparison operator. For example, if we type 1997 greater than 2000, we get false as the output. These operators can be applied to vectors. So suppose we have a vector that contains movie ratings, which looks like this. If we run movie ratings greater than 7.5, R will check each element in the vector to see if the value is greater than 7.5. If so, the resulting value will be true, and if not, the value will be false. You can see how that would look in the output here. In R, factors are variables that can take on a limited number of values. These variables are often referred to as categorical variables. The other extreme would be a continuous variable, which can take on an infinite number of values. Let's encode the vector we have here as a factor. If you look at the output, you'll notice that there are 3 levels, which correspond to the 3 unique categories of the vector: animation, comedy, and crime. The summary function is useful when working with factors. If we apply summary on the original vector, you'll notice that it simply provides some basic information about the vector's structure and content. But if we apply it on the factor, the output shows us the number of occurrences of each of the component categories. There are 2 types of categorical variables. A nominal categorical variable does not have any implied order. The previous examples with movie genres were nominal, since there is no clear ordering between categories like animation and comedy. Ordinal variables, on the other hand, do have an ordering. So consider the vector here. It should be apparent that certain categories are less than others, and we'd want to encode this information into a factor. To do this, we need to pass 2 additional arguments to the factor function. We need to specify that ordered equals true, and then we need to specify a vector with the levels. Notice that the categories in the vector are listed in the order that we want, from lowest to highest, so to speak. If you take a look at the output, you can see that this information has been successfully encoded. By now, you should understand how to create various types of vectors, as well as how to use the factor function. Thank you for watching this video. Hello, and welcome. In this video, we will demonstrate several useful operations you can apply to vectors in the R programming language. Suppose we have a vector that contains the production years of 4 movies. It may be difficult to remember which movies these years belong to, so we can use the names function to map a title to each year. Now we can call our year vector while passing in a title in the brackets. As you can see in the output, the year and title are now mapped together. Finding the number of elements of a vector is simple. All you need to do is call the length function while passing in the vector as input. As expected, the vector has a length of 4. In order to sort a vector, we can simply call the sort function while passing in the vector as input. This will sort the movies in ascending order time-wise from oldest to newest. Notice that since we use the names function, the titles appear in the output along with the year. Finding the smallest and largest numbers in a vector is an easy task as well. To find the smallest number, simply use the min function while passing the vector as input. For the largest number, use the max function instead. We see that the min and max are 1985 and 2010, respectively. Now suppose we have a vector that contains the cost of 3 movies in millions, and we want to compute the average. One way to do this is by using the sum function to calculate the sum of all the vector elements, and then dividing the result by 3. A simpler alternative is to use the mean function instead. Both of these methods will produce the same result. Another useful tool is the summary function. This function will display descriptive statistics about the vector like the min and max, median, mean, and first and third quartiles. In order to retrieve an element of a vector, you simply need to write the vector's name, followed by the desired index in square brackets. So this piece of code would retrieve the second element. You can also use a vector inside the square brackets. In this case, we're telling R to retrieve the second and third elements. You can also retrieve the elements of a vector by specifying a range. In this example, we retrieve the elements from index 1 to index 3. Putting a negative number as the vector index will remove that particular element from the output. So for example, a -1 will remove the element that was in index 1. The vector that you see here only has 5 elements. If you try to access an index beyond 5, R will report a missing value by returning the symbol NA. Now going back to our cost vector, let's apply a logical operation on each of the elements. As we'd expect, the first 2 elements are true, while the third element is false. In order to retrieve the elements from the vector that are true, you can write the conditional inside of the square brackets. Notice that the only elements that are output are the elements that were true from the previous step. As we mentioned before, R handles missing values through the symbol NA. Missing values come up all the time in real-world datasets for various reasons. For example, if these numbers represent age restrictions for a movie, then the indices with missing values might be movies that have an unknown age restriction. An important thing to remember about vectors is that all arithmetic operations are performed element-wise. So let's multiply these 2 vectors together and take a look at the output. You'll notice that the first element, 28, is simply the product of the first element of vector 1 and the first element of vector 2. 48 is the product of the second elements, and so on. In this example, we multiply a vector by a number instead, but the concept is the same. Each element is multiplied by 10. By now, you should have a good idea of how to access the elements of a vector and how to apply useful operations. Thank you for watching this video. Hello, and welcome. In this video, we will show you how to create a list in the R programming language, and how to access and modify the list elements. In R, a list is a collection of objects, similar to a vector. But unlike a vector, the elements inside of a list can differ in terms of data type. So consider the piece of code here. We use the list function and specify the elements that we want to include. Notice that the first element is a string, the second is a number, and the third is a vector. Accessing an element of a list is simple. So for example, say we wanted to access element 2, which is the value 1995. All we need to do is type the index of the element inside the square brackets. This will retrieve the desired element. We can also access all the elements within a given range by specifying the start and end points. Here we access all elements between index 2 and index 3. You can also provide each of the individual variables with a name. This improves the list's organization and makes everything a bit easier to read. In order to access a list element by name, you can use the $ symbol, followed by the name of the element you want to access. Alternatively, you can provide a string that contains the name inside the square brackets. This is similar to how you'd access an element by its numerical index, but notice that both methods produce the same result. You can add a new element to the list by using the variable assignment operator. Simply provide the name of the new element inside the square brackets. Notice that R appends the new element to the last position of the list. To modify a value of the list, simply use the variable assignment operator to overwrite an existing value. If you'd like to remove an element from the list, all you need to do is assign a null value to it. As you can see, the element no longer appears in the list's output. By now, you should understand how to create a list, as well as how to add, modify, and remove items. Thank you for watching this video. Hello, and welcome. In this video, we will show you how to work with arrays and matrices in the R programming language. An array is a structure that contains data of the same type, whether that's strings, or characters, or integers. Arrays can be multidimensional as well, so the data can be contained in multiple rows and columns. In order to create an array, we'll first create a vector using the C command. Afterwards, we need to use the array function. The first argument is the vector we just created. The second argument is a vector that specifies the dimension. In this case, our array will have 4 rows and 3 columns. Notice that the elements start to repeat at row 2, column 3. This is because our original vector only had 9 elements, but the array size is 4 times 3, which is 12. To access an element in an array, we need to specify the element's index. So for example, say we wanted to extract whiplash. Whiplash is in the first row and the second column. All we need to do is specify the row and column in square brackets to get that particular element. We can also extract an entire row from the matrix. To do so, simply type the row you want in the square brackets, but leave the column empty. As you can see, the output is the entire first row. The same can be done for the columns. Leave the row empty and type the column you want to extract. In this case, we've extracted column 2 of the array. A matrix is similar in structure to an array. The main difference is that a matrix must be two-dimensional. Starting with the movie vector from before, we can use the matrix function while specifying 3 arguments. The first argument is simply the vector, while the next 2 arguments are the number of rows and columns, respectively. So in our case, we're building a 3x3 matrix. One thing to note is that by default, the matrix is arranged by columns rather than rows. We can change this by adding the parameter byRow equals true, and you can see how this changes the organization of the matrix. You can access certain subsets of the matrix with the proper notation. Consider the piece of code here. This is telling R to extract the values that are in rows 2 to 3, and in the columns from 1 to 2. The output is the subset of the array whose elements fall into this row and column range. By now, you should understand how to create an array or a matrix and how to access the data. Thank you for watching this video. Hello, and welcome. In this video, we will show you how to create a data frame in the R programming language, as well as how to access data and make changes. A data frame is a type of structure that contains correlated information. So, for example, a data frame would be a great structure for storing these movie titles along with their corresponding years. We need to use the data.frame function, and each argument is a vector that represents one of the columns. Each vector should contain data of the same type, so in our case, we have one vector with numbers and one vector with strings. The variables of a data frame can be accessed using the $sign symbol. So in this case, we will retrieve all the names of the data frame. In addition to the $sign symbol, we can access a column by specifying the column number inside of the square brackets. So in this case, we again retrieve the names column since it's the first column of the data frame. Individual elements can be accessed as well, rather than entire columns. So for example, say we wanted to access the element in row 1, column 2. All we need to do is write the row and column numbers inside the square brackets, like so. And as you can see, we get the desired output. To get some information about the data frame structure, you can pass the data frame as an argument to the str function. In the output, we can see the number of objects and variables, as well as the variable's type and content. The head and tail function can be used to look at the beginning and end of a data frame, respectively. The head function will display the first 6 elements, as you can see here. The tail function will similarly show us the last 6 elements of the data frame. If you want to insert a new column into the data frame, simply specify the new column's name in square brackets and assign it to a vector that contains the individual values. You can see here that we've added a new column for length. In order to insert a new row, we need to use the rbind function and assign the output back to our data frame. The arguments are the data frame itself, as well as a vector that contains values for all the columns. As you can see, we've increased the number of elements in the data frame from 8 to 9. You can delete rows from a data frame by using negative numbers inside the square brackets. You can see here that we use -9 for the row and leave the column blank. The output will be a data frame that has rows 1 through 8, and we then have to reassign it to the original data frame variable. If you look at the result, you'll notice that the 9th movie has been removed. In order to delete a column, like the length column here for example, all we need to do is assign a null value, like so. As you can see, this will remove that column from the data frame. By now, you should understand how to create and access a data frame, as well as how to make modifications. Thank you for watching this video. Hello, and welcome. In this video, we will show you how to utilize conditional statements, for loops, and while loops in the R programming language. Suppose that you have a group of movies in a dataset, like the one you see here, and you want to only select the movies released after the year 2000. To do this, we're going to have to rely on a conditional statement. In other words, we need to examine the dataset row by row and check if the year value is greater than 2000 or not. In R, we can use an if statement to accomplish this. Notice the syntax here. Inside the parentheses, we have the conditional statement. If this statement is true, then we execute the code inside the curly braces. Since 2002 is greater than 2000, we do see the printed statement in the output. You can also add an else block to your if statement. The code inside the else block will only execute if the conditional in the if statement is false. Notice that since 1997 is less than 2000, the print statement inside the else block is executed. Logical operators are used to compare two values, and the output is either true or false. We've already seen the greater than operator, but of course there's a less than operator as well. Putting an equal sign after the greater than sign will make a greater than or equal to operator. The same is true for the less than sign as well. In R, a single equal sign is used for variable assignment, so to check if two values are equal, we need to use a double equal sign. To check if two values are not equal, we write an exclamation point followed by an equal sign. We can also combine multiple conditional statements together. Notice the ampersand that separates the statement on the left from the statement on the right. This is the AND operator, which will return true only if both of the connecting statements are true. So let's see what the output should be. The statement on the left is true since both strings are the same, but the statement on the right is false. So the final output of the AND statement will be false. You can look here for an overview of the comparison and logical operators in R. The OR operator works similarly to the AND operator, except that to return true, only one statement needs to be true rather than both. The NOT operator is used to negate a Boolean value from true to false, or vice versa. And the IN operator checks if one operand is contained in the other. For loops can be used to cycle through all the values in a vector. Take a look at the code snippet here. This for loop will run once for each item of the years vector in order. At each iteration, we can access the current value using the YR variable that we defined. By printing this variable at each iteration, we end up outputting the entire vector. We can also combine the for loop with the if-else block from before. Notice at each iteration of the for loop, we check if the movie year is less than 1980, and we change our output depending on the result. You can see how that works in the output. While loops work a bit differently. A while loop will continue to execute so long as the condition inside the parentheses remains true. Notice that the condition is controlled by a variable called count, so as long as count is less than or equal to 5, the loop will continue to run. Since count starts at 1 and is incremented by 1 for every iteration of the loop, we'd expect the loop to run 5 times. And that's exactly what we see in the output. Keep in mind that this conditional statement was relatively controlled, but while loops are especially useful when you don't know how many times the loop will need to run. By now, you should understand the structure and purpose of conditional statements, for loops, and while loops. Thank you for watching this video. Hello, and welcome. In this video, we're going to show you how to work with functions in the R programming language. A function is a block of code that can be reused in different parts of a program. Generally speaking, this can be broken down into predefined functions and user-defined functions. Predefined functions are the functions that are already defined for you, whether they're built into R or provided in a separate package. Let's take a look at a few common functions. Here we define a small vector of movie ratings, and we use the built-in mean function to find the average, which you can see in the output. The sort function is used to order the elements of a vector. Notice that the elements are arranged in ascending order. This is the default behavior. If you'd like to sort in descending order, you'd need to add the parameter decreasing equals true when calling the function. As we mentioned before, you can define your own functions as well. In this code snippet, we create a function called print_hello_world that, when run, simply prints hello world to the screen. So if we call this function by name, we get the expected output. Our functions can take in arguments as well. The add function here takes in 2 numbers and produces the sum as output. The return statement can be used to explicitly output a value from the function. When return is encountered, anywhere in the function, the corresponding value will be output and the next function will exit. Keep in mind that if the function lacks a return statement, then R will automatically return the value of the last evaluated expression. The return statement is particularly useful when you need an if-else block, since the final output value will be dependent on some condition. Take a look at the function isGoodRating that we've defined. This function takes in a movie rating and runs through a conditional block, so the function will return a different value depending on the input. For example, if we pass in 6, the if statement will be true, and no will be returned. But if we pass in 9.5, the if statement will be false, and the function will return yes inside the else block. If you wish, you can set a default value for a function argument. Notice in the function definition we've added threshold equals 7. Now when we call this function, we only need to specify the rating parameter. R will automatically use the value of 7 for threshold. However, you can also override the default value, like so. Now since 8 is less than the specified value of 8.5, the function will return no as its output. To increase the complexity of an application, you can use functions within other functions. Let's first see the main function we're going to build at a high level. The function will receive a movie name and a threshold, and it will determine whether to watch the movie by outputting yes or no. In order to do this, the function will check a database for the movie's average rating. This rating, along with the default threshold of 7, will be passed to the previously defined isGoodRating function. The final output of the function will depend on the output of isGoodRating. So based on the dataset you see here, let's take a look at the entire function's structure. The function is called watchMovie, and it takes in the movie's name as well as a rating threshold. This line is responsible for pulling the movie's rating from the database. It does this by finding a matching name in the name column and then finding the average rating value in the corresponding row. In the next line of the function, we pass this rating to the isGoodRating function. MyThreshold is passed as well, but it has the same default value of 7. So if we pass in the movie name Akira, the rating is 8.1, which is greater than the default threshold of 7, so the output will be yes. We can also override the threshold, but 8.1 is still greater than 8, so once again we get yes as output. Variables can be defined inside of functions, but there are a few important considerations. The function here, when run, will simply output hello world. But take a closer look at the variables y and temp. If you try to access y outside of the function, you'll notice the output is 3.14. But if you try to access temp, we get an error instead. This is because there is a difference in how these variables are defined. You'll notice that temp uses the standard variable assignment operator, but the operator for y has an extra left arrow. This means that y is defined as a global variable, so it can be accessed outside the function. Temp, on the other hand, is local, so it can only be accessed inside the function. By now, you should understand how to work with both predefined and user-defined functions, how to nest functions within other functions, and how to create global variables. Thank you for watching this video. Hello, and welcome. In this video, we're going to show you several functions for manipulating strings in the R programming language. To begin, we're going to read in text from a file in order to demonstrate the string operations. The summary variable will hold a vector with 3 elements that represent the 3 lines of the file. You can see what those lines look like here. If you'd like to count the number of characters in a string, you can use the nchar function while passing the string in as an argument. As you can see, the first element of our vector is a string with 450 characters. If you want to convert all the characters of a string into uppercase, you can use the toUpper function. You can see how that would look here. Similarly, you can use the toLower function if you'd like to convert all the string's characters to lowercase. In order to replace a specific set of characters in a string, you can use the charTr function. The first argument is a string that contains the characters you'd like to replace. The second argument is a string that holds the replacement characters. And the last argument is the string you'd like to apply the operation on. Based on the output, you can see how the function replaced every space character with a hyphen. The strSplit function allows you to break apart a string by using some kind of expression. Take a look at the syntax here. The first argument is the string to split, and the second argument is the expression that we want to use to perform the split. In this case, we're breaking up the string by the space character. This will return a list, so to form a character vector, we'll need to use the unlist function. When you look at the output, you'll notice that the vector has one element per word, since in the original string, each word is separated by a space character. The word list vector we just created can be sorted as well, by passing it into the sort function. Doing so will order the elements alphabetically. We can also concatenate the elements of a character vector by using the paste function. The collapse argument determines the string value that will separate the individual elements. In our case, we'll simply separate them by a single space character. The output here is a single string representing our alphabetically sorted list. To isolate a specific portion of a string, you can use the substr function. Simply pass in the start and end indices of the segment you want, and this contiguous segment will be output. But notice that this particular substring has a leading and trailing space character. To get rid of them, we can use the trimws function, which removes all white space from the beginning and end of a string. There may be times that you want to form a substring by counting back from the last position. So, for example, you may want the last 8 characters, like the ones you see here. To do this, you'll need to use the str_sub function from the string R library. Notice how the start and end point arguments are negative in this case. So the start point is the 8th character from the last point of the string, and the end point is the index of the last character. You can see in the output that this successfully retrieved the last 8 characters. By now, you should understand how to modify characters in a string, how to split a string into a vector, and how to retrieve specific substrings. Thank you for watching this video. Hello, and welcome. In this video, we are going to show you how to work with regular expressions in the R programming language. In order to demonstrate the regular expression operations, we are going to use the simple data frame here. As you can see, it contains a few names and email addresses from different regions. Suppose our goal is to perform data analysis on each of the domains in the email addresses. The problem is, some of the email addresses have regional differences, so the URLs may differ, like the ones you see here. So what we need to do is isolate all the characters between the @ sign and period symbol. This seems tricky at first since the URLs can have variable lengths or strange characters, so regular expressions are perfect for a task like this. Regular expressions are used to match patterns in strings and text. Suppose you needed to express the structure of an email address, like the one here, but in the general case. Basically, an email can be expressed as a set of characters, followed by an @ sign, followed by another set of characters. What we just described could be written as this regular expression string. We have the @ sign in the middle, with text before it and text after it. So let's take a closer look at what all these symbols mean. The first symbol in the regular expression string is a period, but this has a special meaning. A period is like a wildcard that will match any character. The plus sign is also a special character. It is used to match the preceding pattern element one or more times. So a period followed by a plus sign will match any sequence of one or more characters. The @ sign simply matches an @ sign in the string. Remember that our goal is to isolate text between the @ sign and the period symbol, but since the period symbol has a special meaning, we'll need to alter our expression a bit. Notice in this expression, we've added 2 backslashes before the period character. This ensures that the period character itself will be matched in a string, rather than the period acting as a wildcard. So the expression you see here will match an @ sign, followed by one or more characters, followed by a period. This is exactly what we need for our problem. R provides several functions that make use of regular expressions. The first one we'll look at is grep. Grep takes in at least 2 inputs, the regular expression, and a list of strings you'd like to check for a match. Notice that this regular expression contains an asterisk, rather than a plus sign. An asterisk will match 0 or more of the previous element, rather than 1 or more of the previous element. Other than that subtle difference, their behavior is the same. The output shows the list positions of the strings that match this regular expression. You can use the value parameter to instruct the function to output the matching strings themselves. You can also substitute strings found by the regular expression by using the gsub function. The second argument serves as the replacement string. In our case, all characters after an @ sign will be replaced by newdomain.com. Notice how the second string was unaffected since there was no regular expression match. In order to extract the matched strings, you can use the regexpr function, which is like a more detailed grep. This function will find the matching substrings. We then pass the list of strings and the list of matches to the regmatches function, which gives us the desired output. We're now ready to address our problem. Let's apply a regular expression to the email column, making sure to isolate everything from the @ sign to the period. We'll then extract the matching substrings and add them to a new column called domain. And here is our data frame with the new column. This structure is now well suited for data analysis. We mainly focused on using regular expressions for data extraction, but they're used in a wide variety of areas, like data cleaning and data mining. They're also used for text parsing, which helps with code compilation, so it's good to know how to work with regular expressions. By now, you should understand how to use regular expressions to replace and extract patterns in your strings. Thank you for watching this video. Hello, and welcome. In this video, we'll show you how to work with calendar dates in the R programming language. R has a specialized object class for holding dates of a calendar. The output here may simply look like strings, but R actually represents a date as the number of days since January 1st of 1970. This particular representation for dates has become a standard across computer environments. And as a special note, the dates are based off of the Gregorian calendar. We are going to practice with the date format, but first, let's load up a database of Oscar-winning actors. As you can see, the date of birth for each actor is represented in a non-standard format. By checking the structure of the data frame with the str function, we see that the date of birth column is of type int. As it turns out, this number is represented in the Unix time format, another standard that counts the number of seconds since the beginning of January 1st, 1970. So we're going to have to reformat these values to work with R's date representation. In order to do this, we'll use the as.posixct function. POSIX is just another date format standard that R utilizes for its date class structure. But besides passing in the column we want to convert, we also need to provide the function with a reference point, which will be January 1st of 1970. The function's output will be a full timestamp, which will have this structure. Since we're only dealing with calendar dates, we don't need the hours, minutes, and seconds. So we'll need to use one more function to get to the format we need. The as.date function takes in a character string or a POSIX timestamp and converts it into a date class object. You can see the final result in the output here. Now let's consider another data frame that stores some information about Oscar-winning actresses. Like before, we can pass this data frame to the str function in order to see its structure. We've run into another issue since the date of birth column holds factors and not the date class. So we'll need to convert this column as well. Once again, we'll use the as.date, which works with both factors and character types. The additional parameter tells the function to expect the date format to be year, month, day in that order, separated by slashes. Doing this will successfully convert the column to the date class. Let's look at another example to understand the date formatting parameter. The first argument to the function is the string that we want to transform into a date object. The second argument once again tells R that the first argument has the structure day, month, year separated by slashes. As you can see here, R successfully parsed our string to form a date object. R allows you to specify the format in detail using the codes here, but by default, R will assume the date is year, month, day separated by hyphens or slashes. Notice that since our second parameter has a lowercase y for the year, R knew to look for a 2-digit year representation. There are several operations you can use on date objects. In this example, we simply subtract one date from another to get the number of days in between. Here we use a comparator to see if one date comes after another. You can also subtract a number from a date. In this case, the output is a date that is 14 days back in time. There are also 3 functions that return the date and time based on the system. SystemDate returns the current date as a date class object. The date function returns a character string describing the current date and time. And SystemTime returns the current time in a POSIX timestamp format. You can also apply some useful conversions on a date class object. The weekdays function converts the date into a string representing the weekday that the date falls on. The months function works similarly. And there's also a quarters function, which returns a string containing the quarter the date falls into. If you wish, you can convert your date to the Julian calendar. And as one last function, you can use the seq function to create a sequence of dates based on some reference point and length. This example starts at the current date and moves forward in 1-month increments. By now, you should understand how to create dates in R, as well as how to apply various useful operations. Thank you for watching this video. Hello, and welcome. In this video, we're going to show you how to deal with bugs in the R programming language. If you try to perform an invalid operation, R will alert you with the appropriate error message. Consider the piece of code here. Notice that we're trying to add a character type and a number together. When run, we see in the error output that one of the arguments is non-numeric. An important thing to note is that an error will halt the code's execution. If you look at this code, you'll see that we have a for loop that, under normal circumstances, would run 3 times. But when the error is encountered, the error message is output and the code stops immediately. The previous 2 examples were simple, but these errors can often be difficult to locate in a large body of code. The process of finding the source of these programming bugs and fixing them is known as debugging. If you know that an error might occur, you can catch the error while it's happening to avoid the halting of your script. The way to do this is by using a try-catch statement. A try-catch statement will run the code normally, assuming that there are no errors involved. You can see an example of normal execution here. But if we go back to our invalid addition statement, the try-catch will alert that this is invalid. At first it may seem like nothing new has happened, but try-catch has a special way of dealing with these types of issues. Pay close attention to the syntax here. Notice that we've added a custom print statement inside the parentheses. If the try-catch statement detects an error, it will run this code rather than printing out the default error message. However, if everything is okay, like when we added 10 plus 10, no error will be thrown and everything will run normally. You can even return a value rather than just running a print statement. Notice here that when the error is thrown, we simply return a concatenated string of the two values. It's worth re-examining our previous example with the for loop. The code inside the try-catch statement will run until an error is found. But after the first error is found, the try-catch will not resume execution of the main code inside the parentheses. This is why our custom message is only printed once, rather than 3 times. A try-catch statement will also allow you to catch warnings. Unlike an error, a warning will not halt the code, but it generally suggests that something undesirable is happening. For example, if you look here, you can see that we're passing in the letter A to the as.integer function. When this happens, R provides the warning displayed here. The syntax for catching a warning is similar to the syntax from before. Notice again that we've provided a custom print statement for when the warning occurs. By now, you should understand how to catch errors and warnings, as well as how to run your own code when they occur. Thank you for watching this video. Hello, and welcome. In this video, we will show you how to read CSV files, Excel files, and built-in datasets using the R programming language. A common file format for structured data is CSV, which stands for comma-separated values. CSV files store the data in a table format, and in each row, every column value is separated by a delimiter. As the name would suggest, this delimiter is traditionally a comma. In order to read a CSV data file, all we need to do is call the read.csv function while passing in the path to the file. We can also use R to read in XLS files, which is the file format of an Excel spreadsheet. But unlike CSV, R does not have a native function for reading Excel files. So to add this functionality, we're going to have to run the install.packages function. Once a package is installed, it does not need to be installed again unless it is uninstalled. Whenever you use a library that is not native to R, you have to load it into the R environment by calling the library function. After you've done so, reading an Excel file is as simple as calling read_Excel and passing in the path to the file. In order to make use of the data that we're reading, we need to assign the output to a variable. By default, R will structure the data as a data frame, which provides us with a lot of tools and flexibility. You can see here that after assigning the data to a variable name, we've used the variable name to get a preview of the data. The snippet you're seeing here shows the first 4 columns. Once we have the dataset loaded into a variable, we can start accessing its elements. So for example, say we wanted to access the name column highlighted here. To do so, we can directly reference the column name inside the square brackets. In this output snippet, you can see we get the elements of this particular column. You can also retrieve an entire row from a dataset, like the one highlighted here. Inside the square brackets, simply type the row number you want to access, followed by a comma, leaving the column blank. This will retrieve the selected row with all of the columns of the dataset. It may be the case that you want to retrieve a row, but you're only interested in a select number of columns, like the ones highlighted here. So we can access that row like before, but instead of leaving the column blank, we'll use the sieve function to form a vector with the columns we're interested in. As you can see in the output, this ensures that we only extract the desired columns. We've been working with data that we read in from a file, but R actually provides a number of built-in datasets that we can use. To see the available datasets, all we need to do is call the data function. The output returns all the datasets, each with a small description included. Everything in the datasets package is built in. Take a look at the CO2 dataset here. We're going to use this dataset to quickly show another utility function that R provides. R provides documentation for each of the datasets, which we can access by calling the help function along with the dataset's name. You can see that this provides a lot of information. The description will give you a better idea of the nature of the data, as well as the dataset's size. Since this dataset is built in, we don't need to import it or load it in order to start accessing the data. We can immediately start referencing it by name, since R has already prepared the dataset. So you can start to see what the CO2 data looks like in the output. By now, you should understand how to read and access CSV files, Excel files, and built-in datasets. Thank you for watching this video. Hello, and welcome. In this video, we're going to show you how to read in a text file using the R programming language. We'll also introduce several functions that provide useful information about the file. In order to demonstrate how to read these files, we're going to work with an example, which has the file path shown here. You can also take a quick look at the file's contents. Our example file contains 3 lines of text from Wikipedia's page on the 1995 movie Toy Story. One function that we can use to read the file is readLines. Notice that the argument to the readLines function is the file path from before. The text variable receives a character vector containing 1 item for each of the lines in the file. Keep in mind that a line is not the same thing as a sentence. Instead, lines are broken up by individual line breaks, which essentially form new paragraphs. Let's now take a look at the few functions we can apply to gain information about the file. In order to count the number of lines in the dataset, we can pass our text variable to the length function. The length function will simply count up the number of elements in the vector, which in this case is 3. The nchar function will count up the number of characters in each line of our character vector. You can see the result of that function here. Each value includes letters and numbers as well as symbols. If you'd like to know the size of your file, you can pass the file path to the file.size function. The output here is listed in bytes, which tells us that our example file has a size of 586 bytes. If you'd like to read a text file by word rather than by line, you can use the scan function while following the syntax you see here. Again, the first argument is simply a file path, and the second argument is just an empty string, but it is needed for our purposes. If you look at the output, you'll see the scan function produces a vector with each individual word as an element. By now, you should understand the functions that allow you to work with text files in the R programming language. Thank you for watching this video. Hello, and welcome. In this video, we'll show you how to export data from the R programming language into various file formats. Simple structures like strings and matrices can easily be saved in a text file. Consider the sample matrix here. In order to save this matrix to a file, we're going to make use of the write function. The file argument is simply the target file that we're going to save the data to. The nColumns argument specifies the number of columns that the data will be separated into. And the final argument specifies the separator between the elements. In our case, the elements will be separated by a space character. When working with something a bit more complicated, like a data frame, you may want to save the structure to a CSV file. To do so, you can use the write.csv function. Let's take a quick look at the arguments. The first argument is simply the data frame that you'd like to write to a file. The second argument is the path for the file you'd like to output. And row.names can be used to specify whether or not the file will display the name for each row. You can omit column names as well, but it's a bit trickier. You need to use the write.table function while making sure to add the parameter call.names equals false. Also notice the last parameter here. This ensures that all the values will be separated by commas, making it a true CSV file. You can save your data frames into an Excel file, but you'll need to rely on an external package, like the XLSX package here. If you've never installed the package before, run the install.packages function first. The library function will load the package into the R environment so that it can be used. Once you've done so, you can call the write.xlsx function to write the data to an Excel file. The syntax is similar to the CSV function from before, except we need to specify the sheet name. You can save and load R objects by using the R data format, along with the save function. Take a look at the function's syntax. The list argument takes in a vector, where each element is a variable name of the object you want to save. The file argument simply specifies the file to write to. The save argument specifies whether or not you want the save to be performed atomically. If this is false, there's a chance that the existing file could be damaged if the save fails. By now, you should understand how to export R data into text files, CSV files, Excel files, and R data files. Thank you for watching this video.
Welcome to HTTP Request and REST API. After watching this video, you will be able to explain how the HTTP protocol works, explain the role of the REST Application Programming Interface, or API, in transporting data across the web, and perform HTTP requests and process HTTP responses using the HTTR package. HTTP is probably the most used communication protocol for fetching web resources for clients from servers on the Internet. A resource can include a web page, media files, including images and video clips, or even a CSV file containing a dataset. Let's look at the basic workflow of HTTP. For example, assume that you want to open the home page of IBM Cloud in a browser on your mobile phone. This web page contains content and some media files. The browser uses the HTTP protocol to get all required resources and render them accordingly. First, the browser creates several requests. The requests can be distributed to a web server, which serves static or dynamic web pages, or a media file server, which serves images and videos. The servers respond to the requests by building HTTP responses and sending them back to the browser. After receiving and extracting the resources in the responses, the browser consumes the resources and renders the home page for you. The essential components of HTTP are the HTTP request and the HTTP response. Both the HTTP request and response are comprised of human-readable text called hypertext. Let's look at some core components of a request. The HTTP method describes the operation to be performed on the resource on the server side. Some common methods are the GET method, which requires a resource, the POST method, which sends data to the server for creating or updating a resource, the PUT method, which updates a resource, and the DELETE method, which deletes a resource. The URL, which stands for Universal Resource Locator, uniquely identifies a resource on the Internet. The request header contains some extra metadata about the request, such as the accepting language or the data format. Optionally, a request may also include a body, which contains the data to be sent to the server. The HTTP response includes a status code that indicates the result of the request. Some common status codes are 200, which means the request was successful, 404, which means that the requested resource was not found, and 403, which means the current request is forbidden. The response header includes some extra metadata sent by the server about the response, and the response body includes resource content, such as an HTML page or an image in raw bytes. HTTP is a low-level communication protocol. To help with the design and simplification of high-level distributed applications, such as web applications, representational state transfer, or REST was invented. The REST API is a web service that uses the REST architecture to handle a request on a front-end web service. REST is the most popular web API design standard, so most web APIs that you see today follow REST rules. REST has the following features. REST is resource-centric, meaning that the client should know the resource to be fetched, but not how it will be fetched on the server side. As such, the server and client should be loosely coupled. REST is stateless, which means that the server should not store any information about the connection context. Each request is independent. REST mostly uses JSON or XML to exchange data. By using JSON and XML, different applications on different platforms can communicate with each other without barriers. And finally, REST is a high-level standard. As such, it mostly uses HTTP as the low-level data transportation implementation. In most cases, making an HTTP-based REST call is like making an HTTP request. To work with HTTP requests or REST APIs in R, you can use a popular R package called HTTR. HTTR includes functions for the most common HTTP methods, like GET, POST, DELETE, and PUT. Once you have a basic understanding of HTTP, HTTR is easy to use. To make a basic GET request, simply call the GET function with a URL. The GET function returns an HTTP response wrapped in a response object. It includes a status code, headers, and a response body. To make a POST request, you must first prepare the data to be posted. In this example, the body is a simple list with a course name and an instructor name. Then use the POST function with the URL and the body argument. The POST function returns an HTTP response wrapped in a response object that includes a status code, headers, and a response body. In this video, you learned that HTTP is a communication protocol for fetching web resources for clients from servers on the Internet, and that each instance is comprised of a request and response. You also learned that the REST API is a web service that uses the REST architecture to handle a request on the front-end web service. And finally, you learned that you could perform common HTTP and REST operations using the HTTR package in R. Welcome to web scraping in R. After watching this video, you will be able to identify the components of an HTML page and then perform common web scraping tasks like reading, downloading, and extracting data from a web page using the RVest package in R. HTML stands for Hypertext Markup Language, and it is used mainly for writing web pages. An HTML page consists of many organized HTML nodes or elements that tell a browser how to render its content. Each node or element has a start tag and an end tag with the same name and wraps some textual content. Here is a simple HTML example. The HTML node is the root node, defining this markup file as an HTML page. The head node contains metadata about this page, such as its title. The body node defines the main body of the page. The body contains all content in the page, including headings, paragraphs, images, videos, audio, links, tables, lists, and more. And the P node defines a paragraph to hold some text starting from a new line. A node may also contain attributes. For example, the root HTML node has an attribute called lang that declares the language for this page. After an HTML file loads into a browser, the browser renders its content based on the HTML nodes. For example, the text in the title node appears on the browser title bar. Text in the H1 node, which stands for heading 1, renders with a large bold font. And text in a P node renders as a new paragraph in the page body. One key feature of HTML is that nodes can be nested within other nodes, organizing into a tree-like structure like the folders in a file system. For example, this HTML node is the root node, which has two child nodes, head and body. Since the head and body nodes have the same parent HTML node, they are siblings to each other. Similarly, the body node has two child nodes, the H1 and P nodes. It is important to understand this tree-like structure when writing a new HTML page or extracting data from an existing HTML page. Now, let us see how to parse an HTML page and extract some useful data from it. One simple way is to open an HTML page in a browser and manually copy and paste the data into a CSV or text file. However, this manual process would be very time-consuming if you have hundreds of thousands of pages to process. Instead, you can use web scraping, which is an automatic process of collecting and extracting data from web pages. Take this example. As an analyst, you may need to make some stock trading decisions. You would need to collect different kinds of information from various web pages, such as those containing the company's financial reports or historical stock prices. So, you can write a web scraping program to perform the data collection task for you. However, web scraping can be challenging, mainly because HTML pages are designed for humans, not for machines. HTML pages typically have extra style, layout, and script files to make web pages pretty and interactive for human users, but those add-ons bring extra efforts for web scraping. Luckily, there are many web scraping packages available for programmers to help with this task. The RVest package is a popular web scraping package for R. After RVest reads an HTML page, you can use the tag names to find the child nodes of the current node. Let us look at an example that uses RVest. Suppose you have a simple HTML page stored in a character variable called simple_HTML. Then, to return the root node, in this case the HTML node, load the simple_HTML variable into the RVest function called read_HTML. If you print the contents of the root_node, you will see all its child nodes, including the body node and a P node. More often, you want to read a public HTML page using its URL. For example, to get the homepage of IBM with the URL www.ibm.com, you can pass the URL to the read_HTML function and return the root HTML node for the web page. If you print the root node, you can see all its child nodes, including the head and body nodes. In some scenarios, you may need to download many HTML pages and then scrape them in offline mode. To do this, use the download.file function to download a page by its URL and save it as a local HTML file with a .html extension. Then, use the read_HTML function to read the local file, in this example, ibm.html. This is like reading HTML from a character variable or from a URL. Next, let's see how to extract specific node content. The following example extracts the text content of a P node from an HTML file. First, you use the read_HTML function to read the HTML text and return its root HTML node. Then, find its body node by using the HTML_node function, with root_node as one input and the body tag name as the second input. Next, since the P node is a child of the body node, you can still use HTML_node to return the P node. And finally, use the HTML_text function on the P node to return its text content as "this is an HTML page." To summarize this process, start with the root HTML node, find its child node body, and then, starting from the body node, find its child P node, and then use HTML_text to get its text content. In an HTML page, a table node works like a data frame. With RVest, you can easily extract an HTML table and convert it to an R data frame. Suppose you have a sample color table on the left showing the supported HTML colors, and you want to load it as an R data frame so you can analyze it using data frame-related operations. To do this, use the HTML_node function to find its child table node, and then call the HTML_table function to read this table node as a data frame automatically. If you print the data frame, you can see that all textual and numeric data is now stored in it. In this video, you learned that web scraping HTML pages is a common data analysis task that is made easier using the functions of the RVest package. You can use RVest to perform common tasks, such as reading HTML from a character variable, reading HTML from a URL, downloading a web page and reading it offline, extracting node data from a web page, and converting a table from a web page to a data frame. Hello, and welcome to this introductory course on SQL and relational databases and accessing them with R. This course is suitable for a variety of data and business professionals and anyone interested in leveraging the power of SQL and R for analyzing data. It is of special interest for aspiring data scientists. The demand for data scientists is high, boasting a median base salary of $114,000 and a job satisfaction score of 4.1 out of 5. It's no wonder that data scientist is the #2 job on Glassdoor's Best Jobs in America. Glassdoor analyzed data from the data scientist job postings on its site and found that SQL is one of the top skills required for a data scientist. Before you step into the field of data science, it is vitally important that you set yourself apart by mastering the foundations of this field. One of the foundational skills that you must have is SQL. SQL is a powerful language that's used for communicating with databases. Every application that manipulates any kind of data needs to store that data somewhere, whether it's big data, a database that spans multiple servers, a mobile phone that runs its own small database, or just a table with a few simple rows. If you are interested in data science, there are several advantages to learning SQL. Understanding SQL boosts your professional profile as a data scientist, as it is one of the most sought-after skills by hiring employers. It also provides you with a good understanding of relational databases. Tapping into all this information requires you to communicate with the databases that store the data. And even if you work with reporting tools that generate SQL queries for you, it may be useful to write your own SQL statements. Knowing how to write your own reduces your dependency on others to create SQL statements for you. The popularity of the R programming language continues to grow. In a recent TOBY index of programming language popularity, it ranked in the top 10 right after JavaScript. R plays an important role in data science and is a language of choice for many data scientists and data analysts for statistical analysis. It has a robust set of libraries for data analysis and visualization and is used by quantitative organizations such as those in the financial industry. When you combine the knowledge of SQL and R, you get a winning powerhouse combination for working with data and databases. In this course, you will learn the basics of both the SQL language and relational databases, as well as accessing them using the R programming language. You will start by learning some basic SQL commands and practice using them with a query tool. Then you will learn some relational database concepts, create a relational database instance on the cloud, and get hands-on experience working with tables. Next, you'll develop a working knowledge of SQL by filtering, ordering, and grouping result sets, as well as running nested queries and accessing multiple tables. When you have a good foundation in SQL and databases, you will apply what you've learned to working with SQL and databases using the R programming language. You will connect to a database from R, see how R data frame and database concepts align, and learn some strategies for working with data types. You will further learn the full process of designing and creating a database, loading it with data using R, and accessing and querying the data from R using Jupyter notebooks like a data scientist would. The course includes interesting quizzes and hands-on lab assignments where you can get experience working with databases. There is also a project included towards the end of the course where you will get an opportunity to apply the concepts you've learned by analyzing real-world datasets with SQL and R. So, let's get started.
Hello, and welcome to Retrieving Data with the Select statement. In this video, we will learn about retrieving data from a relational database table by selecting columns of a table. At the end of this lesson, you will be able to retrieve data from a relational database table, define the use of a predicate, identify the syntax of the select statement using the where clause, and list the comparison operators supported by a relational database management system. The main purpose of a database management system is not just to store the data, but also facilitate retrieval of the data. So, after creating a relational database table and inserting data into the table, we want to see the data. To see the data, we use the select statement. The select statement is a data manipulation language statement. Data manipulation language statements, or DML statements, are used to read and modify data. The select statement is called a query, and the output we get from executing this query is called a result set, or a result table. In its simplest form, a select statement is select star from table name. Based on the book entity example, we would create the table using the entity name book and the entity attributes as the columns of the table. The data would be added to the book table by adding rows to the table using the insert statement. In the book entity examples, select star from book gives a result set of 4 rows. All the data rows for all columns in the table book are displayed. In addition, you can also retrieve all the rows for all columns by specifying the column names individually in the select statement. You don't always have to retrieve all the columns in a table. You can retrieve just a subset of columns. If you want, you can retrieve just 2 columns from the table book. For example, book_ID and title. In this case, the select statement is select book_ID title from book. In this case, only the 2 columns display for each of the 4 rows. Also notice that the order of the columns displayed always matches the order in the select statement. However, what if we want to know the title of the book whose book_ID is B1? Relational operation helps us in restricting the result set by allowing us to use the clause where. The where clause always requires a predicate. A predicate is a condition that evaluates to true, false, or unknown. Predicates are used in the search condition of the where clause. So, if we need to know the title of the book whose book_ID is B1, we use the where clause with the predicate book_ID equals B1. Select book_ID, title from book, where book_ID equals B1. Notice that the result set is now restricted to just one row whose condition evaluates to true. The previous example used the comparison operator equal to in the where clause. There are other comparison operators supported by a relational database management system: equal to, greater than, less than, greater than or equal to, less than or equal to, and not equal to. Now you can retrieve data and select columns from a relational database table, define the use of a predicate, identify the syntax of the select statement using the where clause, and list the comparison operators supported by a relational database management system. Thanks for watching this video.
Hello and welcome. In this video, we'll briefly present a few useful expressions that are used with select statements. The first one is count. Count is a built-in database function that retrieves the number of rows that match the query criteria. For example, get the total number of rows in a given table. Select count star from table name. Let's say you create a table called medals, which has a column called country, and you want to retrieve the number of rows where the medal recipient is from Canada. You can issue a query like this. Select count country from medals where country equals Canada. The second expression is distinct. Distinct is used to remove duplicate values from a result set. Example, to retrieve unique values in a column. Select distinct column name from table name. In the medals table mentioned earlier, a country may have received a gold medal multiple times. Example, retrieve the list of unique countries that received gold medals, that is, removing all duplicate values of the same country. Select distinct country from medals where medal type equals gold. The third expression is limit. Limit is used for restricting the number of rows retrieved from the database. Example, retrieve just the first 10 rows in a table. Select star from table name, limit 10. This can be very useful to examine the result set by looking at just a few rows instead of retrieving the entire result set, which may be very large. Example, retrieve just a few rows in the medals table for a particular year. Select star from medals where year equals 2018, limit 5. In this video, we looked at some useful expressions that are used with select statements, namely the count, distinct, and limit built-in functions. Thanks for watching this video.
Hello, and welcome to the insert statement. In this video, we will learn about populating a relational database table. At the end of this video, you will be able to identify the syntax of the insert statement and explain 2 methods to add rows to a table. After a table is created, the table needs to be populated with data. To insert data into a table, we use the insert statement. The insert statement is used to add new rows to a table. The insert statement is one of the data manipulation language statements. Data manipulation language statements, or DML statements, are used to read and modify data. Based on the author entity example, we created the table using the entity name, author, and the entity attributes as the columns of the table. Now we will add the data to the author table by adding rows to the table. To add the data to the author table, we use the insert statement. The syntax of the insert statement looks like this: insert into table name, column name, values. In this statement, table name identifies the table. The column name list identifies each column in the table, and the values clause specifies the data values to be added to the columns in the table. To add a row with the data for Raoul Chong, we insert a row with an author underscore ID of A1, the last name as Chong, the first name as Raoul, the email as rfc@ibm.com, the city as Toronto, and the country as CA for Canada. The author table has 6 columns, so the insert statement lists the 6 column names, separated by commas, followed by a value for each of the columns, also separated by commas. It is important that the number of values provided in the values clause is equal to the number of column names specified in the column name list. This ensures that each column has a value. Tables do not need to be populated one row at a time. Multiple rows can be inserted by specifying each row in the values clause. In the values clause, each row is separated by a comma. For example, in this insert statement, we are inserting 2 rows, one for Raoul Chong and one for Rav Ahuja. Now you can identify the syntax of the insert statement and explain the 2 methods to add rows to a table, one row at a time or multiple rows. Thanks for watching this video. Hello, and welcome to the update statement and the delete statement. In this video, we will learn about altering and deleting data in a relational database table. At the end of this lesson, you will be able to identify the syntax of the update statement and delete statement, and explain the importance of the where clause in these statements. After a table is created and populated with data, the data in a table can be altered with the update statement. The update statement is one of the data manipulation language, or DML statements. DML statements are used to read and modify data. Based on the author entity example, we created the table using the entity name author and the entity attributes as the columns of the table. Rows were added to the author table to populate the table. Sometime later, you want to alter the data in the table. To alter or modify the data in the author table, we use the update statement. The syntax of the update statement looks like this: update table name set column name equal to value where condition. In this statement, table name identifies the table. The column name identifies the column value to be changed, as specified in the where condition. Let's look at an example. In this example, you want to update the first name and last name of the author with author underscore IDA2 from Rav Ahuja to Lakshmi Kata. In this example, to see the update statement in action, we start by selecting all rows from the author table to see the values. To change the first name and last name to Lakshmi Kata, where the author ID is equal to A2, enter the update statement as follows: update author set last name equal to Kata, first name equal to Lakshmi, where author ID is equal to A2. Now to see the result of the update, select all rows again from the author table, and you will see that in row 2 the name changed from Rav Ahuja to Lakshmi Kata. Note that if you do not specify the where clause, all the rows in the table will be updated. In this example, without specifying the where clause, all rows in the table would have changed the first and last names to Lakshmi Kata. Sometime later, there might be a need to remove one or more rows from a table. The rows are removed with the delete statement. The delete statement is one of the data manipulation language statements used to read and modify data. The syntax of the delete statement looks like this: delete from table name, where condition. The rows to be removed are specified in the where condition. Based on the author entity example, we want to delete the rows for author ID A2 and A3. Let's look at an example. Delete from author where author ID in A2, A3. Note that if you do not specify the where clause, all the rows in the table will be removed. Now you can identify the syntax of the update statement and delete statement, and explain the importance of the where clause in these statements. Thanks for watching this video. Hello, and welcome to SQL for Data Science. First, we will talk a little bit about what you'll learn in this course. This course teaches you the basics of the SQL language and the relational database model. There will be some lab exercises, and at the end of each section, there are a few review questions, and at the end, there is a final exam. By the end of this course, you will be able to discuss SQL basics and explain various aspects of the relational database model. In this video, we will learn about SQL and relational databases. By the end of this video, you will be able to describe SQL, data, database, a relational database, and list 5 basic SQL commands. But wait, what is SQL and what is a relational database? What is SQL? SQL is a language used for relational databases to query or get data out of a database. SQL is also referred to as SQL, and is short for its original name, Structured English Query Language. So SQL is a language used for a database to query data. But what is data? And what is a database? Data is a collection of facts in the form of words, numbers, or even pictures. Data is one of the most critical assets of any business. It is used and collected practically everywhere. Your bank stores data about you, your name, address, phone number, account numbers, etc. Your credit card company and your PayPal accounts also store data about you. Data is important, so it needs to be secure, and it needs to be stored and accessed quickly. The answer is a database. So, what is a database? Databases are everywhere and used every day, but they are largely taken for granted. A database is a repository of data. It is a program that stores data. A database also provides the functionality for adding, modifying, and querying that data. There are different kinds of databases of different requirements. The data can be stored in various forms. When data is stored in tabular form, the data is organized in tables, like in a spreadsheet, which is columns and rows. That's a relational database. The columns contain properties about the item, such as last name, first name, email address, city. A table is a collection of related things, like a list of employees or a list of book authors. In a relational database, you can form relationships between tables. So a database is a repository of data. A set of software tools for the data in the database is called a database management system, or DBMS for short. The terms database, database server, database system, data server, and database management systems are often used interchangeably. For relational databases, it's called a Relational Database Management System, or RDBMS. RDBMS is a set of software tools that controls the data, such as access, organization, and storage. An RDBMS serves as the backbone of applications in many industries, including banking, transportation, health, and so on. Examples of relational database management systems are MySQL, Oracle Database, DB2 Warehouse, and DB2 on Cloud. For the majority of people using a database, there are 5 simple commands to create a table, insert data to populate the table, select data from the table, update data in the table, delete data from the table. So those are the building blocks for SQL for data science. You can now describe what is SQL, what is data, what is a database, and what is a relational database. You know that RDBMS stands for Relational Database Management System. And you can list 5 basic SQL commands to create a table, insert data to populate the table, select data from the table, update data in the table, and delete data from the table. Thanks for watching this video.
Hello and welcome to Database Concepts. In this video, we will learn about different types of models, how we use models to map data to tables and define relationships between tables. At the end of this lesson, you will be able to explain the advantage of the relational model, explain how the entity name and attributes map to a relational database table, describe the difference between an entity and an attribute, identify some commonly used data types, and describe the function of primary keys. The relational model is the most used data model for databases because this model allows for data independence. Data is stored in a simple data structure, tables. This provides logical data independence, physical data independence, and physical storage independence. An entity relationship data model, or ER data model, is an alternative to a relational data model. Using a simplified library database as an example, this figure shows an entity relationship diagram, or ERD, that represents entities, called tables, and their relationships. In the library example, we have books. A book can be written by one or many authors. The library can have one or many copies of a book. Each copy can be borrowed by only one borrower at a time. An entity relationship model proposes thinking of a database as a collection of entities. Rather than being used as a model on its own, the ER model is used as a tool to design relational databases. In the ER model, entities are objects that exist independently of any other entities in the database. The building blocks of an ER diagram are entities and attributes. An entity can be a noun, person, place, or thing. In an ER diagram, an entity is drawn as a rectangle. Entities have attributes, which are the data elements that characterize the entity. Attributes tell us more about the entity. In an ER diagram, attributes are drawn as ovals. Using a simplified library as an example, the book is an example of an entity. Attributes are certain properties or characteristics of an entity and tell us more about the entity. The entity book has attributes such as book title, the edition of the book, the year the book was written, etc. Attributes are connected to exactly one entity. The entity book becomes a table in the database, and the attributes become the columns in a table. A table is a combination of rows and columns. While mapping, the entity becomes the table. Having said that, the table has not yet taken the form of rows and columns. The attributes get translated into columns in a table, providing the actual table form of rows and columns. Later, we add some data values to each of the columns, which completes the table form. Each attribute stores data values of different formats: characters, numbers, dates, currency, and many more besides. In the book table example, the title is made up of characters. As book titles vary in length, we can set the variable character data type for the title column, varchar. For character columns that do not vary in length, we use character or char. The edition and year columns would be numeric. The ISBN column would be char because it contains dashes as well as numbers, and so on. Using the book entity mapping as an example, we can create the tables for the remainder of our simplified library example using entity names like author, author list, borrower, loan, and copy. The entity attributes will be the columns of the tables. Each table is assigned a primary key. The primary key of a relational table uniquely identifies each tuple or row in a table, preventing duplication of data and providing a way of defining relationships between tables. Tables can also contain foreign keys, which are primary keys defined in other tables, creating a link between the tables. Now you know that the key advantage of the relational model is logical and physical data independence and storage independence. Entities are independent objects which can have multiple characteristics called attributes. When mapping to a relational database, entities are represented as tables and attributes map to columns. Common data types include characters such as char and varchar, numbers such as integer and decimal, and timestamps including date and time. A primary key uniquely identifies a specific row in a table and prevents duplication of data. Hello and welcome. This video will cover the key concepts around databases in the cloud. In order to learn SQL, you first need to have a database available to practice your SQL queries. An easy way to do so is to create an instance of a database in the cloud and use it to execute your SQL queries. After completing this lesson, you will be able to understand basic concepts related to cloud databases, list a few cloud databases, describe database service instances, as well as demonstrate how to create a service instance on an IBM DB2 on cloud. A cloud database is a database service built and accessed through a cloud platform. It serves many of the same functions as traditional databases with the added flexibility of cloud computing. Some advantages of using cloud databases include ease of use. Users can access cloud databases from virtually anywhere using a vendor's API or web interface, or your own applications whether on cloud or remote. Scalability. Cloud databases can expand and shrink their storage and compute capacities during runtime to accommodate changing needs and usage demands, so organizations only pay for what they actually use. Disaster recovery. In the event of a natural disaster or equipment failure or power outage, data is kept secure through backups on remote servers on cloud in geographically distributed regions. A few examples of relational databases on cloud include IBM DB2 on cloud, databases for PostgreSQL on IBM Cloud, Oracle Database Cloud Service, Microsoft Azure SQL Database, and Amazon Relational Database Services. These cloud databases can run in the cloud, either as a virtual machine which you can manage, or delivered as a managed service depending on the vendor. The database services can either be single or multi-tenant depending on the service plan. To run a database in cloud, you must first provision an instance of the database service on the cloud platform of your choice. An instance of a database as a service, or DBaaS, provides users with access to database resources in cloud without the need for setting up of the underlying hardware, installing the database software, and administering the database. The database service instance will hold your data in related tables. Once your data is loaded into the database instance, you can connect to the database instance using a web interface or APIs in your applications. Once connected, your application can send SQL queries across to the database instance. The database instance then resolves the SQL statements into operations against the data and objects in the database. Any data retrieved is returned to the application as a result set. Now let's see how a database instance is created for DB2 on cloud. IBM DB2 on cloud is a SQL database provisioned for you in the cloud. You can use DB2 on cloud just as you would use any database software, but without the overhead and expense of hardware, setup, or software installation and maintenance. Now let's see how we can set up a service instance of DB2. Navigate to IBM Cloud Catalog and select the DB2 service. Note there are several variations of the DB2 service, including DB2 Hosted and DB2 Warehouse. For our purposes, we will choose the DB2 service, which comes with a free Lite plan. Select the Lite plan. If need to, change the defaults. You can type a service instance name, choose the region to deploy to, as well as an org and space for the service. Then click Create. You can view the IBM DB2 service that you created by selecting Services from your IBM Cloud dashboard. From this dashboard, you can manage your database instance. For example, you can click on the Open Console button to launch the web console for your database instance. The Web Console allows you to create tables, load data, explore data in your tables, and issue SQL queries. In order to access your database instance from your applications, you will need the service credentials. For the first time around, you'll need to create a set of new credentials. You can also choose to create multiple sets of credentials for different applications and users. Once a set of service credentials is created, you can view it as a JSON snippet. The credentials include the necessary details to establish a connection to the database and includes the following: a database name and port number, a host name, which is the name of the server on the cloud on which your database instance resides, a username, which is the user ID you'll use to connect along with the password. Note that your username is also the schema name in which your tables will be created by default. Now that you know how to create a database instance on cloud, the next step is to actually go and create one. Thank you for watching this video. Welcome to Types of SQL Statements. At the end of this video, you will be able to distinguish between data definition language statements and data manipulation language statements. SQL statements are used for interacting with entities, that is, tables, attributes, that is, columns, and their tuples, or rows with data values, in relational databases. SQL statements fall into two different categories: data definition language statements and data manipulation language statements. Data definition language, or DDL statements, are used to define, change, or drop database objects such as tables. Common DDL statement types include create, alter, truncate, and drop. Create, which is used for creating tables and defining its columns. Alter is used for altering tables, including adding and dropping columns and modifying their data types. Truncate is used for deleting data in a table, but not the table itself. Drop is used for deleting tables. Data manipulation language, or DML statements, are used to read and modify data in tables. These are also sometimes referred to as CRUD operations, that is, create, read, update, and delete rows in a table. Common DML statement types include insert, select, update, and delete. Insert is used for inserting a row or several rows of data into a table. Select reads or selects row or rows from a table. Update edits row or rows in a table, and delete removes a row or rows of data from a table. Now you know that DDL, or data definition language statements, are used for defining or changing objects in a database, such as tables. And DML, or data manipulation language statements, are used for manipulating or working with data in tables. Thanks for watching this video. Welcome to Create Table Statement. At the end of this video, you will be able to explain how the entity name and attributes are used to create a relational database table. Now let's look at the most common DDL statement, create. The syntax of the create table is shown here. You start with create table, followed by the name of the table you want to create. Then enclose the rest of the statement inside a pair of parentheses or round brackets. Each row inside the parentheses specifies the name of a column, followed by its data type and possibly some additional optional values that we will see later. Each attribute or column definition is separated by a comma. For example, if we want to create a table for provinces in Canada, you would specify create table provinces, open parentheses, ID car, 2, primary key, not null, comma, name varchar, 24, close parentheses. In this example, the data types used are car, which is a character string of a fixed length, in this case 2, and varchar, which is a character string of a variable length. In this case, the variable character field can be up to 24 characters long. Issuing this statement would create a table in the database with two columns. The first column, ID, for storing the abbreviated two-letter province shortcodes such as AB, BC, etc. And the second column, called Name, for storing the full name of the province such as Alberta, British Columbia, etc. Now let's look at a more elaborate example based on the library database. This database includes several entities such as author, book, borrower, etc. Let's start by creating the table for the author entity. The name of the table will be author, and its attributes such as author_ID, first name, last name, etc. will be the columns of the table. In this table, we will also assign the author_ID attribute as the primary key, so that no duplicate values can exist. Recall, the primary key of a relational table uniquely identifies each tuple or row in a table. To create the author table, issue the following command. Create table author, open parentheses, author_ID, car2, primary key not null, comma, last name varchar 15, not null, comma, first name varchar 15, not null, comma, email varchar 40, comma, city varchar 15, comma, country car 2, close parentheses. Note that the author_ID is the primary key. This constraint prevents duplicate values in the table. Also note that the last name and first name have the constraint not null. This ensures that these fields cannot contain a null value, since an author must have a name. Now you know that create is a DDL statement for creating entities or tables in a database, and the create table statement includes definition of attributes of columns in the table, including names of columns, data types of columns, and other optional values if required, such as the primary key constraint. Thanks for watching this video. Hello and welcome to Alter, Drop, and Truncate tables. After watching this video, you will be able to describe the alter table, drop table, and truncate statements, explain the syntax, and use the statements in queries. You use the alter table statement to add or remove columns from a table, to modify the data type of columns, to add or remove keys, and to add or remove constraints. The syntax of the alter table statement is shown here. You start with alter table, followed by the name of the table that you want to alter. Differently to the create table statement, though, you do not use parentheses to enclose the parameters for the alter table statement. Each row in the alter table statement specifies one change that you want to make to the table. For example, to add a telephone number column to the author table in the library database to store the author's telephone number, use the following statement. Alter table author, add column, telephone_number, big int, semicolon. In this example, the data type for the column is big int, which can hold a number up to 19 digits long. You can also use the alter table statement to modify the data type of a column. To do this, use the alter column clause specifying the new data type for the column. For example, using a numeric data type for telephone number means that you cannot include parentheses, plus signs, or dashes as part of the number. You can change the column to use the car data type to overcome this. This code shows how to alter the author table. Alter table author, alter column telephone_number, set data type car, open parentheses, 20, close parentheses, semicolon. Altering the data type of a column containing existing data can cause problems, though, if the existing data is not compatible with the new data type. For example, changing a column from the car data type to a numeric data type will not work if the column already contains non-numeric data. If you try to do this, you will see an error message in the notification log and the statement will not run. If your spec changes and you no longer need this extra column, you can again use the alter tables statement, this time with the drop column clause to remove the column as shown. Alter table author drop column telephone _ number semicolon. Similar to using drop column to delete a column from a table, you use the drop table statement to delete a table from a database. If you delete a table that contains data, by default the data will be deleted alongside the table. The syntax for the drop table statement is drop table _ name semicolon. So you use this statement, drop table author semicolon, to remove the table from the database. Sometimes you might want to just delete the data in a table rather than deleting the table itself. While you can use the delete statement without a where clause to do this, it is generally quicker and more efficient to truncate the table instead. You use the truncate table statement to delete all of the rows in a table. The syntax of this statement is truncate table _ name immediate semicolon. The immediate specifies to process the statement immediately and that it cannot be undone. So, to truncate the author table, you use this statement, truncate table author immediate semicolon. In this video, you learned that the alter table statement changes the structure of an existing table, for example, to add, modify, or drop columns. The drop table statement deletes an existing table. And the truncate table statement deletes all rows of data in a table.
Hello, and welcome to Retrieving Data with Select Statement String Patterns. In this video, we will learn about some advanced techniques in retrieving data from a relational database table. At the end of this lesson, you will be able to describe how to simplify a select statement by using string patterns, ranges, or sets of values. The main purpose of a database management system is not just to store the data, but also facilitate retrieval of the data. In its simplest form, a select statement is select star from table name. Based on our simplified library database model and the table book, select star from book gives a result set of 4 rows. All the data rows for all columns in the table book are displayed. Or you can retrieve a subset of columns, for example, just 2 columns from the table book, such as book _ ID and title. Or you can restrict the result set by using the where clause. For example, you can select the title of the book whose book _ ID is B1. But what if we don't know exactly what value to specify in the where clause? The where clause always requires a predicate, which is a condition that evaluates to true, false, or unknown. But what if we don't know exactly what value the predicate is? For example, what if we can't remember the name of the author, but we remember that their first name starts with R? In a relational database, we can use string patterns to search data rows that match this condition. Let's look at some examples of using string patterns. If we can't remember the name of the author, but we remember that their name starts with R, we use the where clause with the like predicate. The like predicate is used in a where clause to search for a pattern in a column. The % is used to define missing letters. The % sign can be placed before the pattern, after the pattern, or both before and after the pattern. In this example, we use the % after the pattern, which is the letter R. The % sign is called a wildcard character. A wildcard character is used to substitute other characters. So, if we can't remember the name of the author, but we can remember that their first name starts with the letter R, we add the like predicate to the where clause. For example, select first name from author, where first name like R %. This will return all rows in the author table whose author's first name starts with the letter R. And here is the result set. 2 rows are returned for authors Raul and Rav. What if we wanted to retrieve the list of books whose number of pages is more than 290 but less than 300? We could write the select statement like this, specifying the where clause as where pages is greater than or equal to 290 and pages is less than or equal to 300. But in a relational database, we can use a range of numbers to specify the same condition. Instead of using the comparison operators greater than or equal to, we use the comparison operator between and. Between and compares two values. The values in the range are inclusive. In this case, we rewrite the query to specify the where clause as where pages between 290 and 300. The result set is the same, but the select statement is easier and quicker to write. In some cases, there are data values that cannot be grouped under ranges. For example, if we want to know which countries the authors are from. If we wanted to retrieve authors from Australia or Brazil, we could write the select statement with the where clause repeating the two country values. However, what if we want to retrieve authors from Canada, India, and China? The where clause would become very long, repeatedly listing the required country conditions. Instead, we can use the in operator. The in operator allows us to specify a set of values in a where clause. This operator takes a list of expressions to compare against. In this case, the countries Australia or Brazil. Now you can describe how to simplify a select statement by using string patterns, ranges, or sets of values. Thanks for watching this video. Hello, and welcome to Sorting Select Statement Result Sets. In this video, we will learn about some advanced techniques in retrieving data from a relational database table and sorting how the result set displays. At the end of this lesson, you will be able to describe how to sort the result set by either ascending or descending order and explain how to indicate which column to use for the sorting order. The main purpose of a database management system is not just to store the data, but also facilitate retrieval of the data. In its simplest form, a select statement is select star from table name. Based on our simplified library database model and the table book, select star from book gives a result set of 4 rows. All the data rows for all columns in the table book are displayed. We can choose to list the book titles only, as shown in this example. Select title from book. However, the order does not seem to be in any order. Displaying the result set in alphabetical order would make the result set more convenient. To do this, we use the order by clause. To display the result set in alphabetical order, we add the order by clause to the select statement. The order by clause is used in a query to sort the result set by a specified column. In this example, we have used order by on the column title to sort the result set. By default, the result set is sorted in ascending order. In this example, the result set is sorted in alphabetical order by book title. To sort in descending order, use the keyword des. The result set is now sorted according to the column specified, which is title, and is sorted in descending order. Notice the order of the first 3 rows. The first 3 words of the title are the same, so the sorting starts from the point where the characters differ. Another way of specifying the sort column is to indicate the column sequence number. In this example, select title, pages from book, order by 2 indicates the column sequence number in the query for the sorting order. Instead of specifying the column name pages, the number 2 is used. In the select statement, the second column specified in the column list is pages, so the sort order is based on the values in the pages column. In this case, the pages column indicates the number of pages in the book. As you can see, the result set is in ascending order by number of pages. Now you can describe how to sort the result set by either ascending or descending order, and explain how to indicate which column to use for the sorting order. Thanks for watching this video. Hello, and welcome to Grouping Select Statement Result Sets. In this video, we will learn about some advanced techniques in retrieving data from a relational database table, and sorting and grouping how the result set displays. At the end of this lesson, you will be able to explain how to eliminate duplicates from a result set, and describe how to further restrict a result set. At times, a select statement result set can contain duplicate values. Based on our simplified library database model, in the author table example, the country column lists the 2-letter country code of the author's country. If we select just the country column, we get a list of all of the countries. For example, select country from author order by 1. the order by clause sorts the result set. This result set lists the countries that authors belong to, sorted alphabetically by country. In this case, the result set displays 20 rows, 1 row for each of the 20 authors. But some of the authors come from the same country, so the result set contains duplicates. However, all we need is a list of countries the authors come from. So in this case, duplicates do not make sense. To eliminate duplicates, we use the keyword distinct. Using the keyword distinct reduces the result set to just 6 rows. But what if we wanted to also know how many authors come from the same country? So now we know that the 20 authors come from 6 different countries. But we might want to also know how many authors come from the same country. To display the result set listing the country and number of authors that come from that country, we add the group by clause to the select statement. The group by clause groups a result into subsets that has matching values for 1 or more columns. In this example, countries are grouped and then counted using the count function. Notice the column heading for the second column in the result set. The numeric value 2 displays as a column name because the column name is not directly available in the table. The second column in the result set was calculated by the count function. Instead of using the column name 2, we can assign a column name to the result set. We do this using the as keyword. In this example, we change the derived column name 2 to column name count using the as count keyword. This helps clarify the meaning of the result set. Now that we have the count of authors from different countries, we can further restrict the number of rows by passing some conditions. For example, we can check if there are more than 4 authors from the same country. To set a condition to a group by clause, we use the keyword having. The having clause is used in combination with the group by clause. It is very important to note that the where clause is for the entire result set, but the having clause works only with the group by clause. To check if there are more than 4 authors from the same country, we add the following to the select statement. Having count country greater than 4. Only countries that have 5 or more authors from that country are listed in the result set. In this example, those countries are China with 6 authors and India also with 6 authors. Now you can explain how to eliminate duplicates from a result set and describe how to further restrict a result set. Thanks for watching this video.
Hello and welcome. In this video, we'll go over SQL functions built into the database. So let's get started. While it is very much possible to first fetch data from a database and then perform operations on it from your applications and notebooks, most databases come with built-in functions. These functions can be included in SQL statements, allowing you to perform operations on data right within the database itself. Using database functions can significantly reduce the amount of data that needs to be retrieved from the database, that is, reduces network traffic and use of bandwidth. When working with large datasets, it may be faster to use built-in functions rather than first retrieving the data into your application and then executing functions on the retrieved data. Note that it is also possible to create your own functions, that is, user-defined functions, in the database, but that is a more advanced topic. For the examples in this lesson, let's consider this pet rescue table in the database for a pet rescue organization. It records rescue transaction details and includes the columns ID, animal, quantity, cost, and rescue date. For the purposes of this lesson, we have populated it with several rows of data as shown here. What are aggregate or column functions? An aggregate function takes a collection of like values, such as all of the values in a column, as input and returns a single value, or null. Examples of aggregate functions include sum, minimum, maximum, average, etc. Let's look at some examples based on the pet rescue table. The sum function is used to add up all the values in a column. To use the function, you write the column name within parentheses after the function name. For example, to add up all of the values in the cost column, select Sum Cost from Pet Rescue. When you use an aggregate function, the column in the results set by default is given a number. It is possible to explicitly name the resulting column. For example, let's say we want to call the output column in the previous query as Sum of Cost. Select Sum Cost as Sum of Cost from Pet Rescue. Note the use of as in this example. Minimum, as the name implies, is used to get the lowest value. Similarly, maximum is used to get the highest value. For example, to get the maximum quantity of any animal rescue in a single transaction, select Max Quantity from Pet Rescue. Aggregate functions can also be applied on a subset of data instead of an entire column. For example, to get the minimum quantity of ID column for dogs, select Min ID from Pet Rescue where animal equals dog. The average function is used to return the average or the mean value. For example, to specify the average value of cost as select Average Cost from Pet Rescue. Note that we can perform mathematical operations between columns and then apply aggregate functions on them. For example, to calculate the average cost per dog, select Average Cost divided by Quantity from Pet Rescue where animal equals dog. In this case, the cost is for multiple units, so we first divide the cost by the quantity of the rescue. Now let's look at the scalar and string functions. Scalar functions perform operations on individual values. For example, to round up or down every value in the cost column to the nearest integer, select Round Cost from Pet Rescue. There is a class of scalar functions called string functions that can be used for operations on strings, that is, char and varchar values. For example, to retrieve the length of each value in animal column, select Length Animal from Pet Rescue. Uppercase and lowercase functions can be used to return uppercase or lowercase values of strings. For example, to retrieve animal values in uppercase, select Uppercase Animal from Pet Rescue. Scalar functions can be used in the where clause. For example, to get lowercase values of the animal column for cat, select star from Pet Rescue where lowercase animal equals cat. This type of a statement is useful for matching values in the where clause if you are not sure whether the values are stored in upper, lower, or mixed case in the table. You can also have one function operate on the output of another function. For example, to get unique cases for animal column in uppercase, select Distinct Uppercase Animal from Pet Rescue. In this video, we looked at some built-in SQL aggregate functions, such as sum, minimum, maximum, and average. We also looked at scalar and string functions, such as round, lowercase, and uppercase. Thank you for watching. Hello and welcome. In this video, we'll go over date and time SQL functions built into the database. So let's get started. Most databases contain special data types for dates and times. DB2 contains date, time, and timestamp types. In DB2, date has 8 digits for year, month, and day. Time has 6 digits, hours, minutes, and seconds. Timestamp has 20 digits, year, month, day, hour, minute, seconds, and microseconds, where double X represents month and 6 Z's or Z's represents microseconds. Functions exist to extract the day, month, day of week, day of year, week, hour, minute, and second. Let us look at some examples of queries for date and time functions. The day function can be used to extract the day portion from a date. For example, to get the day portion for each rescue date involving cat, select day, rescue date, from pet rescue, where animal equals cat. Date and time functions can be used in the where clause. For example, to get the number of rescues during the month of May, that is, for month 5, select count, from pet rescue, where month, rescue date equals 05. You can also perform date or time arithmetic. For example, to find out what date it is 3 days after each rescue date. Maybe you want to know this because the rescue needs to be processed within 3 days. Select rescue date plus 3 days from pet rescue. Special registers current time and current date are also available. For example, to find out how many days have passed since each rescue date till now, select current date minus rescue date from pet rescue. The result will be in years, months, days. In this video, we looked at different types of built-in SQL functions for working with dates and times. Thank you for watching.
Hello and welcome. In this video, you'll learn how to write subqueries or nested select statements. Subqueries or subselects are like regular queries but placed within parentheses and nested inside another query. This allows you to form more powerful queries than would have been otherwise possible. An example of a nested query is shown. In this example, the subquery is inside the where clause of another query. Consider the employees table from the previous video. The first few rows of data are shown here. The table contains several columns, including an employee ID, first name, last name, salary, etc. We will now go over some examples involving this table. Let's consider a scenario which may necessitate the use of subqueries. Let's say we want to retrieve the list of employees who earn more than the average salary. To do so, we could try this code. Select from employees where salary is greater than average salary. However, running this query will result in an error like the one shown, indicating an invalid use of the aggregate function. One of the limitations of built-in aggregate functions, like the average function, is that they cannot always be evaluated in the where clause. So, to evaluate a function like average in the where clause, we can make use of a subselect expression like the one shown here. Select employee ID, first name, last name, salary from employees where salary is less than, open parenthesis, select average salary from employees, close parenthesis. Notice that the average function is evaluated in the first part of the subquery, allowing us to circumvent the limitation of evaluating it directly in the where clause. The subselect doesn't just have to go in the where clause. It can also go in other parts of the query, such as in the list of columns to be selected. Such subqueries are called column expressions. Now, let's look at a scenario where we might want to use a column expression. Say we wanted to compare the salary of each employee with the average salary. We could try a query like select employee ID, salary, average salary as average salary from employees. Running this query will result in an error indicating that no group by clause is specified. We can circumvent this error by using the average function in a subquery placed in the list of the columns. For example, select employee ID, salary, open left parenthesis. Select average salary from employees, closed right parenthesis, as average salary from employees. Another option is to make the subquery be part of the from clause. Subqueries like these are sometimes called derived tables or table expressions because the outer query uses the results of the subquery as a data source. Let's look at an example to create a table expression that contains non-sensitive employee information. Select star from Select Employee ID, First Name, Last Name, Department ID from Employees as Employee for All. The derived table in the subquery does not include sensitive fields like date of birth or salary. This example is a trivial one, and we could just as easily have included the columns in the outer query. However, such derived tables can prove to be powerful in more complex situations, such as when working with multiple tables and doing joins. In this video, you have seen how subqueries and nested queries can be used to form richer queries, and how they can overcome some of the limitations of aggregate functions. You also learned to use subqueries in the where clause, in the list of columns, and in the from clause. Thanks for watching this video.
Hello and welcome.
In this video, you will learn how to write queries that access more than one table. There are several ways to access multiple tables in the same query, namely using subqueries, implicit join, and join operators, such as inner join and outer join. In this video, we'll examine the first two options. The third option is covered in more detail in other videos. Let's consider the employees and departments tables from a previous video. The employees table contains several columns for categories such as employee ID, first name, last name, and salary, to name a few. The departments table contains a department ID, department name, manager ID, and location ID. Some sample data from these tables is shown here. We will utilize these tables for the examples in this video. In a previous video, we learned how to use subqueries. Now, let's use subqueries to work with multiple tables. If we want to retrieve only the employee records from the employees table for which a department ID exists in the departments table, we can use a subquery as follows. Select star from employees, where department ID in, select department ID, department from departments. Here the outer query accesses the employees table, and the subquery on the departments table is used for filtering the result set of the outer query. Let's say we want to retrieve only the list of employees from a specific location. We do not have any location information in the employees table, but the departments table has a column called location ID. Therefore, we can use a subquery from the departments table as input to the employee table query as follows. Select star from employees, where department ID in, select department ID, department from departments, where location ID equals L0002. Now, let's retrieve the department ID and department name for employees who earn more than $70,000. To do so, we will need a subquery on the employees table to satisfy the salary criteria, and then feed it as input to an outer query on the departments table in order to get the matching department info. Select department ID, department, department name from departments, where department ID, department in, select Department ID from employees where salary is greater than $70,000. We can also access multiple tables by specifying them in the From clause of the query. Consider the example, select star from employees, departments. Here we specified two tables in the From clause. This results in a table join, but note we are not explicitly using the join operator. The resulting join in this example is called a full join or Cartesian join because every row in the first table is joined with every row in the second table. If you examine the result set, you will see more rows than in both tables individually. We can use additional operands to limit the result set. Let's look at an example where we limit the result set to only rows with matching department IDs. Select star from employees, departments, where employees, department ID equals departments, department ID, department. Notice that in the where clause, we prefix the name of the column with the name of the table. This is to fully qualify the column name, since it's possible that different tables could have some column names that are exactly the same. Since the table names can sometimes be long, we can use shorter aliases for table names as shown here. Select star from employees E, departments D, where E, department ID, equals D, department ID, department. Here we define the alias E for employees table and D for departments table, and then use these aliases in the where clause. If we wanted to see the department name for each employee, we would enter the code as follows. Select Employee ID, Department Name from Employees E, Departments D, where E, Department ID equals D, Department ID, Department. Similar to before, the column names in the select clause can also be prefixed by aliases, as shown in the query, select E employee ID, D department ID, department, from employees E departments D, where E department ID equals D department ID, department. In this lesson, we have shown you how to work with multiple tables using subqueries and implicit joins. Thanks for watching.
In this video, we'll tell you why you should use R with databases. There may be several motivations using R with relational databases. The simplest case is that the data to be analyzed resides in a relational database, and R, well known for its powerful data analysis and data visualization capabilities, lends naturally to this purpose. But sometimes, even when the data to be analyzed does not reside in a relational database, there may be benefits for employing a relational database when using R to analyze that data. The reasons for it are as follows. One of the key limitations of analyzing data with R is that the data must reside in memory to complete most tasks. If the data resides in a relational database, SQL can be used to more efficiently extract subsets of the data for analysis within R. R is able to persist and retrieve data structures such as data frames, but the data is either stored in a binary format or it is converted into a text file. There is no simple method of updating or changing a few observations within a data frame without loading the data into R and then recreating the data file on disk. When the data is stored in a relational database, individual observations or rows can be easily changed. Relational database servers are designed for scalability and can easily support large data sets. Database servers provide concurrent access to these datasets to multiple users. Therefore, a single database could be used for generating standard summary reports using SQL, and the data could also be used to perform deeper analysis using R. Relational database servers ensure data integrity, consistency, and security. Any update to the data stored in a relational database must adhere to defined constraints, and updates are wrapped within atomic units known as transactions. Access to data can be managed using data control language statements, such as the SQL grant or revoke statement. Database servers can also be configured to provide a data audit trail to better understand any unauthorized data access. Before we move into the world of relational databases, let's examine how data can be stored and retrieved using R and files. To store and retrieve a single R object, the save RDS and read RDS functions can be used as shown. Notice how in this scenario we store the df1 object to a local file and then loaded the object into a new R object called df2. If you need to persist multiple objects, you can use the save function. There are two examples shown here. They both store an external representation of the df1 and df2 objects in a single file called multi.rda. These persisted objects can be retrieved using the load function. Notice how they are restored as objects with their original names and cannot be directly associated with a new object. If you wish to preserve all of the data structures in your current R workspace, you can use the save.image function. There are some other useful options available with these save functions, including the ability to compress the data as it is being stored. In this video, let's examine some terminology differences between R and relational databases. A relational database can be considered a collection of related data that is manipulated using a standard access language known as SQL, or structured query language. A database contains a set of data stored in tables or relations. A table can be considered a similar structure to an R data frame. Each table is given a name, and in most database servers, the name consists of two parts: schema, table, name. The first part of the name is known as the schema, followed by a period, and then the name of the table itself. Schemas are usually used to group a set of tables within a database, as a single database might be used for multiple applications and multiple users. In R, there are namespaces for function resolution, which could be considered somewhat similar to the use of schemas within a database. An R data frame is usually stored as a table, where each observation is considered a row or tuple, and each variable is known as a column or attribute. Therefore, a collection of observations would be stored as a single table. Relational data access is performed using SQL. The SQL standards are well established and fairly consistent among database servers. SQL is a declarative programming language. It is flexible and powerful. It is important to consider that there are times when R techniques of querying data, such as using the function subset, order, or using conditions within the bracket notation, is preferred to SQL, and other times when using the power of SQL is ideal. In this video, we'll look at the mapping of data between R and relational databases, as each database server has a slightly different set of supported data types. The examples shown here are from IBM databases, -DB, and DB2 on Linux, Unix, and Windows. Here we examine the mapping for numeric data types between R and database servers. The precision associated with R numeric data types can also vary across platforms and the R function. .machine can be used to examine the platform limits for your R environment. It returns platform details about numeric types and limits. The interface or driver between R and the database server should provide a configurable mapping for data types, as data is exchanged between R and the database server. One item to note here is that R double values will map to double data types in a relational database. But some database servers, such as DB2, provide more precision numeric data types, such as decimal, numeric, or des float. Character data in R will be mapped to either a fixed size character column or a variable size varchar column in a database. Usually logical data from R will be mapped to a single character column in a database. Dates are always a bit difficult to handle with R and within relational databases. You should consider using character strings for date or time representations as the information is exchanged between R and the database. If you are querying data from the database, the R driver may automatically detect that the data represents dates or times and map the data to an appropriate R class. But this is something you should validate once you start accessing data from databases. Factors should be converted to their native representation, which is usually character or integer values, as it is exchanged with the database server. Once the data has been retrieved from the database server, you can use the factor function to coerce the data into a categorical observation for your analysis tasks. To conclude this module, we should keep in mind some design considerations of relational databases. Relational databases are usually designed to minimize data redundancy. Data redundancy can lead to data anomalies and corruption and is generally avoided by design. Applying database normalization techniques reduce redundancy and improve usage of storage. Proper use of foreign keys also reduces data redundancy and the chance of destructive anomalies. In R, data redundancy must be handled manually with functions like unique and duplicated. Relational databases model the relationships between tables accurately. If the data has been modeled well, the consistency of the relationships and attributes are maintained. For example, relational databases can manage dependency relationships between two tables by specifying a primary key in the parent table and a related foreign key in the secondary table. This is often known as declarative referential integrity. These structures have no equivalent options within data frames in R. You may find that the data frame you would like to construct will require data from many different tables. Fortunately, database servers are very efficient at joining tables into a single structure for analysis. Often, databases have virtual tables or views defined to simplify this process of reconstructing a full data set. Of course, it is possible to create multiple datasets in R and use the merge function, but this operation is best avoided when a simple SQL join or predefined view object can be used. Relational databases are designed for transactions, which is a sequence of operations performed as a single logical unit of work. To qualify as a transaction, the unit of work must exhibit four properties: atomicity, consistency, isolation, and durability, commonly known as the ACID properties. Database security deals with various aspects of protecting the database content, its owners, and its users. It includes protection from unauthorized database uses and preventing corruption, destruction, or removal of data. On the other hand, how would you support the same transactional processing and security measures with R? Is it even possible? In this video, we'll look at database connectivity options. There are many different R packages available for database server data access. Your data might be stored in a relational or non-relational database store, but in this course we will focus on relational database servers only. The common interfaces for accessing relational databases from R are ODBC, which stands for Open Database Connectivity, and DBI-based, which stands for Database Interface Based. ODBC includes RODBC, i.e. Open Database Connectivity using R. DBI-based includes the following interfaces: database specific, which is based on DBI and includes R MySQL, R PostgreSQL, R Oracle, R SQLite, etc. JDBC, which stands for Java Database Connectivity and includes RJDBC, i.e. JDBC using R. One of the most popular R packages for database access is RODBC. This package uses the Open Database Connectivity or ODBC interface for data access. ODBC was originally developed by Microsoft in the early 1990s, and since it has become standardized as the ISO SQL CLI or call level interface. The RODBC package can be used with many different database servers. The setup requires a platform-specific ODBC driver manager and a database vendor-specific ODBC driver. The RODBC package provides convenient R functions to query and manipulate data stored in a relational database server. There's another set of alternative R packages for database access based on the DBI or database interface. DBI is a virtual interface as it relies on the individual DBI drivers to provide methods for the defined interfaces. There are DBI-based drivers for various database servers such as MySQL, PostgreSQL, and Oracle. There's also a package called RJDBC that uses JDBC drivers to provide connectivity and requires a JRE, i.e. a Java runtime environment. In this module, we'll start with RJDBC, but the focus will be primarily on using RODBC. In this video, we'll show you how to connect with RJDBC. RJDBC allows the use of JDBC to access databases from R. Specifically, RJDBC is a package implementing DBI, Database Interface, in R on the basis of JDBC, Java Database Connectivity. This allows the use of any DBMS in R through the JDBC interface. The only requirement is working Java and a JDBC driver for the database engine to be accessed. We will take a minute to show how the RJDBC package along with a JDBC driver can be used for connectivity to a database like DB2. We first load the RJDBC package in the R script and then create a JDBC object which is used to identify the driver to be used. The driver must be in the Java_path on the R client, as does the Java runtime environment. We then create a connection object to the specific server by supplying the host name or IP address, port information, database name, and the user ID and password. In this example, we issue a simple SQL select statement to retrieve all of the data from the US_fuel_economy data from August 2013. DBI defines a common set of functions that are to be implemented by the specific DBI-based driver. In this case, the RJDBC driver has implemented the dbConnect, dbSend query, and dbDisconnect functions. The fetch function will fetch 32K rows first and then continue fetching 512K rows until the remaining data is returned. If you know how many rows to expect, then you can replace the -1 parameter with the expected value to improve performance. Once the data is available in a data frame, we can use standard R expressions to extract the information we are interested in. Here we display the cars with the best fuel combined, fuel economy according to our data. Since there is a Java runtime environment required for this environment to work, it may not perform as well as interfaces that use native libraries to access data. One nice feature of the RJDBC interface is that it provides a mechanism to substitute arguments into SQL statements. In this example, we see that the manufacturer's name is substituted as an argument to the dbSend query function. Here we see the results that indicate that the Mini Cooper within the BMW family of vehicles has the best fuel economy. In this video, we'll look at database connectivity using ODBC. As previously mentioned, ODBC is a cross-platform standard for accessing databases. ODBC consists of two components, an ODBC driver manager and one or more ODBC drivers. The ODBC driver manager is platform-specific, i.e. for Windows, Linux, etc. ODBC drivers are database server-specific, i.e. for DB2, MySQL, and Oracle. RODBC provides R functions to interact with the database servers. Windows has an ODBC driver manager pre-installed, so the only additional component required is a supported ODBC driver for the database server. Each database must be configured using the Data Source Administration tool within the Windows control panel as shown below. A data source name, or DSN, is a detailed reference to a database that is either local or remote. To access the Data Source Administration tool, go to Control Panel, select Administrative Tools, then select Data Sources, ODBC. Here we are creating a user data source called RSample, which we will be using for some of our scripts. For other platforms like Linux, the ODBC driver manager must be installed along with the ODBC driver for the database server. The link to most commonly used ODBC driver manager for Linux is provided in the link shown here, unixodbc.org. You might be wondering where to find the ODBC driver for a database server. Usually drivers are provided at no cost by the database vendors or other third-party vendors. For example, for DB2 connectivity, there are a few different driver package options. If you plan to use DB2 utilities, such as the command line processor and possibly other non-ODBC programming interfaces, then you should download and install the IBM Data Server Driver package. If your computer will only be used for R data analysis, then you can download and install the IBM Data Server Driver for ODBC and CLI driver. Users of the DB2 service already get a cloud-based R runtime environment. Therefore, they do not need to install any of these drivers. However, if you want to connect a DB2 instance remotely, you can go to the Download section in the DB2 web console and download the driver package for the appropriate platform. Instructions for installing the DB2 drivers can be found in the link shown here. In this video, we'll cover RODBC in detail. First of all, outside of R, you'll need to obtain and install the ODBC driver for your database server. Then configure the ODBC DSN, i.e. data source name. If you don't know how to do this, you'll need to do some online research on ODBC and your database server. Now that we have the DSN created, we've completed the necessary steps outside of R. Within R, we will need to install RODBC package from CRAN using the install.packages function. CRAN refers to the Comprehensive R Archive Network, CRAN, which is a collection of sites that carry identical material consisting of the R distributions, the contributed extensions, documentation for R, and binaries. The CRAN master site can be found at the URL cran.r-project.org. First, install the RODBC package using the code shown here. In the example shown here, we use our first RODBC function called ODBC Data Sources to determine which databases are accessible from our R console. The ODBC Data Sources function returns a character vector of DSNs. In this example, we see that there are 6 DSNs registered, and the RSample DSN has been registered to use the IBM DB2 ODBC driver. This diagram shows the connectivity from R to DB2, or DB2 on cloud. Here we have visualization of how an R script connects to local or remote DB2 databases through the RODBC package and a valid DB2 ODBC CLI driver. As you can see in the diagram, the DB2 database could be on Linux, Unix, or Windows, and even on DB2 for Z, OS, or DB2 for I. A database connection can be established using the ODBC Connect or ODBC Driver Connect functions. The ODBC connect function requires separate parameters for the DSN, user ID, and password, and relies on an ODBC DSN to be already configured with details like driver, IP hostname, database name, etc. Both functions will return a connection object known as a channel in RODBC. These connection objects represent client resources on the database server, so it is important to close these objects at the end of your scripts when they are no longer needed. To properly determine if a connection object was established, you should verify that the object is not null and that it has a non-negative value. If a connection error occurs, a negative return value will be provided. This code shows how to bypass registration of DSN with ODBC Driver Manager. The ODBC Driver Connect function can be used to create a direct connection to a database server without a registered data source name or DSN. Since it does not rely on a pre-configured DSN, the ODBC Driver Connect function uses a specifically formatted connection string to establish a connection. This connection string includes the driver, database, hostname, port, etc. Here we see the proper format of a full connection string to a remote DB2 server. The string must include all of the attributes shown here to be successful. If the server is managed by someone else, you will likely need to request the connection information for you to start your data analysis tasks. Here we take a quick look at the attributes associated with an RODBC connection object. The key things to note here are case and rows_at_time. Database servers have different rules regarding valid names for database objects like tables. For example, it is possible to create table names using mixed case or lowercase, but it is highly recommended to use only uppercase table references whenever possible. When you establish a connection object using ODBC Connect, simply include the optional case parameter to ensure object references are always uppercase. Another optional connection parameter is called rows_at_time. If you are accessing a large number of rows into R for analysis, to improve query performance, you may want to change this parameter to return 1,000 rows instead of the default of 100. In this video, we'll cover how to discover metadata. Let's first determine the ODBC driver and level. This connection metadata can be obtained with the ODBC getInfo function using the code shown here. The output returns the version and platform of the database server you have established your connection with, and it will also state the ODBC conformance level. In this example, we note that they are connecting to a DB2 version 10.5 64-bit Windows server that conforms to the ODBC 3.5 standard. As we exchange data between R and a database server, it is important to keep in mind that there are different data types supported in these environments. The SQL typeinfo function can be used to determine the supported data types available with your database server, as shown in the code snippet. In the output, we see that this version of DB2 supports XML and many other data types. Since R has a very limited set of native data types, we will typically use only the core data types in the database server. In this module, we will focus on numeric, character, and date-time data for most of our analysis. As we retrieve or store data, we can control the data type mappings using various techniques. The SQL tables function will return a data frame of the tables, views, or other table-like objects from the database server. How can you tell which tables exist? What are the table types and the number of tables? For example, a typical R user would like to query data across multiple tables, and therefore a multiple table view can simplify the analysis task. It is a good idea to work with a database administrator to have them define views within the database that would provide the required data for your analysis work. So how many tables exist? In this example, we have 47 table-like objects available for use. There are optional parameters available with the SQL tables function to limit the results to only certain types of tables. Or table object names can be limited using wildcard characters as shown here. a data analyst must have some knowledge of the database schema or structure. This is usually best provided using an entity relationship or ER diagram from a database modeling tool such as IBM InfoSphere Data Architect. We want to preserve the integrity of the data as we analyze it using R. Therefore, as we query data from a relational database into an R data frame, it is important to understand the data types used to store the data in the database. There are two approaches to this task. We can either use a database-specific command or an equivalent RODBC function. Either of these options will provide us with the column names, data types, precision, size, and whether or not null values are allowed. SQL columns is an RODBC function. This code shows how to use the SQL columns function, and here is the output. The db2 command describe table, as shown here, will provide similar information. And here is the output. In this video, we will examine the task of obtaining data from an external data source and mapping it to a relational database design. The database design will be physically created using native database commands, both in a client server environment and in a database as a service or cloud environment. We will then also consider how the tables can be created directly from R without using native database commands. We have already used the RODBC SQL fetch function to return all of the rows from a relational table, but later we will see how we can use any valid SQL select statement to work with our data. We will also consider how to remove database objects from our database. Now let's examine the enrollment of students across the 5,000 or so different publicly funded schools in the province of Ontario in Canada. This school enrollment data is available on the Ontario government website and licensed under the Open Government License Ontario. On the Open Data, Province of Ontario Public School Data, data is structured and provided in a single delimited file. The issue is the redundancy of data. The opportunity is to design a database system to support many concurrent R users. As you can see here, each observation has redundant data, such as the school board number and name. If this data structure was designed for use in a relational database, it would be normalized to some degree. The data would likely be split into at least two different tables. One of the tables would be used to store information about each school board, and the other table would store information about each individual school. This is a somewhat trivial example of data analysis using R and a database, but you will likely encounter similar data sets, either pre-existing as database tables, database dump files, or raw data. We will consider our logical and physical database designed for this data, and then create the tables and load the data for our analysis. Here's a summary of the tasks that need to be done. Task 1. Create the logical and physical database designs. Tools are available that are extremely helpful for this task. IBM InfoSphere Data Architect is an excellent option here. Task 2. Clean and split the data into load files. Python or other tools languages are usually used for this task. Task 3. Create the physical database objects using database commands or using R. Task 4. Get the data into the database using database commands or using R. And finally, Task 5. Analyze the data in the database using R. What are the considerations? Now that we have some data to work with, and it's relatively small in this case, the steps are consistent even with large data sets. The only difference might be in the database design process and choice of database server. If you have extremely large amounts of data and no need to support data updates, sharing, or concurrent access, then you would likely load the data into a Hadoop cluster and use R to perform your analysis. In this scenario, we will use IBM DB2 as the database server, which can be on your local network or in the cloud. Let's review the tasks that need to be done with the considerations in mind. Task 1. Examine the data. We want to better understand the quality and nature of the data. Since we want the data to be analyzed from a database server, we should build a logical and physical model of the data using a tool like IBM InfoSphere Data Architect. These tools provide many benefits, especially if you expect more attributes to be added to the data over time. The data models can be easily maintained and shared with others. Task 2 could take a few minutes or a few hours depending on the quality of the data, and often this phase involves the use of tools such as Python. Task 3 involves the creation of tables to hold the data to be analyzed. This can be accomplished outside of R using database tools or from R using RODBC. Task 4 involves loading the data into the newly defined tables. Task 5 involves the use of R and/or SQL to extract data from the database and perform data analysis tasks. In this video, we'll look at database design and data preparation. We'll start with designing the database structures to support the data analysis, and then look at other applications that will also access the data. Relational database designers use a process called normalization to define logical models of the data, which will be managed within a given domain. In this example, we have a domain of schools and school boards or school districts. The database notation is referred to as an entity relationship diagram. For the data integrity rules or relationship, we say that school boards have a one-to-many relationship with the schools. A commonly used visualization for database modeling involves the use of entity relationship, or ER diagrams. This model is quite simple as there are only two relations or tables. We have called these tables board and school. The board table has 4 attributes or columns defined. The B_ID column is a primary key, and therefore a value must exist and it must be unique within the table. This attribute is defined as a character data type within the model. The other non-key attributes in the board table also contain character data. The school table has 5 attributes or columns defined. The S_ID attribute is a primary key, and there is a foreign key of B_ID identified to maintain a referential constraint between the two tables. This relationship is modeled to ensure that any new school must belong to a school board before the school can be created. Note that the ER diagram shows a one-to-many relationship based on the symbol shown in the connection line between the tables. This is a good review before we examine how to interface R scripts with relational databases. Now we need to examine the quality and format of the data provided. In this case, we realize that we should separate the data provided into 2 separate load files to match our relational database model. R is not an ideal programming language for cleansing and formatting data, so you may decide to use Python or other tools to prepare the data before moving the data into the defined tables. In this example, we created 2 delimited CSV files to match table definitions, as shown here. In this video, we'll be looking at Task 3, creating physical database objects. You will need to use your database model to create a physical database and the required database objects such as tables. For this example, we will use DB2 as our database server. The concept is similar for most relational database servers. To get started, we need to ensure a database or storage area has been allocated on our database server. We are using the DB2 command line processor to create 2 databases. The first database will automatically allocate storage, and the second example will create the database at a specific path. In DB2, the create database command will create system tables and log files in preparation for user data to be loaded to support your application needs. The connect command can then be used to ensure you can connect to the newly created database. By default, the creator of the database becomes the owner of all of its resources, and here we are connecting as the user called db2user1. We will examine 2 ways of creating tables. First, directly using native commands within the database server, and then from within R itself using RODBC functions. Now we will create the 2 tables, board and school. Here we have the SQL data definition language, or DDL statements to create the necessary tables and optional primary and foreign key objects in the database. This can be done using the web console in DB2 on cloud or the command line processor CLP in DB2. Some databases provide graphical tools and wizards for this purpose. With R, using RODBC, database objects are often created using database vendor tools, but they can be created directly from an R script using the SQL query function. Here we will use the SQL query function. Here we create the school table. Database tables can be dropped using the SQL drop function, and if you would like to maintain the table definition, but simply remove the data, you can use the SQL clear function to accomplish this task quickly. The SQL clear function will use the truncate table command for most database servers, including DB2. When you are using RODBC, it is best to use the errors parameter set to false so that any errors can be easily detected by checking the return value of the SQL query function. Here, we see that if an error occurs, the df2 variable will be set to -1 following the call to SQL query. We can then use the low-level ODBC getError message function to obtain the full message. The final block here provide the SQL state, SQL code, and the database error message from the server, and it also provides a second message that is generated by RODBC itself. Usually this information would be stored in an application log file and not directly displayed to the end user. In this video, we'll look at Task 4, loading the data. Database servers like DB2 on cloud provide several options for getting large amounts of data into a database. The import command performs SQL insert statements for a group of rows and then commits the transaction periodically. This technique is fine for a few thousand rows of data, but if you have hundreds of thousands or millions of rows of data, the load command is the better option. The load command will bypass the database transactional logging mechanism and store the data on disk very quickly. Once the data has been stored properly and an integrity check is complete, the table will be made available for applications to use. Therefore, in summary, to get the data into the database, use the import command for small to medium datasets. It uses the SQL insert statement as well as transactional logging. The load command, on the other hand, is best for large datasets. It bypasses the logging mechanism and is much faster. In this video, we'll show you how to query data using the SQL select statement. A full table select can be accomplished using the SQL fetch function as shown in this code snippet. The function will dynamically create a data frame and populate it with the data from the database server. Here is the output. Data mapping is determined by RODBC. It is defined in the database and when the data is retrieved. Avoid using empty tables. On this line, we see that the option strings as factors parameter is set to false. In this case, we wanted to ensure that character data remains as character data types in R. You may need to modify some of the data types after the initial data retrieval. For example, notice how the EMPNO column is defined a character data in the table, but RODBC decided to map the data to an integer data type in R. This also happened with phone data. You would also likely want to consider attributes like work department and job to be factors, instead of characters, as they represent categorical data types. Fortunately, the hire date and birth date columns were properly mapped to the POSIX CT data types in the data frame automatically, and the remaining numeric data was mapped from decimal data types in DB2 to double data types in R. Now let's try to make sense of the data and examine two data analysis scenarios. In scenario 1, we want to examine possible correlations between the age and the salaries of a group of employees. Of course, the data is stored in a database table, and we have retrieved the data using the SQL fetch function. First, we need to convert birth date to an age. In part A, we create a new variable called age. This variable is based on the values of the birth date variable. In part B, which is optional, we remove the birth date variable from our data frame by setting its value to null. In part C, we create a simple scatter plot of salaries and ages. In part D, we create a linear regression model and add it to our scatter plot as a blue line. And finally, in part E, we calculate the correlation of ages and salaries and add it to the plot as text. Now let's interpret the data for scenario 1. Here we see the plot that was generated. Our analysis has shown that there is very little correlation between ages and salaries. We can also see the outlier, which would likely represent the president or CEO of the company. The correlation between age and salary is practically non-existent. The outliers, are they the CEO or president? What is the distribution by age? The distribution of values is also a bit strange, as there are 4 employees who seem to be 10 or 11 years old. This might indicate a problem with the data set. Let's move on to scenario 2. In scenario 2, we decide to analyze the distribution salaries by job type. Are the salaries by job type reasonable? Here we need to consider job type as a factor or category variable. In part A, we modify the job variable to be a factor instead of a character vector. In part B, we create a box plot to show distribution and mean by job. The qplot or quick plot function from the ggplot2 package does a great job at visualizing data relationships. Box plots are used to visualize the median and distribution both within a category and across categories. Finally, here is our visualization of salaries within and across each job type. In this example, we generate a box plot with jitter of salaries by job category. Now let's interpret the data for scenario 2. This chart provides us with some insight regarding the distribution of salaries within a job category and between categories. Here we can see that the job type manager earns higher salaries than most other job types. In this video, we'll look at Task 5, Analyzing the Data. Now that the database tables have been populated and your R tools have been connected, you can start your analysis. Since you have a powerful database engine at your disposal, you should take advantage of any SQL functions that meet your data analysis needs to avoid shipping data back to R. Database stored procedures can also be used to limit the movement of data and increase performance. When data is to be retrieved into R, simply call the RODBC SQL query or SQL fetch functions. Here is an example of using SQL query to execute a SQL statement. Now we will take a quick look at a few visualizations of our school and school board data that we loaded. The code shown on the next 3 slides utilizes RJDBC. In the hands-on lab, we will write equivalent code using RODBC functions. Let's examine the code. We first load the RJDBC and ggplot2 libraries. Then enter the database credentials, and then create a connection string and connect to the database. We build the query based on the data that we want for the elementary school, and then execute the query. Then define the parameters for the corresponding histogram and plot. Then we create a similar query to get the elementary school data and execute the query. Again, we define the parameters for the histogram and plot. The third query that is executed gets the data for the Toronto District School Board. This code defines the data frames that we need. These statements print the data frames. And the last statement creates the density box plot for the secondary, elementary, and Toronto District School Board. Density plots are shown for elementary and secondary schools within the Toronto District School Board below. We can see that there is quite a different distribution of enrollment at elementary and secondary schools. There is a clear bimodal distribution of sizes for secondary schools and a normal distribution of elementary schools. The box plot tells us that secondary schools are larger on average than elementary schools. In summary, avoid data shipping if possible. Use SQL functions provided by the database vendor. Use stored procedures whenever possible. Create data frames using the RODBC SQL query or SQL fetch functions. Complete your analysis tasks using R.
Welcome to the Data Analysis with R course. Now that you have basic knowledge of R fundamentals, let's put that knowledge to work. After completing this course, you will know how to use data to solve your problems and make data-driven decisions. Data is growing at a very fast rate, and so are the ways in which data is being tapped by businesses, industries, institutions, and governments all over the world for making decisions that guide their future and the future of the people they serve. How much value we can derive from data really depends on just two things: the accuracy of data and the efficiency with which we are able to access the data we need when we need it. But you might ask, why should I learn data analysis? You use data analysis to derive value from data. With data analysis, you can firstly predict data trends, analyze and interpret data in meaningful ways, and finally, and most importantly, it solves the problems and derives effective decision-making in real-world scenarios. So, who is this course for? This course is for people who want to become a data analyst or a data scientist. This course starts with a question and then walk you through the process of answering it through data. You will first learn important techniques for preparing your data for analysis. You will then learn how to gain better understanding of your data through exploratory data analysis, helping you to summarize your data and identify relevant relationships between variables that can lead to insights. Once your data is ready to analyze, you will learn how to develop your model and evaluate and tune its performance. By following this process, you can be sure that your data analysis performs to the standards that you have set, and you can have the confidence in the results. In this course, we will use the real-world data from Data Asset Exchange. DAX offer high-quality datasets with clearly defined data licenses on the IBM developer website. We will use the airline dataset from DAX throughout this course. To learn more effectively and efficiently, please go through every video, check your learnings by completing the quizzes, connect with your peers on discussion platform, and consolidate your learnings by completing the hands-on labs and the final project. Now, equip yourself with the new data analysis skills and put data to work. Good luck.
Welcome to The Problem. In this video, you'll learn why data analysis is important by exploring a real-world scenario that requires it. You'll also learn about a source for sample data that you can use to learn data analysis techniques. As you know, data is everywhere. It's collected manually by scientists and collected digitally every time you click on a website or access an app on your mobile device. But data does not mean information. Data analysis, and in essence, data science, helps you answer questions by unlocking information and providing insights from raw data. So, data analysis plays an important role by helping you to discover useful information from the data, answer questions, and even predict the future or the unknown. To understand the importance of data analysis, it's helpful to look at a real-world scenario involving airline on-time performance. You may have volumes of data that track every flight, but can you predict the likelihood of a flight delay on a given airline? Data analysis in R helps you make sense of the data and answer this question and many more. By using the R packages, you can perform data cleaning, exploratory data analysis, model development, and model evaluation. Assume that you're working with an airline customer named Amy. Amy wants to choose a flight from Los Angeles to New York for a business trip. She has a tight schedule, so she wants to make sure her flight won't be delayed. But the problem is, she needs to predict the flight delay rate so she can decide which flight to book. Can you help Amy determine which flight to take? Think like a data scientist and clearly define some of the problems. For example, are there data on past flight delays and related impact factors? Are there factors that impact flight delays, like the destination weather, flight wheels, travel distance, or flight company? Or are there reasons for delays, like security, the carrier, or the national air system? Or does delay minutes in the past predict the future? As a data analyst or data scientist, you will start thinking about some of these questions. To answer these questions, you're going to need some data. The Data Asset Exchange has over 30 open and free datasets for you to use. This course uses the Airline Reporting Carrier On-Time Performance dataset. You can find this and other datasets by visiting the Data Asset Exchange website. This raw dataset is from the Airline Reporting Carrier On-Time Performance dataset. It's difficult to gain any useful insights from the data in this form, but after you import it into R, you can begin to discover useful information, answer questions, and predict the future or the unknown. In this video, you learned that the purpose of data analysis and data science is to help you transform information into answers and insights. You also discovered an important resource for sample datasets called the Data Asset Exchange that you can use to learn and test your data analysis techniques on real-world data. Welcome to Understanding the Data. In this video, you'll review the components of a commonly used file format for datasets, the CSV file, and then you'll explore the meanings of the variables in the Airline Reporting Carrier On-Time Performance dataset. The Airline Performance dataset is from the Data Asset Exchange, which you can find at ibm.biz/data-exchange. You can freely download it and other datasets from the website. The file for this dataset, here viewed as a table, is in CSV format, which separates each of the column values within a row with commas. This common file format is easy to import into many tools and applications. Each row in the table is an observation. Do you notice anything different about the first row? The first row is the header, which contains the names of each of the variables from the dataset. So each column displays a record of how the variable changes with each observation. Note that the terms column, variable, feature, and attribute are often used interchangeably. In the hands-on lab, you'll download and use the CSV file for this dataset. In this dataset, 21 columns from the original dataset have been selected, and you will perform statistical analysis on them. The origin column is set to LAX, and the dest, or destination column, is set to JFK. These two variables are the fixed variables in the scenario. You can now use the resulting dataset to predict the flight delay rate between the two cities. R delay is the target variable. This means that R delay is the value that you want to predict from the dataset. The predictors on the other variables listed, such as distance, carrier delay, weather delay, NOS delay, security delay, and late aircraft delay. The goal of this project is to predict R delay for a given flight date and airline. R delay refers to the arrival delay in minutes. If the value is positive, the flight arrived late. If the value is negative, the flight arrived early. Similarly, R delay minutes captures only the positive values in R delay. It only includes the situations when flights arrive late. Airlines report the reasons for delay in 5 broad categories that were created by the Air Carrier On-Time Reporting Advisory Committee: air carrier, extreme weather, national aviation system, security, and late arriving aircraft. There are variables for each cause in the dataset. You can find definitions for each carrier delay as well as definitions for all of the other variables in the airline carrier dataset in the data glossary at the link at the bottom of the slide. Understanding the meanings of each of the variables in your dataset is the first crucial step to data analysis. In this video, you learned about the variables in the Airline Reporting Carrier On-Time Performance dataset, including R delay and R delay minutes, the possible target values, and some of the other variables which may contribute to reasons for delay. Welcome to R Packages for Data Science. In this video, you'll learn about the tidyverse library, a collection of R packages that you can use to perform operations on your datasets. And you'll also learn how to select and filter data using some of the key functions in the dplyr package. An R package bundles together code, data, documentation, and tests and is easy to share with others. One of the reasons that R is so successful is that there is a large variety of packages available. There is a high chance that someone has already solved a problem similar to what you're working on, and you can benefit from their work by downloading their package. In this course, you'll primarily use the tidyverse library, which is a collection of essential R packages for data science. The core tidyverse library contains packages that you're likely to use in everyday data analysis. The tidyverse library is divided into 4 groups. The data wrangling and transformation group includes packages like dplyr and tidyr. The greatest advantages of these packages is you can use the pipe operator to combine different functions. From filtering to grouping the data, this package does it all. The data import and management group includes the reader package. This package solves the problem of parsing a flat file, like a CSV file, into a tibble. The functional programming group includes the per package. This package provides statistics for the dataset, such as calculating the mean value for each column. And the data visualization and exploration group includes the ggplot2 package. Data scientists love using ggplot2 to produce charts and visualizations, such as box plots, density plots, violin plots, tile plots, and time series plots. The dplyr package from the tidyverse introduces functions that perform some of the most common operations you'll use when working with data. There are 5 key dplyr functions. The select function selects variables by their names. The filter function filters observations based on values. The summarize function computes summary statistics. The arrange function reorders the rows, and the mutate function creates new variables. For example, let's say that you're only interested in a few of the columns in the airline dataset. You can use the select function to select only the columns that you want. You'll first specify the dataset you will perform the action on, in this case, sub_airline, and then the columns you would like to select. You can also filter the dataset to only show the American Airlines flights. You can use the filter function to return the rows where the reporting_airline is equal to AA. But what if you want to select a few columns and then filter the observations based on some criteria? To combine functions, use the pipe operator. You can read the pipe operator as then in the function. For example, you start with a dataset, then you select some columns, and then you perform a filter. This function combines the 2 separate steps in the previous slides. It applies the select and filter functions to the sub_airline dataset by first selecting the columns month, day of week, reporting_airline, and CRS dep time, and then filtering the rows where reporting_airline is equal to AA. You can use the pipe operator to combine as many functions as needed. In this video, you learned that tidyverse packages, including dplyr, tidyr, reader, per, and ggplot2, provide a wealth of functionality that you can leverage in your data analysis. Functions provided in packages like dplyr help you perform some of the most common operations you'll use when working with data, like selecting, filtering, summarizing, arranging, and mutating. And you can even combine functions using the pipe operator to build more powerful operations. Welcome to importing and exporting data in R. In this video, you'll learn how to import data using the R package reader. You can read data several ways, including from a file or a URL. After importing the data into R, you can perform all the subsequent data analysis procedures you need and export the results. Data acquisition is the process of loading and reading data from various sources. To read any data using the R Reader package, there are two important factors to consider: the format of the file and the file path of the dataset. The format is the way data is encoded. You can usually identify the different encoding schemes by looking at the file extension. Some common encodings are .csv, .json, .xlsx, and .hdf. The file path identifies where the data is stored. It can be stored on the computer you're using or online on the internet. For example, assume you downloaded the dataset of airline on-time performance from the Data Asset Exchange from a URL and saw something like this. Each row is one data point, or observation, and there are many properties associated with each data point. Because the properties are separated from each other by commas, you know the data format is .csv. At this point, these are just numbers and don't mean much to humans. But once you read this data into R, you can try to make more sense out of it. To use the dataset, you need to first load the tidyverse package in R. This is the first time you have used tidyverse, so you must first install it. After installing, load the tidyverse library. Loading the tidyverse library automatically loads the reader package. The reader package includes the read_CSV function, which you can use to read the .csv files into a data frame, also called a tibble, which is a special type of data frame. You can pass the location of the data you want to use to the read_CSV function as a file name. This example tells the function to find the data.csv file in a folder called lax_2_jfk on your computer. You can find the documentation for functions by adding a question mark before the function name. The documentation includes the arguments for the function and examples of their use. You can also import a dataset from a URL. The first step is to define a variable that contains the URL path to the file. In this example, the URL variable is assigned the URL to the airline dataset. The next step is to download the file locally using the download.file function. The first argument loads the URL variable, and the second argument provides a local name for the downloaded file. In this example, the destination file has the same name as the file in the URL. After the file is downloaded, unzip the content using the untar function. The final step is to read the data from the local file using the read_CSV function. This example specifies the path to the file that was created earlier by the download.file and untar operations. It also specifies the column types of div_distance and div_rdelay properties. The read_CSV function guesses column types from the first 1,000 rows of the input. While this is convenient and fast, it is not robust. If the imputation fails, you'll need to supply the correct types yourself. Use the col_types argument to override the default choices. After reading the dataset, you should look at the data frame to get a better intuition and to ensure that everything occurred the way you expected. Printing the entire dataset may take up too much time and resources, so to save time, you can use the head function to show the first 6 rows of the data frame. Similarly, the tail function shows the bottom 6 rows of a data frame. After completing some operations on your data frame, you may want to export it to a new .csv file. You can do this using the write_csv function. This example saves the data frame sub_airline as lax_2_jfk.csv to your computer. So far, you have read and saved only .csv files, but Reader also supports other data formats. This table shows the different data formats and the functions you can use to read files and save them to a different format. The code syntax for reading and saving other data formats is very similar to reading or saving a .csv file. In this video, you learned that there are different approaches to importing a dataset based on the format of the file and the file path. You also learned that you need to install and load a package like tidyverse before you can use it. And once installed, you can use its functions to perform operations like importing, reading, and exporting datasets. Welcome to Getting Started with Analyzing Data in R. In this video, you will learn why it is important to understand your data before you attempt to perform any data analysis on it. You'll also learn about several tidyverse functions that you can use to gain a better understanding of your data. So your data now is loaded, but before you start your analysis, it is important to first have a complete understanding of the data. You can explore the data to gain basic insights about the variable data types and how the data is distributed. You should also identify any potential issues with the data that might cause problems during your analysis. Some of the known data types in the tidyverse include integer, double, logical, character, and date. One way to determine the types of the variables in your dataset is to use the glimpse function. This function shows you the number of rows and columns in the dataset, and each column's name, type, and data preview. There are two reasons to check data types in a dataset. First, R automatically assigns types based on the encoding it detects from the original data table. For several reasons, this assignment may be incorrect. For example, what if the day of week variable, which you expect to contain a double type, is instead assigned the character type? In this case, you may need to manually change the data type to double. The second reason is that this allows you to see which R tidyverse functions can be applied to a specific variable. For example, some math functions can only be applied to numerical data. If these functions are applied to non-numerical data, an error will result. It is also important to understand the distribution of the data in your dataset. You can use the summarize and group_by functions to return a statistical summary of the data. This example returns the statistical summary of the reporting_airline variable that shows the distribution of the arrival delay time for each airline. The statistical metrics can tell you if there are mathematical issues that exist in a particular variable, such as extreme outliers and large deviations that you may have to address later. This method returns the mean value of arrival delay, but you can also select the standard deviation, median, or other metrics. In this video, you have learned why it is important to explore your data to gain basic insights about it, such as the variable data types and how the data is distributed. This also helps you identify any potential issues with the data that might cause problems during your analysis. You can also use functions to quickly view information that helps you understand the data. Welcome to Pre-Processing Data in R. In this video, you'll learn the purpose of pre-processing data in R, as well as simple data frame operations that you can perform during this process. If you're unfamiliar with the term, data pre-processing is a necessary step in data analysis. It is the process of converting or mapping data from one raw form into another format to prepare it for further analysis. Data pre-processing is also often called data cleaning or data wrangling. You will usually perform data frame operations along columns, with each row of the column representing a sample, for example, different flight status in the database. You can access a column by specifying the name of the column. For example, you can access R delay and dep delay. Each of these columns is a vector. There are many ways to manipulate data frames in R. For example, you can add a value to each entry of a column, or you can just add a value to the R delay column while leaving others blank. If you do not specify values in all columns, tidyverse fills the value with NA. In this video, you have learned that data pre-processing, otherwise known as data wrangling, is the process of converting or mapping data from the initial raw form into another format to prepare the data for further analysis. R provides many ways to manipulate data frames to assist in this process. Welcome to dealing with missing values in R. In this video, you will learn about the pervasive problems of missing values, as well as strategies you can take when you encounter missing values in your data. When no data value is stored for a variable for a particular observation, this variable has a missing value. Usually, a missing value in a dataset appears as a question mark, NA, 0, or just a blank cell. This example shows the first 12 rows of the airline dataset. There are a few missing values in the cause variables, like carrier delay, shown here, as well as other variables that we will explore later in the lesson. There are many ways to deal with missing values, and this holds true whether you're using Python, R, or any other tool. There is no one-size-fits-all approach. Different approaches fit in different contexts. Fortunately, there are some typical options you can consider. The first is to check if the person or group that collected the data knows something additional about the missing data and can determine what the missing values should be. Another possibility is to drop the data where the missing value is found. When you drop data, you can either drop the whole column or just the single data entry with the missing value. If you do not have a lot of missing data, usually dropping the entry is the best option. If you're dropping data, you want to take an approach that has the least amount of impact. To avoid wasting data, replacing data entries is often better than simply dropping them. However, it is less accurate because you need to replace missing data with a guess of what the data should be. One standard replacement technique is to replace missing values with the average value of the entire column, or in the airline dataset, you can replace it with the value 0, based on the assumption that most flights do not arrive late. What you replace missing data with is very dependent on the nature and context of the data. For example, suppose you have some entries which have missing values for the R delay column, and the column average for entries with data is 20. While there is no way for you to get an accurate guess of what the missing values under the normalized losses column should have been, you can approximate their values by using the average value of the column 20. But what if the values cannot be averaged, as with categorical variables? For a variable like reporting_flight, there isn't an average reporting flight type, since the values are not numbers. In this case, one possibility is to try using the mode, the most common flight, or drop the data point. And of course, in some cases, you may simply want to leave the missing data as missing data. For one reason or another, it may be useful to keep that observation, even if some features are missing. You can identify missing data in the dataset by checking the value of the is.na function. The first function uses is.na to count the number of missing values in a specific column, which is carrier delay in this example. In this second function, it uses is.na to count the missing values in all columns. All columns are specified by using the dot. From the output, you can see which variables have missing values, like carrier delay, weather delay, NOS delay, security delay, and so on. Now that you know that you have missing values, let's see how to drop or replace missing values. The easiest way to drop missing values is to manually drop specific rows or columns. In R, the complement of a set is given by the hyphen operator. This example drops the second, fourth, and sixth rows from the dataset. Similarly, you can also drop the second, fourth, and sixth columns from the dataset. To remove data that contains missing values, the tidyverse library has a built-in function called drop_na. Notice that carrier delay, weather delay, NOS delay, security delay, and late aircraft delay all have the same number of missing values from the summary. By inspecting the data, you can see that dropping the missing values in one column will also solve the missing value issues in the others, because they appear in the same rows. You're trying to predict the delay of flight arrival in your upcoming analysis, so you should remove the data points that don't have departure delay variables. You can do this with one line of code using drop_NA, open parentheses, data, close parentheses. In the drop_NA function, you need to specify the column names that contain the missing values you want to drop. So actually, entire rows are being dropped. This example drops the missing values in the carrier delay column. Do not forget that this line of code does not change the original data frame. The modified data will not be saved unless you point to a new variable. In this example, the new data is saved as carrier_delays. Now, if you compare the original dataset dimensions with this new one, the new one has less rows. This is because for every row that had carrier delay equal to NA, that entire row was dropped. To replace missing values, like NAs, with specified values, the tidyverse library has a built-in function called replace_NA. For example, assume that you want to replace the missing values in multiple columns with the value 0. Since carrier delay equals NA means there is no delay in carrier, the delay in minutes is 0, or carrier delay equals 0. Let's replace the missing values in columns carrier delay, weather delay, NOS delay, security delay, and late aircraft delay with zeros. You should always consult the documentation if you are not familiar with a function or method. The tidyverse webpage has lots of useful resources. There are, of course, other techniques you can use to deal with missing data, such as replacing missing values with the average of a group instead of the entire dataset. You learned to drop problematic rows or columns containing missing values, and then you learned how to replace missing values with other values. But don't forget the other ways to deal with missing data. First, you can try to find a dataset or source with higher quality data. Here, you don't need to worry about this because the data from the Data Asset Exchange is a reliable source to acquire datasets. Second, in some other cases, as the last resort, you may want to leave the missing data as missing data. In this video, you have learned about the importance of identifying missing data and developing a strategy for handling it. This may involve dropping or replacing the missing values, or working with the source of the data to either determine what the missing values should be or provide a better source of data. And sometimes the best strategy is to simply leave the missing values in place. Welcome to Data Formatting in R. In this video, you'll learn about data formats and why reformatting data can help improve your data analysis. You'll also learn about some ways you can standardize values in the same format, unit, or convention, including reformatting an entire column and correcting data types. Data is usually collected from different sources and by different people, and it may be stored in different formats. Data formatting means bringing data into a common standard of expression, which allows you to make meaningful comparisons. As part of dataset cleaning, data formatting ensures that data is consistent and easily understandable. For example, people may use different expressions to represent New York City, such as the abbreviations shown here. Usually, you want to treat them all as the same entity or format, so the statistical analyses will be easier down the road. The datasets from the Data Asset Exchange are already cleaned and handled by the IBM research team, so all the data is in coherent expressions. Coherence in statistics is an indication of the quality of the information within a single dataset. Fully coherent data is logically consistent and can be reliably combined for analysis. In the airline dataset, there's a column named Flight Date. The Flight Date column is in the format year-month-day. For example, 2003 for the year, 03 for March, and 28 for the day. You can reformat the Flight Date column into 3 separate columns: year, month, and day. In tidyverse, reformatting the date can be easily done with one line of code. This example uses the separate function to reformat the column, separating the date and renaming the 3 new columns as year, month, and day. For any number of reasons, including when you import a dataset into R or process a variable, the data type may be incorrectly established. For example, notice that the assigned data type for the flight date is character, although the expected data type should really be numeric. It is important for later analysis to explore the column's data type and convert them to the correct data types. Otherwise, the models that you later develop may behave strangely, and valid data may end up being treated like missing data. To identify column data types in R, you can use the sapply function to check the data type of each column in a dataset. And in situations where the data types are incorrect, you can use the mutate_all type.convert and mutate_if functions to convert them to different data types. This example converts the data type from character to integer in columns year, month, and day. In this video, you learned that reformatting data is a way to bring it into a common standard of expression, which helps you to then make meaningful comparisons. You also learned a couple of ways to reformat data, reformatting an entire column by using the separate function, or correcting data types by using the mutate_all and mutate_if functions. Welcome to Data Normalization in R. In this video, you'll learn about data normalization, an important technique to understand in data preprocessing. Different columns of numerical data may have very different ranges, and direct comparison is often not meaningful. Normalization is a way to bring all data into a similar range for more meaningful comparison. This video focuses on centering and scaling techniques. When you look at the airline dataset, you'll notice in the data that feature R delay ranges from -73 to 682. You may want to normalize these variables to minimize the effects of outliers. Normalization enables a fair comparison between the different features, and making sure they have the same impact is also important for computational reasons. Also, it can make some statistical analyses easier. Here is another example that will help you understand why normalization is important. Consider a dataset containing 2 features, age and income, where age ranges from 0 to 100, while income ranges from 0 to 20,000 and higher. Income is about 1,000 times larger than age and ranges from 20,000 to 500,000. So these 2 features are in very different ranges. When you do further analysis, like linear regression, the attribute income will intrinsically influence the result more due to its larger value. But this doesn't necessarily mean it is more important as a predictor. So the nature of the data biases the linear regression model to weigh income more heavily than age. To mitigate this, you can normalize these 2 variables into values that range from 0 to 1. Compare the 2 columns at the right. After normalization, both variables now have similar influence on the models you will build later. There are several ways to normalize data. Simple feature scaling divides each value by the maximum value for that feature. This makes the new values range between 0 and 1. Min-max takes each value, x_old, subtracted from the minimum value of that feature, then divides it by the range of that feature. Again, the resulting new values range between 0 and 1. And z-score, or standard score. In this formula, for each value, you subtract the mu, which is the average of the feature, and then divide it by the standard deviation, or sigma. In most scenarios, the resulting values often hover around 0 and typically range between -3 and +3. But can be higher or lower in some rare circumstances. Now, let's dive in and perform some computations. This example uses the simple feature scaling method, where each value in the R delay feature is divided by the maximum value in the feature. Using the max function, you can do this in just one line of code. This example uses the min-max method on the length feature. It subtracts each value by the minimum of that feature, then divides it by the range of that feature, the max minus the min. And this final example applies the z-score method on the length feature to normalize the values. It applies the mean and SD, or standard deviation, functions to the length feature. The mean function returns the average value of the feature in the dataset, and the SD function returns the standard deviation of the features in the dataset. In this video, you learned that normalization is a way to bring all data into a similar range for more meaningful comparison. There are several ways to normalize data, but you learned a few of the most common methods: simple feature scaling, min-max, and z-score. Welcome to binning in R. In this video, you'll learn about data binning. Binning creates categories which are discrete from numerical values which are often continuous. It is particularly useful for comparison between groups of data. Binning is a method of data pre-processing that you can use to group numerical values together into bins. For example, you can bin R delay into 0 to 5, 6 to 10, 11 to 15, and so on. Sometimes binning can improve accuracy of the predictive models. You can also use data binning to group a set of numerical values into a smaller number of bins to have a better understanding of the data distribution. For example, R delay has an attribute range from -73 to 682, with 2,855 unique values. Using binning, you can categorize arrival delays into 4 bins by quartiles. Quartiles refer to the boundaries that divide observations into 4 defined intervals. They are often determined based on the values of data points and how they are compared with the rest of the dataset. In tidyverse, you can easily implement binning. For example, assume you want 4 bins that contain equal numbers of observations, so you'll need 3 numbers as dividers: the first quartile, the second quartile, and the third quartile. The median of the dataset divides the dataset into 2 halves. The first quartile, or the lower quartile, is the median of the lower half of the dataset. You would denote this quartile as Q1. The second quartile, Q2, is the median of the whole dataset. The upper quartile, or the third quartile, Q3, is the median of the upper half of the dataset. You can get a sense on how the data appears by plotting a histogram before binning. Note, you don't need to master this code example. This is simply to show you how to get to the plot. From the plot, it's clear that most flights have 0 delays, and it is approximately bell-shaped while right-skewed. This bell-shaped curve is also known as the normal distribution. In normal or typical distribution, the probability that a random sample falls on either side of the average is the same. Right skewness means that the histogram has a longer tail on the right side. Now let's start binning. First, you'll use the dplyr function nTile to break R delay into 4 buckets, which each have equal numbers of observations of flight arrival delays. Then create a list quartile_rank that contains 4 bins, which are respectively labeled 1, 2, 3, 4. This puts the observations into different bins based on the flight's delay minutes. The larger the bin label is, the longer the flight was delayed. In this video, you learned that binning is a data pre-processing technique that groups a set of numerical values into a set of bins. Binning can improve the accuracy of predictive models and help you better understand the distribution of your data. You also learned a binning approach that divides numerical values into quartiles to improve data analysis. Welcome to turn categorical values to a numeric variable in R. In this video, you'll learn how to make statistical modeling easier by converting categorical values into quantitative values. Most statistical models cannot take in objects or strings as input, and for model training, only take the numbers as inputs. In the airline dataset, the reporting_airline feature is a categorical variable that has 9 values: AA, AS, B6, DL, HP, PA1, TW, and UA, or VX, which are in the character type. For further analysis, you'll need to convert these variables into some form of numeric format. To solve this problem, encode the values by adding new features corresponding to each unique element in the original feature you would like to encode. The feature reporting_airline has 9 values, so you create 9 new features: AA, AS, B6, and so on. When a value occurs in the original feature, you set the corresponding value to 1 in the new feature. The rest of the features are set to 0. In the reporting airline example, in the first row, the reporting airline is UA. Therefore, you would set the feature UA to 1 and the other features to 0. Similarly, for the second row, the reporting airline value is AS. Therefore, we set the feature AS to 1 and the other features to 0. In tidyverse, you can use the spread function to convert categorical variables to dummy variables. To do this, you need to define 3 arguments in the spread function: key, which is the column to convert into categorical values, reporting_airline; value, which is the value you want to set the key to, in this case, dummy; and fill, which fills the missing values as 0. Otherwise, they would be left as NAs. Alternatively, instead of assigning the dummy values 0 or 1, you can assign flight delay, R delay, values to each feature. In the reporting airline example, for the first row, the reporting airline is UA and the arrival delay is 2 minutes. Therefore, you can set the feature UA to 2 and leave the other features as NA or blank. Similarly, for the second row, the reporting airline value is AS and arrival delay is -21 minutes. Therefore, you can set the feature AS to -21 and leave the other features as NA or blank. To accomplish this, you will use the spread function. Continuing with the previous example, the key argument is set to the reporting_airline column, and for the value, you can choose to either convert the data to 0 or 1, or you can assign the values in the R delay column. This example does not declare a parameter fill, so the function will leave the missing values as NA. Also remember that the spread function drops the reporting_airline and R delay columns by default in output if you use them as arguments in the function. In this video, you learned a technique for turning categorical values to a numeric value. This technique is often called one-hot encoding and involves creating dummy variables by using the spread function and then converting the categorical variables to any dummy variables that make sense to you. Welcome to Descriptive Statistics. In this video, you'll learn about descriptive statistics, one approach you can use in exploratory data analysis. When you begin to analyze your data, it's important to first explore your data before you spend time building complicated models. One easy way to do so is to calculate some descriptive statistics for your data. The main question you are trying to answer in this module is, What causes flight delays? You'll learn some useful exploratory data analysis techniques that will help you answer this question, starting with descriptive statistics. Descriptive statistical analysis helps to describe the basic features of a dataset and generates a short summary about the sample and measures of the data. Let's review a couple of different useful methods for describing data. One way to do this is by using the summarize function in tidyverse dplyr. The group_by function is often used together with summarize to summarize each group into a single row summary of that group. Group_by takes as arguments the column names that contain the categorical variables for which you want to calculate the summary statistics. The summary statistics can show the mean, the total number of data points, the standard deviation, the quartiles, or the extreme values. Any NA values are automatically skipped in these statistics. The summarize function gives you a clear idea of the distribution of your variables. You can also have categorical variables in your dataset. These are variables that can be divided into different categories or groups and have discrete values. For example, this dataset has the reporting airline as a categorical variable, which consists of the categories UA, AS, DL, and 6 others. One way you can summarize the categorical data is by using count function. You can see that there are 1,096 flights from AA, American Airlines, 45 flights from AS, Alaska Airlines, 258 from B6, JetBlue Airlines, and so on. Box plots are a great way to visualize numeric data since you can visualize the various distributions of the data. A box plot shows the median of the data, which represents where the middle data point is, and the lower quartile shows where the 25th percentile is. The upper quartile shows where the 75th percentile is. The data between the upper and lower quartile represents the interquartile range. Next, you have the lower and upper extremes. These are calculated as 1.5 times the interquartile range above the 75th percentile, and as the 1.5 times the IQR below the 25th percentile. Finally, box plots also display outliers as individual dots that occur outside the upper and lower extremes. With box plots, you can easily spot outliers and the distribution and skewness of the data. Box plots make it easy to compare between groups. In this example of a box plot, you can see the distribution of different categories of the reporting airline feature over arrival delays. Notice that the distribution of arrival delays between the AA, AS, B6, and the other categories are similar, but the outliers of flight delays are much more distinct in different airlines. The lab for this module includes the code script used to create this box plot. You will often see continuous variables in your data. These data points are numbers contained in some range. For example, in the airline dataset, departure delays and arrival delays are continuous variables. What if you want to understand the relationship between departure delay and arrival delay? Could departure delay possibly predict arrival delay? One good way to visualize this is using a scatter plot. Each observation in a scatter plot is represented as a point. This plot shows the relationship between two variables. The predictor variable is the variable that you are using to predict an outcome. In this case, the predictor variable is the departure delay. The target variable is the variable that you are trying to predict. In this case, our target variable is the arrival delay since this would be the outcome. In a scatter plot, you typically set the predictor variable on the x-axis, or horizontal axis, and the target variable on the y-axis, or vertical axis. In this case, departure delay is on the x-axis, and arrival delay is on the y-axis. To generate the scatter plot, use the ggplot function passing in the x and y variables. It is important to label your axes and provide a plot title so you know what you are looking at. Now, how is the variable departure delay related to arrival delay? From the scatter plot, you can see that the departure delay time goes up. The time of the arrival delay also increases. You can find the code script to create this scatter plot in Lab 3. This is giving us an initial indication that there is a positive linear relationship between these two variables. In this video, you learned that descriptive statistics describe basic features of data and generate short summaries about the sample and measures of data. Using box plots and scatter plots, you can visualize data distribution and relationships in a visual way. Welcome to grouping data in R. In this video, you'll learn the basics of grouping and how you can use it to transform and visualize a dataset. Consider the following questions. Is there any relationship between the reporting airline and the flight delays? If so, does the day of the week of the flight have a relatively longer delay time? For example, people take flights for business trips most frequently on Mondays and Fridays. And does that impact the length of the flight delay? You could answer these questions by grouping the data by different reporting airline, and then compare the results for each day of the week against each other. In tidyverse, you can do this by using the group_by function. You can apply the group_by function to categorical variables and group the data into subsets according to the different categories of the variable. You can group by a single variable, or you can group by multiple variables by passing in multiple variable names. Let's say you are interested in finding the average delay minutes of flights and observe how they differ between different reporting airline and day of the week variables. To do this, first call on the dataset, and then group the data by reporting airline and day of the week in the second line. You are interested in knowing how the average flight delays differ across the board, so you can take the mean of arrival delay minutes on each group in the third line. The data is now grouped into subcategories, and only the average flight delay of each subcategory is shown. You can further your analysis by sorting the mean delays column with the longest delay values at the top. This example uses the arrange descending function to sort the mean_delays column in descending order and then prints the output table. According to the table, PA1, Pan America World Airlines, has longer flight delays on Fridays and Saturdays than the others, but a table is not easily readable and is difficult to visualize. To make the data easier to understand, you can transform this table into a heat map. A heat map is a data visualization technique that shows magnitude of a phenomenon as color in 2 dimensions. The variation in color may be by hue or intensity, giving obvious visual cues to the reader about how the phenomenon is clustered or varies over space. It is a great way to plot the target variable over multiple variables, and through this we get visual cues of the relationship between these variables and the target. In the average_delays dataset, both reporting_airline and day of week are listed in columns. A heat map has one variable displayed along the x-axis, and the other variable displayed along the y-axis. You can see that the top section of the heat map seems to have higher flight delays on average than the bottom section. A heat map is a more direct way to visualize the average flight arrival delays depending on reporting airline and the day of the week. To create the heat map in the previous slide, use the ggplot function. To do that, put reporting_airline on the x-axis and day of the week on the y-axis, and fill the value with mean_delays which you created previously. You can define the gradient color scales by using the scale_fill_gradient function and create a 2-color gradient, low and high. In the output plot, each reporting airline is placed along the x-axis, and the day of the week label is featured along the y-axis. The mean_delays are plotted with varying colors corresponding to the values on the color bar. For something more sophisticated, you can always add more blocks in your code. If you are interested in how to plot this heat map, check out Lab 3. In this video, you learned that you could answer more sophisticated questions about your categorical data by grouping or sorting it. And a visualization, like a heat map, can make this data easier to read by highlighting areas of interest. Welcome to Analysis of Variance, or ANOVA. After watching this video, you will be able to identify reasons for using an analysis of variance, or ANOVA, test in your data analysis. You'll also learn how to perform an ANOVA F-test and interpret the results. Let's say you want to analyze a categorical variable and see the correlation among different categories. For example, consider the airline dataset. The question you may want to ask is, how do different categories of the reporting airline feature as a categorical variable impact flight delays? This diagram shows the average flight delays of different airlines. To analyze categorical variables, such as reporting_airline, you can use the ANOVA method. ANOVA is a statistical method that stands for Analysis of Variance. You can use ANOVA to find the correlation between different groups of a categorical variable. In the airline dataset, you can use ANOVA to see if there is any difference in the average flight delays for the different airlines. So, the null hypothesis for ANOVA is that the mean, the average value of the reporting airline, is the same for all groups. The alternative, or research hypothesis, is that the average is not the same for all groups. In this scenario, the null hypothesis is that the mean values of AA and AS are the same, while the alternative hypothesis is that the mean values of AA and AS are not the same. The ANOVA test returns two values, the F-test score and the p-value. The F-test calculates the ratio of variance between the group's mean over the variation within each of the sample groups. The p-value shows whether the obtained result is statistically significant. Generally, if the p-value is smaller than 0.1 or 0.05, you can consider the variation to be statistically significant. Without going too deep into the details, the F-test calculates the ratio of variance between group means over the variation within each of the sample group means. This diagram illustrates a case where the F-test score is small because the variation of the prices in each group of data is way larger than the differences between the average values of each group. In this diagram, assume that Group 1 is AA and Group 2 is AS. Both are the reporting airline feature categories. Since the F-score is small, the correlation between arrival delay as the target variable and the groupings is weak. In this second diagram, notice that the F-test score is large. The variation between the averages of the two groups is comparable to the variations within the two groups. Assume that Group 1 is AA and Group 2 is PA1. Both are reporting airline feature categories. Since the F-test score is large, the correlation is strong in this case. Getting back to the example, the bar chart shows the average delay for different categories of the reporting airline feature. As you can see from the bar chart, you can expect a small F-test score between AA and AS because there is a small difference between the average delays. On the other hand, you can expect a large F-test score between AA and PA1 because the differences between the average delay is very significant. However, from this chart you do not know the exact variances. So let's perform an ANOVA test to see if your intuition is correct. The first line of this example extracts the reporting airline and flight delay data. Then it filters the data by different reporting airlines. You can perform the ANOVA test by using the AOV function in the stats package. Pass in the arrival delay data of the two airline groups that you want to compare, and it calculates the ANOVA results. The results confirm what you guessed at first. The prices between AA and AS are not significantly different, as the F-test score of 0.13 is less than 1 and p-value is larger than 0.05. You can do the same analysis for AA and PA1. The flight delays between AA and PA1 are significantly different, since the F-test score of 17.95 is very large and the p-value is 0.0000245, which is smaller than 0.05. From this result, you can say that there is a strong correlation between a categorical variable and other variables because the ANOVA test results in a large F-test score and a small p-value. In this video, you learned that using an ANOVA test helps you find correlations between different groups of a categorical variable. And you can determine the strength of the correlation by examining the F-test score and the p-score. Welcome to Correlation in R. After watching this video, you will be able to explain the difference between correlation and causation and plot data to determine if two variables have a strong or weak linear correlation. Correlation is a statistical metric for measuring to what extent different variables are interdependent. In other words, when you look at two variables over time and one variable changes, how does this affect change in the other variable? For example, smoking is known to be correlated to lung cancer because you have a higher chance of getting lung cancer if you smoke. In another example, there is a correlation between umbrella use and rain variables because precipitation means more people use umbrellas. Also, if it does not rain, people would not carry umbrellas. Therefore, you can say that umbrellas and rain are interdependent and, by definition, they are correlated. But it is important to know that correlation doesn't imply causation. In fact, you can say that umbrella usage and rain are correlated, but you do not have enough information to say whether the umbrella caused the rain or the rain caused the umbrella. In data science, we usually deal more with correlation. Positive correlation is a relationship between two variables in which both variables move in the same direction. A positive correlation exists when one variable decreases as the other variable decreases, or one variable increases as the other variable increases. Negative correlation is a relationship between two variables in which one variable increases as the other decreases, and vice versa. The value of a correlation coefficient ranges between -1 and +1. In statistics, a perfect negative correlation is represented by the value -1. A 0 indicates no correlation, and a +1 indicates a perfect positive correlation. A perfect negative correlation means the relationship that exists between two variables is -100% of the time. Look at the correlation between departure and arrival delay minutes. This time, visualize these two variables using a scatter plot and add a linear line called a regression line, which indicates the relationship between the two. The regression line is a visual summary of the relationship between two numerical variables. In this case, the departure delay minutes variable and the arrival delay minutes variable. The positive slope of the blue line suggests that there is a positive relationship between these two variables. With longer departure delay, the time of arrival delay will go up as well. As another example, look at the relationship between arrival delay and weather delay. As you can see in this plot, arrival delay is weakly positively related to weather delay. As the weather delay goes up, arrival delay barely goes up. This means that having a longer weather delay does not necessarily lead to an increase in arrival delay. Additionally, this graph demonstrates the relationship between carrier delays and late aircraft delays. As you can see in this plot, When carrier delay lasts longer, the last of late aircraft delay somehow goes down. Therefore, there is a weak negative linear relationship between carrier delay and late aircraft delays. Although this relationship is negative, the slope of the line is very flat, which means that the carrier delay is not a good predictor of late aircraft delays. These two variables are said to have a weak negative correlation. In this video, you learned that correlation measures to what extent different variables are interdependent. But correlation does not equal causation. You also learned that a positive correlation is a relationship between two variables in which both variables move in the same direction, while a negative correlation is a relationship between two variables in which one variable increases as the other decreases, and vice versa. Welcome to Correlation Statistics. In this video, you'll learn about the Pearson correlation and how you can use it to measure and determine the strength of the correlation between two or more variables. One way to measure the strength of the correlation between continuous numerical variables is by using a method called Pearson correlation. The Pearson correlation method provides you with two values, the correlation coefficient and the p-value. So, how do you interpret these values? For the correlation coefficient, a value close to 1 implies a large positive correlation, while a value close to -1 implies a large negative correlation, and a value close to 0 implies no correlation between the variables. The p-value measures the certainty of the correlation that you calculated. Roughly speaking, a p-value that is less than 0.001 indicates a strong certainty about the correlation coefficient. A value between 0.001 and 0.05 gives you moderate certainty. A value between 0.05 and 0.1 gives you a weak certainty, and a p-value larger than 0.1 gives you no certainty of correlation at all. So, when can you say the correlation between two variables is strong? There are two criteria you must meet. First, the correlation coefficient is close to 1 or -1, and second, the p-value is less than 0.001. This image shows data with different correlation values. In the top row, the correlation reflects the strength and direction of a linear relationship. In the middle row, the correlation not only shows the strength and direction, but also the slope of a linear relationship. In the bottom row, it shows many aspects of nonlinear relationships. Note that the figure in the center has a slope of 0, but in that case, the correlation coefficient is undefined because the variance of y is 0. This example looks at the correlation between departure delay and arrival delay using the correlation function, cor. This function takes two arguments, x and y, which are the variables you want to calculate the correlation for. Both values must be numeric, which includes integers or real numbers, such as 1, 2, 3, 1.5, or 6.7. Notice that the correlation coefficient is approximately 0.88. And because this is close to 1, there is a strong positive correlation. To examine whether the strong correlation is statistically significant, you must also calculate the p-value of this correlation using the cor.test function. Notice that the p-value is very small, much smaller than 0.001. So you can be certain that there is a strong positive correlation. To calculate correlations on multiple variables, you can use the rcor function from the H miscellaneous package. This function computes a matrix of Pearson's correlation coefficients for all possible pairs of columns. Then it returns a data frame with all correlations between the columns. This example uses the rcor function to calculate the correlations between 7 variables, including arrival delay minutes, departure delay minutes, carrier delay, weather delay, NOS delay, security delay, and late aircraft delay. Taking all variables into account, you can now create a heat map that visualizes the correlation between each of the variables with one another. The color scheme indicates the Pearson correlation coefficient, indicating the strength of the correlation between two variables. Notice the diagonal line with a dark red color. This indicates that all the values on this diagonal are highly correlated. This makes sense because when you look closer, the values on the diagonal are the correlation of all variables with themselves, which will always be 1. This correlation heat map gives you a good overview of how the different variables are related to one another, and most importantly, how these variables are related to arrival delays. This example uses the core plot function to plot an elegant graph of a correlation matrix. If you are interested in the code script that was used to create this heat map, you can check out Lab 3. In this video, you learned that the Pearson correlation measures the strength of the correlation between two or more variables. You also learned to measure the strength of a correlation by examining the correlation coefficients that are returned by the core and R-core functions, as well as interpreting the p-values using core.test. Welcome to Introduction to Model Development. After watching this video, you will be able to explain why model development is important to helping you answer questions about your data, the difference between independent and dependent variables, and the role of data relevancy in model development. The question is, can we predict the arrival delay of a flight? You can when you develop predictive models using relevant data. The model, or estimator, can be thought of as a mathematical equation used to predict a value given one or more other values. The model relates one or more independent variables or features to dependent variables. For example, you input a flight's departure delay as the independent variable or feature, and the output of the model, or dependent variable, is the arrival delay. Usually, the more relevant data you have, the more accurate your model is. For example, you input multiple independent variables or features to your model. Therefore, your model may predict a more accurate arrival delay for the flight. To understand why more data is important, consider the following situation. You have two flights to choose from that each depart at the same time, and the flights are from different airlines. You want to use your model to determine the arrival delay of two flights, one flight by Alaska Airlines and the other by Pan Am Airways. If your model's independent variables or features do not include the reporting airline, your model will predict the same arrival delay for flights that may differ, because arrival delay is likely correlated with the airline due to factors such as the quality of their management. In addition to getting more data, you can try different types of models. In this course, you will learn about simple linear regression, multiple linear regression, and polynomial regression. In this video, you learned that you could develop a model to help predict a value given one or more other values, and that models work by relating one or more independent variables to dependent variables. You also learned that you could develop more accurate models when you have more relevant data. Welcome to Simple Linear Regression. In this video, you'll learn how to apply the simple linear regression model for understanding the relationship between variables. And then you'll calculate a prediction based on the fitted model. Linear regression will refer to one independent variable to make a prediction. Multiple linear regression will refer to multiple independent variables to make a prediction. In this module, we'll focus on simple linear regression. Simple linear regression, or SLR, is a method for understanding the relationship between two variables, the predictor, or independent variable x, and the target, or dependent variable y. Assume you want to define a linear relationship between the variables shown here. The parameter b0 is the intercept, and the parameter b1 is the slope. When you fit or train the model, you will define these parameters, b0 and b1. This step requires lots of math, so we will not manually calculate this. The computer will do the job for us. Let's clarify the prediction step. It's hard to determine the length of a flight delay, but you can use the departure delay information to get some ideas. If you assume that there is a linear relationship between these variables, you can use this relationship to formulate a model to determine the delay of a flight. If the departure delay of a flight is 20, you can input this value into the model to obtain a prediction of an arrival delay of approximately 32 minutes. There are 4 assumptions associated with a linear regression model. Linearity. The relationship between x and the mean of y is linear. Independence. Observations are independent of each other. Homoscedasticity. The variance of the residual is the same for any value of x. And normality. For any fixed value of x, y is normally distributed. For example, assume you want to build a linear regression model of departure delay minutes and arrival delay minutes. Start by checking through the 4 criteria in the list. First, as departure delay takes longer, the average time of the arrival delay gets longer. Second, the error term is the same across all values of departure delay minutes. You can understand the error term to be the difference between the predicted value and the actual value of the arrival delay. Third, each observation of flight delay is independent of each other. And fourth, for the same value of departure delay, arrival delay is normally distributed. In other words, variable x, departure delay minutes, and variable y, arrival delay minutes, satisfy the 4 assumptions of linear regression. You will fit a linear regression between these 2 variables in the following slides. To determine the line, you take data points from the dataset marked in blue. You then use these training points to fit the model. The results of the training points are the parameters. You usually store the data points in a data frame as a numeric. The value you would like to predict is called the target. You'll store this value in the column Arrival Delay Minutes, or Array Y, and you'll store the dependent variable in the column Departure Delay Minutes, or Array X. Each sample corresponds to a different row in each data frame or array. In many cases, many factors influence the length of a flight delay. For example, the day of the week, or what generally causes the delay, such as the weather, security, or carrier-related issues. In this model, this uncertainty is taken into account by assuming a small random value is added to the point on the line. This is called noise. The figure on the left shows the distribution of the noise. The vertical axis shows the value added, and the horizontal axis illustrates the probability that the value will be added. Usually, a small positive value is added, or a small negative value. Sometimes large values are added, but for the most part, the values added are near 0. Let's summarize the process like this. You have a set of training points. You use these training points to fit or train the model and get parameters. You then use these parameters in the model. You now have a model. You use the hat character on the Y to denote the model is an estimate. You can use this model to predict values that you haven't seen. For example, you have no Alaska flights with a 60-minute departure delay. You can use your model to make a prediction for the arrival delay. But don't forget, your model is not always correct. You can see this by comparing the predicted value to the actual value. You have a sample for 60-minute departure delays of an Alaska flight, but the predicted value does not match the actual value. If the linear assumption is correct, this error is due to the noise, but there can be other reasons. To fit the model in R, you'll first define the predictor variable and target variable, and then follow several steps. For this example, let's start by creating a subset of the original dataset by selecting only Alaska flights and define it as AA delays. Then fit the predictor and target data values into a linear regression model using the LM function. And finally, use the summary function to view the result of fitting the linear model. The summary function produces result summaries of the results of various model fitting functions. This example shows you information about residuals, coefficients, the statistical significance of the model, and more. In reviewing the summary table, you get the values of B0 and B1. The relationship between departure delay and arrival delay is given by the equation in bold. Arrival delay minutes equals 17.35 plus 0.7523 times departure delay minutes, which reflects the equation you saw earlier in the video. You can now obtain a prediction using the predict function. But first, you need to create new data for the prediction. For this example, the names of the never seen data is new_dep delay. It is a data frame containing only one column, departure delay minutes, with 3 observations, 12, 19, and 24. These numbers were randomly selected and could be any set of numbers. You can now use the predict function in R, passing it to the linear regression model that you fitted previously, the new data, and the optional argument interval. This example specifies the confidence interval. When you print the pred object, you can see that there are 3 columns, fit, lower, and upper. The fit column contains the prediction results of the inputs, and the LWR and UPR columns are the lower bound and upper bound of the 95% confidence intervals of prediction results. The confidence interval reflects the uncertainty around the mean predictions. In this video, you learned how to fit a linear regression model based on a predictor, independent variable, and a target, dependent variable, and then calculate the prediction using the predict function. Welcome to Multiple Linear Regression. In this video, you'll learn how to apply the multiple linear regression model to understand the relationship between variables, and then you'll calculate a prediction based on the fitted model. Recall that linear regression will refer to one independent variable to make a prediction, while multiple linear regression will refer to multiple independent variables to make a prediction. In this module, we'll look at multiple linear regression. From the last session, recall that there are 4 assumptions associated with a linear regression model. Linearity, the relationship between x and the mean of y is linear. Independence, observations are independent of each other. Homoscedasticity, the variance of the residual is the same for any value of x. And normality, for any fixed value of x, y is normally distributed. You can use multiple linear regression to explain the relationship between one continuous target, y variable, and 2 or more predictor, x variables. For example, if you have 4 predictor variables, then B0 is the intercept, x equals 0, B1 is the coefficient or parameter of x1, and B2 is the coefficient of parameter x2, and so on. If there are only 2 variables, then you can visualize the values. Consider the following function. The variables x1 and x2 can be visualized on a 2D plane. For example, this table contains different values of the predictor variables x1 and x2. The position of each point is placed on the 2D plane and color-coded accordingly. Each value of the predictor variables, x1 and x2, will be mapped to a new value y, y hat, and the new values of y, y hat, are mapped in the vertical direction, with height proportional to the value that y hat takes. To fit the multiple linear regression, first define the dataset, or use the one you already defined in the simple linear regression example, AA_delays. Second, use the two predictor variables, connecting them with a plus sign, and then add them as the x parameter of the LM function. Finally, use summary to output the model results. Similar to simple linear regression, from the summary, you can derive the formula learned to predict arrival delay minutes. You can now use the predict function, following the same steps that you used with the simple linear regression example. First, create a new dataset with values for the two variables, carrier delay and late aircraft delay. Then, calculate the predictions using the predict function. So, to interpret the results, when carrier delay is 10 minutes and late aircraft delay is 20 minutes, then predicted arrival delay is 49 minutes. And we are 95% confident that the interval 45.33, 54.64 captures the true mean arrival delay for this instance. In this video, you learned how to fit a multiple linear regression model based on one continuous target, y, variable, and two or more predictor x variables, and then calculate the prediction using the predict function. Welcome to Assessing Models Visually. In this video, you'll learn how to assess models visually using a variety of methods to determine if they meet model assumptions. It is usually helpful to complement the numeric analysis of metrics with visualizations that help you understand the predictions and check whether there might be problems with your model. Also, you'll need to check the assumptions of a linear model, as previously stated, by checking for linearity, independence, normality, and equal variance. We will talk about the numeric metrics later in the course. In this part, you will learn about the visualization component. There are several ways to check the linearity of the relationships between the predictor and the outcome. In this lesson, you'll learn about two ways: regression plots and residual plots. Regression plots are a good estimate of the relationship between two variables, the strength of the correlation and the direction of the relationship, positive or negative. Here we show a regression plot as a combination of the scatter plot, where each point represents a different y, the target value, arrival delay minutes, and the fitted linear regression line y_hat, which represents the predicted value. As you can see, the scatter plot shows a linear relationship where, as departure delay minutes increase, arrival delay minutes also increase. There are several ways to plot a regression plot. One simple way is to use the ggplot function from the ggplot2 library. First, load the ggplot2 library. Then call the ggplot function. The parameter x is the name of the column that contains the dependent variable or feature, which is departure delay minutes. The parameter y contains the name of the column that contains the name of the dependent variable or target, which is arrival delay minutes. The parameter data is the name of the data frame. This example uses the AA_delays subset created in the previous section, which only contains flight data about Alaska Airlines without the missing values. The function geom_point creates a scatter plot that represents the data points of departure and arrival delays. The function stat_smooth plots the red line and gray confidence interval bands of the fitted linear regression model. The model to fit can be specified by the default is y/x. The result is this plot. This looks linear, but let's see what our other diagnostic plots say. When you run the plot of a model, the output is 4 different diagnostic plots. You can visually inspect these plots to get a sense of how you did on several of the assumptions outlined above. The first plot, residuals versus fitted, is useful for checking the assumption of linearity and homoscedasticity. Looking at this plot, you can see a few problems. R automatically flagged 3 data points that have large residuals, observations 82, 107, and 53. Besides that, the residuals do not appear to be linear because the red line plotted through the residuals is not straight. It also looks like the data is not homoscedastic, given that they do not appear evenly spread around the y equals 0 line. Let's talk about several cases of a residual plot and what they indicate. First, this is a good residual plot. You expect to see that the results have 0 mean and are distributed evenly around the x-axis with similar variance and no curvature. This type of residual plot indicates that the assumption of linearity and homoscedasticity is met. In this residual plot, there is curvature and the values of the error change with x-axis. For example, in this area, all the residual errors are positive. In this area, the residuals are negative. And in the final area, the error is large. The residuals are not randomly separated. This suggests the linear assumption is incorrect. This plot suggests a nonlinear function, which we will handle in the next section. In this plot, you can see that the variance of the residuals increases with x, therefore our model violates an assumption. The normality assumption is evaluated based on the residuals and can be evaluated using a quantile-quantile plot, or QQ plot, by comparing the residuals to ideal normal observations along the 45-degree line. R automatically identifies 3 data points that have large residuals, observations 55, 107, and 62. The plot shows some deviation from the straight line pattern, indicating a distribution with heavier tails than a normal distribution. So, what useful information can you read from a QQ plot? Let's look at 3 general situations and explain their implications. Here is how an optimal normal QQ plot appears, and it suggests that the error terms are normally distributed. This is an example where the QQ plot is heavily tailed. There are too many extreme positive and negative residuals, so the error terms are not normally distributed, and the relationship between the sample percentiles and theoretical percentiles is not linear. So the condition that the error terms are normally distributed is not met. This is an example where the QQ plot is skewed. From this plot, you can tell the distribution of the residuals must be quite skewed as well, so the error terms are not normally distributed. This means that the condition that the error terms are normally distributed has not been met. The scale location plot, which shows the square-rooted standardized residual versus the predicted value, is useful for checking the assumption of homoscedasticity. This example plot determines if there is a pattern in the residuals. If the red line you see on your plot is flat and horizontal, with equally and random spread data points, like the night sky, you're good. If your red line has a positive slope to it, or if your data points are not randomly spread out, you violated this assumption. In this case, R again flagged observations 62, 107, and 55. Besides that, there is not a horizontal line with randomly scattered data points around it, so the homoscedasticity assumption is not satisfied. This plot helps you find influential cases if any are present in the data. Not all outliers are influential in linear regression analysis. Even though data has extreme values, they might not be influential to determine a regression line. That means the results wouldn't be much different if you either include or exclude them from the analysis. The red dashed curved lines on the plot represents Cook's distance. If you don't have influential cases, the dashed red curve will be minor, with none of the data points crossing them, or the line will not present at all. For example, points with high leverage and high absolute residual, like the red dots, would be considered influential. However, looking at this plot, none of the points cross the dotted lines, but some points come close. Observations 62, 55, and 91 come close to being influential. You could still try to remove these observations, rerun this analysis, and determine how much the model improved. In this video, you learned that you could use visuals to check model assumptions, including linearity, independence, normality, and equivariance, or homoscedasticity. You also learned some methods for visually assessing models, including regression plots, diagnostic plots, residual plots, quantile-quantile plots, scale location plots, and residuals versus leverage plots. Welcome to polynomial regression. In this video, you will learn about using polynomial regression for nonlinear model development, transforming data using the orders of polynomial regression, and fitting the model in R. What do you do when a linear model is not the best fit for your data? Let's look into another type of regression model, polynomial regression. Polynomial regression is a special case of general linear regression. With this model, you transform your data into a polynomial and then use linear regression to fit the parameter. This method is beneficial for describing curvilinear relationships. A curvilinear relationship is what you get by squaring or setting higher order terms of the predictor variables in the model, thus transforming the data. The model can be quadratic, which means that the predictor variable in the model is squared. This is a second-order polynomial regression with a figure representing the function. The model can be cubic, which means that the predictor variable is cubed. This is a third-order polynomial regression. Looking at the figure on the right, you can see that the function has more variation. There also exists higher-order polynomial regressions when a good fit hasn't been achieved by a second or third order. You can see in the figures how much the graphs change when you change the order of the polynomial regression. The degree of the regression makes a big difference and can result in a better fit if you pick the right value. Even though the data is nonlinear, that is, the model is a polynomial function of x, since the x is squared or cubed, etc., the model in all cases is linear in the regression coefficients. That is, the b0, b1 are never squared or cubed, etc. These values are what are learned by the model, which is why polynomial regression is still considered a special case of general linear regression. Let's look at an example. Suppose you have data for time and temperature. You can do a quick plot to see the relationship between them. In the plot, you can see a curvilinear pattern of data that can be modeled through a second-degree polynomial, as shown in the following equation. In R, to fit a polynomial regression model, use the LM function together with the poly function. The poly function is especially useful when you want to obtain a higher degree. You must also specify raw equals true so you can get the coefficients. To see the result, call the summary function. The symbolic form for the model is given by the following expression: negative 13.7 plus 3.76 times 1 minus 0.14 times 1 squared. You can also plot the fitted polynomial model by using the geom smooth function and specifying the method and the second-order polynomial formula. In this video, you learned that polynomial regression is a special case of the linear regression model that is useful for describing curvilinear relationships. And polynomial regression models can be quadratic, cubic, or higher order, and you can specify the order when fitting the module using the poly function. Welcome to Assessing the Model. In this video, you'll review two of the most common metrics that you can use to assess regression models: the mean squared error, or MSE, and R-squared. Now that you've seen how to evaluate a model by using visualization, you'll want to numerically assess your models. There are several metrics to evaluate regression models, but the most popular ones are the mean squared error, or MSE, the root mean squared error, or RMSE, the mean absolute error, or MAE, and R-squared. In this video, we will focus on MSE and R-squared. To measure the MSE, you find the difference between the actual value y and the predicted value y hat, and then square it. In this case, the actual value is 150, and the predicted value is 50. Subtracting these points, you get 100. You then square the number, so in this example, you get 100 squared. You then take the mean or average of all errors by adding them all together and dividing by the number of samples. The MSE is the mean of the square of the residuals. You can get this value in R by squaring the residuals from the model and then taking the mean. In this example, the MSE is 394. One caveat with MSE is that because you are squaring the values, the unit is also going to be squared. Therefore, the number you get here will be hard to interpret. The solution is to calculate the RMSE, which is the square root of the MSE. This will have the same units as the target variable. In addition to MSE, R-squared is another metric used in regression. R-squared is also called the coefficient of determination. It's a measure to determine how close the data is to the fitted regression line. That is, it can tell you the percentage of variation of the target variable, y, that is explained by the linear model. You can think about R-squared as comparing an estimated regression model to a simple model, such as the mean of the actual data points. If the variable x is a good predictor, your model should perform much better than just the mean. Before you can calculate R-squared, you must first get the average of the data points, or y-bar. In this example, this value is 6. The coefficient of determination, or R-squared, is 1 minus the ratio of the MSE of the regression line divided by the MSE of the average of the data points. For the most part, R-squared is a value between 0 and 1. Let's look at a case where the line provides a relatively good fit. The blue line represents the regression line. The blue squares represent the MSE of the regression line. The red line represents the average value of the data points, and the red squares represent the MSE of the red line. Notice that the area of the blue squares is much smaller than the area of the red squares. In this case, because the line is a good fit, the MSE is small, therefore the numerator is small. The MSE of the line is relatively large. As such, the numerator is large. A small number divided by a larger number is an even smaller number. Taken to an extreme, this value tends to 0. If you enter the value from the previous slide for R-squared, you get a value near 1. This means the line is a good fit for the data. Here is an example of a regression line that does not fit the data well. If you just examine the area of the red squares compared to the blue squares, you see that the area is almost identical. Therefore, the ratio of the areas is close to 1. Using the formula for R-squared, you can enter the ratio found in the previous slide. In this case, R-squared is near 0. This regression line performs about the same as just using the average of the data points. Therefore, this line did not perform well. It is important to emphasize that R-squared values are between 0 and 1. Recall that when you run the summary of a model in R, you get several values, including R-squared. You can extract R-squared from the summary by calling the R-squared function. From the value in this example, you can say that the model explains approximately 76% of the variance. In this video, you learned two metrics you can use to assess your model: the mean squared error, or MSE, which is the mean of the square of the residuals, and R squared, a measure to determine how close the data is to the fitted regression line. Welcome to Prediction and Decision Making. In this video, you'll learn the steps you can take to determine if your model is correct. When determining a final best fit for your model, your first step is to make sure your model results make sense. You should always use visualization, numerical measures for evaluation, and comparing between different models to help you decide. Let's look at our example of prediction. If you recall, we fit the regression model using the LM function. Now we want to find out what the arrival delay would be for a flight that has a departure delay of 12, 19, or 24 minutes. So we'll enter the vector of values into the predict function. If a flight departs 12 minutes late, this gives us, on average, an arrival delay of 26 minutes. This seems to make sense since the value is not negative, extremely high, or extremely low. This is the equation for the simple linear model, if you recall, that predicts arrival delay minutes from departure delay minutes. For an increase of 1 minute in departure delay, the value of the arrival delay increases by approximately 0.75 minutes. This value also seems reasonable. Now that you have determined that the predicted values make sense, use visualization to confirm this. Using a regression plot to visualize your data is the first method you should try. For this example, the effect of the independent variable is evident in this case. The data trends up as the dependent variable increases. The plot shows some linear behavior. Let's now examine the residual plot of our model. The red line is the fitted line. The green points are the predicted values using the original dataset, and the black points are the actual values. Plotting these values takes a couple of intermediate steps, and we'll show you how you can do it. This is how you plot the actual and predicted values. First, add the predicted values in the original dataset as a new column called Predicted. Then, start plotting by using the ggplot function step by step. This plot shows an example of a mean square error of 3,495. This example has a mean square error of 3,652. The final plot has a mean square error of 12,870. As the square error increases, the targets get further from the predicted points. Recall that R squared is another popular method to evaluate models. In this plot, we see the target points in red and the predicted line in blue. With an R squared of 0.9986, the model appears to be a good fit. This model has an R squared of 0.9226, indicating that there is still a strong linear relationship. An R squared of 0.806 indicates that the data is a lot messier, but the linear relation is evident. In this graph, the linear function is a bit harder to see, but on closer inspection, we see the data is increasing with the independent variable. An acceptable value for R squared depends on what field you're studying. Here are some considerations for comparing multiple linear regression, MLR, and simple linear regression, or SLR. Is a lower MSE always implying a better fit? Well, not necessarily. MSE for an MLR model will be smaller than the MSE for an SLR model, since the errors of the data will decrease when more variables are included in the model. Polynomial regression will also have a smaller MSE than regular regression. A similar inverse relationship holds for R squared. In this video, you learned a 4-step process for deciding if your model is a good fit. Determine if your model makes sense. Confirm your models using visualization. Employ numerical measures for evaluation. And compare models to help you decide. Welcome to Model Evaluation. In this video, you will learn techniques for evaluating the performance of your models. You'll learn how to split your dataset into training and testing sets, build and train the model with a training set, and compute metrics on the training set to assess the performance of the model. You'll also learn a technique for handling cases with small datasets. So far, you have used the entire dataset to train your model. If you try to evaluate your model based on data you have trained it on, it will most likely lead to a result that is too optimistic. The whole point of a model is to be able to work with unseen data. The solution is to split your data into training and testing sets. Separating data into training and testing sets is an important part of model evaluation. A training set is a subset of data used to train the model. A test set is a subset of data used to test the trained model. You use the test data to determine how well your model will perform in the real world. When you split a dataset, the larger portion of data is usually used for training and a smaller part is used for testing. For example, you can use 80% of the data for training. You can then use 20% for testing. You first use a training set to build a model. You then use a testing set to evaluate model performance. When you have completed the testing of your model, you should then use all the data to retrain the model to get the best performance. In this module, we are using the Tidy Models package. Tidy Models is a collection of packages for modeling and machine learning using tidyverse principles. To create training and testing sets, you'll use functions from the Tidy Models library. The first step is to load the Tidy Models library. Then, you provide a seed value using the set.seed function. This function sets the starting number used to generate a sequence of random numbers. This ensures that you get the same result if you start with the same seed each time. You can set the seed to any arbitrary value. This example uses 1, 2, 3, 4. Finally, you use the initial underscore split function to create a single binary split of the data into a training set and a testing set. You must specify the dataset you want to split and the proportion of the dataset you want to use for the training set. In this case, we want the training set to be 80% of the dataset. You'll find more readings about training and testing functions later in this module. Now that you have training and testing sets, you need to train it using the model of your choice. This example uses linear regression and the modeling functions in the Tidy Models framework. The first step is to pick the model. This example specifies a linear regression model by calling the linear_reg function and setting the engine to LM. We are going to call this specification LM_spec. You can now fit the model using the training data. The output shows the formula and the respective coefficients. Now it's time to evaluate the models to estimate how well the models perform on new data, the test data. This example uses the model created in the previous step to make the predictions. This output is stored in a data frame with only one column called pred. You can then add a new column to this data frame using the mutate function. This new column is named truth and contains values of R delay minutes from the test_data. In the end, you will have a data frame with the predictions and the true values. The testing root mean squared error, or RMSE, provides an estimate of how well your model performs on new data. So let's compare it to the training RMSE. From the code, you can see that the RMSE is higher for the testing data than it is for the training data. The same happens to the R-squared value. So why is the test set RMSE higher than the training set RMSE? The reason is that the built model corresponds too closely or exactly to the training data, so it has a lower RMSE in training. In this case, the model fits the data very well, but performed poorly when predicting new data. This is called overfit. You can also make a plot to visualize how well you predicted the arrival delay. This example shows the actual values, the truth of R delay minutes, versus the model predictions as a scatter plot. It also plots the line y equals x through the origin. This line is a visual representation of the perfect model where all predicted values are equal to the true values in the test set. The farther the points are from this line, the worse the model fit. There is a noticeable problem when you do the training and testing set split on small data sets. If you have a small data set, splitting it into a training and testing set might leave you with a small test set. This actually introduces bias into your testing because you're reducing the size of your in-sample training data. Another problem is that you may be keeping some useful examples out of the training set. There is also a risk that you may not effectively evaluate the model performance because you do not have enough data in the test set. One solution to this problem is to perform n-fold cross-validation. One of the most common out-of-sample evaluation techniques is cross-validation. Cross-validation is an effective use of data because each observation is used for both training and testing. In this method, the dataset is split into k equal groups. Each group is referred to as a fold. This example has 4 folds. Some of the folds can be used as a training set, which you use to train the model, and the remaining parts are used as a test set, which you use to test the model. For example, you can use 3 folds for training and then use 1 fold for testing. This is repeated until each partition is used for both training and testing. At the end, you use the average results as the estimator of out-of-sample error. The evaluation metric that you use depends on the model. So you might ask why it's worth the effort to perform cross-validation. It's because cross-validation is used to test the generalizability of the model. Generalizability is a measure of how useful the results of a study are for a broader group of people and situations. As you train a model on the training set, it tends to overfit most of the time. To avoid this situation, you can use regularization techniques. Cross-validation provides a check on how the model is performing on a test data. New, unseen data. And since you have limited training instances, you need to be careful while reducing the amount of training samples and reserving it for testing purposes. Moreover, cross-validation works well with small amounts of data. For example, assume that you only have 100 samples. If you do a train test with an 80 to 20% split, then you only have 20 samples in the test set, which is too small to generalize reliable results. With cross-validation, you can have as many as k-folds, so you can build k different models. In this case, you can make predictions on all of your data and then average out the model performance. In R, you can use the vfold_cv function to create folds for cross-validation. Usually you would fit multiple models and select the one with the smallest RMSE. This example demonstrates the process with only one model. In this video, you learned that separating data into training and testing sets is an important part of model evaluation. You also learned the 3 steps to evaluating the model: train the model, make predictions, and compute metrics. And finally, you learned that cross-validation techniques, like n-fold cross-validation, can help improve the evaluation of models when datasets are small. Welcome to overfitting and underfitting. In this video, you will learn about underfitting and overfitting models, using polynomial regression as an example and how those concepts relate to the bias-variance trade-off. You'll also learn how to select the best polynomial order and how to identify problems that arise with selecting the wrong order polynomial. Let us start with a visual that demonstrates the idea of overfitting, underfitting, and ideal balance for a regression model. This model is underfitting because it misses the clear curvature in the relationship between the predictor and a response. This model can neither fit the training data nor generalize to new data. An underfit model will have poor performance on the training data. Underfitting is often not discussed because it is easy to detect given a good performance metric. The remedy is to move on and try to alternate machine learning algorithms. This model is overfitting. This overly complicated model can predict its own data very well, but that is because the model you see is catching a lot of the specific random behavior in the dataset. This model too closely corresponds to the training data and thereby fails to generalize on test data. It isn't hard to imagine that a new dataset, generated by the same process but exhibiting different random behavior, would be poorly predicted by even this complicated model. The last model appears to be the preferred one to generalize and make predictions from. This is because it captures the systemic trend in the predictor-response relationship. You can see high bias resulting in an oversimplified model, that is, underfitting, high variance resulting in overcomplicated models, that is, overfitting, and lastly, striking the right balance between bias and variance. However, there is a dilemma. You want to avoid overfitting because it gives too much predictive power to specific quirks in your data. And you want to avoid underfitting because you will ignore important general features in your data. How do we balance the two? This is known as the bias-variance trade-off. High bias corresponds to underfitting. Your predictions are too vague to account for general patterns that do exist in the sample. And high variance corresponds to overfitting. Your predictions are so specific that they only reflect your specific sample. In summary, the bias-variance trade-off is about balancing and finding a sweet spot between errors due to bias and errors due to variance. Let's look at a plot of the mean square error for the training and testing set for different model complexities. The training error decreases with the complexity of the model. The error decreases until the best model complexity is determined, and then the error begins to increase. The region on the left, where both training and validation errors are high, is the region of high bias. On the other hand, the region on the right, where test error is high, but training error is low, is the region of high variance. A model that is underfit will have high training and high testing error, while an overfit model will have extremely low training error, but a high testing error. In the end, you want to be in the sweet spot in the middle. To demonstrate these concepts, let's use the cars dataset in R to predict the distance, or dist, it takes for cars to stop given their speed. This example uses a simple polynomial model with degree 0 that predicts the distance using one value, the average distance over the whole dataset. In R, you can use ggplot to visualize this simple model by using geom_hline and setting the horizontal line's y-intercept to be the mean of the distances. On the right is the plot created from the code. The x-axis is the speed, the y-axis is the distance, and the simple model is the red line. From this graph, you can see that the model is underfitting since, for all the speeds less than 10, the predicted stopping speed would be much higher than in reality, and for speeds greater than 20, the predicted stopping distance would be much lower. There are several ways to prevent underfitting in the context of linear regression. First, you can increase the model complexity. For example, instead of using a linear function with a polynomial with degree 1, you can use a polynomial with a higher degree. Or you can switch from a linear to a nonlinear model. Another option is to add more features. Your model may be underfitting because the training data is too simple. It may lack the features that will make the model detect the relevant patterns to make accurate predictions. You can also try different models, such as regression trees or random forest. Coming back to the cars dataset in R, you can now try using a more complicated model, a polynomial with 8 degrees. Using ggplot, you can use the geom_smooth function to create a model. The method LM is for linear models, and the formula uses poly to introduce greater degrees of polynomials, in this case up to 8. Looking at the graph created on the right, the model in red looks like it is overfitting. The model is fitting to the points in the top right. If this model received new speeds, it may not be able to predict accurate distances. There are a few ways to prevent overfitting. One way is to reduce the model complexity. For example, if the model is a high-degree polynomial, you can decrease the degree. Another option is collecting more data. However, this method is considered expensive and not always possible. A third option is to perform cross-validation. Cross-validation is a powerful preventative measure against overfitting. And finally, the regularization technique is another way to prevent overfitting. Regularization refers to a broad range of techniques for artificially forcing your model to be simpler. Going back to the example with the cars dataset, you can reduce the complexity of the model. In the previous overfitting example, a polynomial model of 8 degrees was used. Instead, you can now use a polynomial of degree 1 or a simple linear regression model. In R, you can set the formula to y over x. And now, from the plot on the right, you can see that the model is generalizing more to the data. In this example, we demonstrated how you can prevent overfitting and underfitting models by changing the model complexity. In this video, you learned that the bias-variance trade-off is finding the right balance between overfitting, which gives too much predictive power to specific quirks in your data, and underfitting, which ignores important general features in your data. You can prevent overfitting and underfitting models by changing the model complexity and employing other strategies. Welcome to regularization. In this video, you will learn what regularization is and when you should use it. Additionally, you will learn about 2 widely used regularization techniques, ridge and least absolute shrinkage, and selection operator or lasso regression. Regularization is a way to handle the problem of overfitting. It is a technique you can use to reduce the complexity of the model by adding a penalty on the different parameters of the model. After it is applied, the model will be less likely to fit the noise of the training data and will improve the generalization abilities of the model. So, regularization is a way of avoiding overfitting by restricting the magnitude of model coefficients. In machine learning and statistics, a common task is to fit a model to a set of training data. You can later use this model to make predictions or classify new data points. When the model fits the training data, but does not have a good predicting performance and generalization power, you have an overfitting problem. Regularization is a technique used to avoid this overfitting problem. The idea behind regularization is that models that overfit the data are complex models that have, for example, too many parameters. There are a few methods of regularizing linear models, including ridge or L2 regularization, lasso or L1 regularization, and elastic net, which is a regularized regression method that linearly combines the L1 and L2 penalties of the lasso and ridge methods. You'll learn more about elastic net in the lab. Assume the dots in this graph are your data, and you have divided them into two parts. The two red dots are the training data, and the remaining green dots are the test data. You fit a red line between the two red dots using least squares. Since the red line overlaps the two red points, the minimum sum of squared residuals equals 0. The sum of squared residuals for the two red points is small, but the sum of squared residuals for the green points, which are the test data, is large. The red line is overfit on the training data and has high variance on the test data. The main idea behind regularization is to find a new line that doesn't fit the training data too well by introducing a small amount of noise or bias into the new line. In return for the additional amount of noise or bias, you get a significant drop in variance. In other words, by starting with a slightly worse fit, with regularization, the new regression can provide better long-term predictions. When using least squares to determine the equation, arrival delay minutes equals intercept plus slope times departure delay minutes, the function minimizes the sum of the squared residuals. When using the ridge regression function to determine the equation, the function minimizes the sum of the squared residuals plus lambda times weight squared. When using the lasso regression function to determine the equation, the function minimizes the sum of the squared residuals plus lambda times the absolute value of weight. In summary, to find the best model, the common method in machine learning is to define a loss or cost function that describes how well the model fits the data. The goal is to find the model that minimizes this loss function. The idea is to penalize this loss function by adding a complexity term that would give a bigger loss for more complex models. In the case of polynomials, you can use the square sum of the polynomial parameters. In the visualization on the previous slides, you can increase or decrease the value of lambda to penalize complex models more or less. This way, for large lambda values, models with high complexity are ruled out. And for small lambda values, models with high training errors are ruled out. The optimal solution lies somewhere in the middle. Lasso is similar conceptually to ridge regression. It also adds a penalty for non-zero coefficients, but unlike ridge regression, which penalizes sum of squared coefficients, the L2 penalty, Lasso penalizes the sum of their absolute values, the L1 penalty. As a result, for high values of lambda, many coefficients are exactly zeroed under Lasso, which is never the case for ridge regression. Let us look at an example of modeling ridge regression with tidy models. First, create a recipe that includes the model formula. You could pre-process the data more in this step, but the data here is already pre-processed. Next, use the linear_reg function from the tidy models library to specify the model. Penalty is the value of lambda. Mixture is the proportion of L1 penalty. For ridge regression, specify mixture equals 0. This means there is no L1 penalty and only the L2 penalty is used. For lasso regression, specify mixture equals 1. Next, create a workflow object so you can more conveniently combine pre-processing, modeling, and post-processing requests. And finally, add the ridge model and fit the model. To view the result of the fitted ridge regression model, use the pull_workflow_fit function. There are two results columns. The estimate column contains the estimates of the coefficients learned by the model. Penalty contains the value of lambda, which in this example is 0.1. This model focused on ridge regression. To get more information about lasso regression, check out the lab. In this video, you learned about regularization, a technique you can use to avoid overfitting by restricting the magnitude of model coefficients. It works by adding a penalty on the different parameters of the model to reduce its complexity. By manipulating the lambda and weight parameters, you can find the model with the right balance. Welcome to Grid Search. In this video, you'll learn about hyperparameters and how you can use a grid search, a technique to try multiple values of a model's parameters in few lines of code, to tune the hyperparameters in your model. You choose the hyperparameters in your model. They do not result from training. For example, for ridge and lasso regression, lambda is a hyperparameter because you can choose the value of lambda. The model does not learn the value of lambda. In comparison, the model does learn the coefficients of the regression model. Choosing the value of lambda can be a tedious process because you have an infinite number of choices to try. Having a method like grid search can help make this process easier. The goal of grid search is to find the values of the hyperparameters that results in the best model. This is known as tuning hyperparameters. Grid search takes a list of values for each hyperparameter it is tuning and iterates through each combination. It then uses every combination of parameters to produce a model. For each model, a metric like RMSE is calculated. You then determine the best value of the hyperparameters by choosing the model with the best RMSE. In R, you can use functions in tidy models to run grid search. For every parameter that you use in grid search, a new model is trained. Grid search tries to find the value of the parameter that has the smallest error. For example, if you are training a lasso or ridge regression model, the error metric could be RMSE and the parameter could be lambda. Using tidy models in R, you can use grid search to tune your models. This example uses lasso and tunes the hyperparameter lambda. First, define the lasso model. Recall that mixture equals 1 specifies lasso, while mixture equals 0 specifies ridge. Penalty is the lambda, and since you are tuning that, you set it to tune. Second, set up cross-validation to re-sample the data multiple times when running each value for lambda. Third, define the grid to tune the penalty or lambda. Here we set levels to 50, which means 50 values of lambda are used. Range is the range of values to use. By default, the values are the inverse log transformed, so -3 is really 10 to the -3, and 0.3 is 10 to the 0.3. And finally, use tune_grid to tune the lambda for lasso regression. Recall that lasso_WF is the workflow that contains the model's formula. Using the show_best function, you can view the values for lambda that give the best results in the defined grid. Since metric is set to RMSE, the best result is defined by the models that have the lowest RMSE. In the table, the penalty is lambda. Additionally, cross-validation is run for each value of lambda, so the mean in the table is the mean of the RMSE from cross-validation. In this example, the lowest average RMSE is 12.8, which is obtained by setting lambda equal to 1.25. Additionally, you could view a graph of the results. The dip in the graph corresponds to the best value for lambda. If you are interested in how to draw the graph, please see the lab. In this video, you learned that a grid search makes the process of tuning the hyperparameters in your models easier. Grid search does this by training a new model for every parameter that you specify and finding the value of the parameter that has the smallest error. You also learned how to use the functions in the Tidy Models library to define a grid search and plot the result. Welcome to Introduction to Data Visualization. In this video, you will learn why data visualization is important, the different chart types that are available and when you should use them, and the R packages you can use for visualization. Data visualization represents data in the form of graphs, charts, plots, and any other formats. With the amount of data you have around you, data visualization helps you interpret and understand the story that the data is trying to convey through visuals. It is storytelling with a purpose. Visualization makes it easy to identify patterns, trends, and anomalies in the data, making it easier for human brains to process and grasp the information. Let's see this in action. This Excel spreadsheet has data about domestic U.S. airline performance. If asked to determine the month and reporting airline with the highest number of flights, how effective and easy do you think it is to extract this information from the spreadsheet? Here is the same data represented as charts. Which one is easier to understand? Of course, the visuals. And that is the focus of this course, to equip you with the tools to help make data more understandable. Charts can be classified into 6 categories based on the chart's goals, aesthetics, or visual features. Comparison charts are designed for comparison and aim to visualize the differences between elements. You will use these charts for time-based data and categorized data. Trend charts represent data along the time dimension. You will use them mainly to track changes over periods of time or to show the distribution of continuous variables. Part-to-whole charts show the inner subdivision of a value among different categories or groups. You will primarily use these charts to represent percentages, but you can also use them for absolute values. Correlation charts highlight the possible correlation between 2 or more indicators and how they might affect each other. Relationships and connections charts represent hierarchies. The intent is to explain the role of an element within an ecosystem or to observe the inner nature of a subject in different phases and states of a process. And maps are the easiest and most immediate way to communicate geolocated information. 2 popular R packages for data visualization include the ggplot2 package, which includes some of the most common chart types, and the leaflet package, which includes the map chart type. Using these packages, you can transform your data into visuals and convey details as well as insights about the data to your stakeholders. In this video, you learned that data visualization helps you see trends, patterns, or anomalies that are not obvious when looking at raw data. There are 6 main categories of charts. And the R packages for visualization include ggplot2 and leaflet. Welcome to using ggplot2. In this video, you will learn some of the benefits of using the ggplot2 package for R to visualize your data, the 3 components of a visualization, and how to create a simple visualization using ggplot2 functions. We all know that languages have grammar, and they are essential to effectively communicating our thoughts. Did you know that graphics also have grammar? The R package, ggplot2, is based on the grammar of graphics, a coherent system for describing and building graphs. ggplot2 enables you to compose simple to complex graphs by combining independent components. By learning this one system, you can apply it in many places and do more faster, making ggplot2 both easy and powerful. Now, let us look into the components of the graphics. The most fundamental component is the data set that you will use to make visualizations. The second component is the aesthetics. Aesthetics map data to visual variables such as color or position on the X or Y axis. The third component is the geometry. Geometric objects represent the actual items that you see on the plot, such as points, lines, shapes, and more. These three elements are the bare minimum that you must specify to create a graph with ggplot2. The ggplot2 package is an excellent choice for visualization because having consistent grammar across the graphs makes ggplot2 easy to extend, enabling you to build graphs by adding layers of components. Also, the ggplot2 package has great documentation. There are two functions in the ggplot2 package that you can use to create visualizations. This is the basic syntax for the first function, ggplot. ggplot initializes a ggplot object. You use it to declare the input data frame for a graphic, and then add layers to specify the set of plot aesthetics that are common throughout all subsequent layers unless specifically overridden. ggplot has no default settings, which means that you must specify all aspects of the chart and have more control. You can visualize the ggplot function as drawing on a plain canvas. You start off with data, and then you add points to a coordinate system to get a final plot. Although the function ggplot creates the initial object, there are three common ways to invoke the plot. Use the first method if all layers use the same data and the same set of aesthetics. With the second method, you only provide the data frame without any aesthetics. Use this method if you use one data frame predominantly, but the aesthetics vary from one layer to another. Use the third method when creating complex graphics where each layer uses a different data frame and aesthetics. In this course, you will work mostly with the first method. Now that you know how to add data and aesthetics to the graph object, let's see how to add layers to the graph. First, you create the initial graph object. Then you add layers using the plus sign followed by visual marks using geomes. Here are some examples. Geome area is for plotting area graphs. Geome line is for plotting line graphs. And geome bar is for plotting bar graphs. Another ggplot2 function is qplot. You can use this quick plot function to create simple plots. It can create a complete plot given the data, mappings, and geome. The function also supplies many useful defaults. While qplot is quick and easy to use, it is not as flexible as ggplot. You can find the link to the ggplot2 cheat sheet in the reading list for reference. And with this, creating attractive visualizations should be quick and easy. In this video, you learned that the three components of a plot are data, aesthetics, and geometry. You also learned about the two ggplot2 functions for creating visualizations. The ggplot function, which provides the most flexibility for creating plots, and the qplot function, which is a quick and easy way to plot data, but its functionality is limited.
Hello and welcome. In this video, we will show you how to create bar charts using the ggplot2 library and the R programming language. Bar charts are representations of group data, and they're extremely versatile in their application. For example, they're good at plotting the counts of groups, like the number of employees in each division of a company. They're also good at plotting the averages of groups, like the average height for both men and women. We're going to be using a data frame of automobiles and forming a bar chart that displays the frequency of each engine type based on the number of cylinders. In order to create the plot, we're going to use the ggplot2 library. ggplot2 allows you to create aesthetically pleasing, customizable data visualizations, but since it's external, you first need to install it if you haven't already done so. You can do this by passing the library name into the install.packages function. After it's installed, make sure to load it with the library function in order to use it in your code. The dataset that we are going to work with is called MT-CARS, which stands for Motor Trend Car Road Tests. This is a built-in dataset that contains data from the 1974 Motor Trend US magazine. In total, there are 32 automobiles in the dataset from 1973 to 1974. For each automobile, there are 11 variables in the dataset, including fuel consumption. When we build our bar chart, we're going to use the SIL column, which stands for cylinder. Since the dataset is built into the R programming language, you don't need to import anything. Simply reference the name MT cars in the R code to access the data. Before we continue, let's briefly cover the two different ways that data can be categorized. Qualitative data, as the name suggests, describes some data quality, data attribute, or data category. So with this dataset, an example is an automobile name. Another example might be an address or a color, things like that. Quantitative data is data that is measured and described numerically. That could be things like price, mileage, and weight. Some variables, like the cylinder variable, appear to be quantitative, but they can also be interpreted as a qualitative variable. When creating your graphs, it's important to understand the difference between these two data categories, so make sure to keep them in mind. Let's now take a look at some code samples. We're going to use the qplot function, which is relatively easy to work with. As you can see here, we are plotting the cylinder data from the MT cars dataset. The cylinder value can be thought of as qualitative data, and in our case, the possible values are 4, 6, and 8. To form a bar chart, we'll include the argument shown here, which sets the geometry type to bar. So this plot displays the number of occurrences of each cylinder value. Right now our graph looks a bit dull, so let's see how we can make it more visually appealing. One simple approach is to alter the colors. The fill parameter changes the color of the bars, while the color parameter will change the color of the bar's outline. If you don't include the color parameter, by default the outline color will match the fill color. There are a lot of colors to choose from, including blue, pink, green, and yellow. Use the help function if you'd like to know the full list. We can also change the name of our axes to make the plot more understandable. This parameter specifies the x-axis label, and this parameter specifies the y-axis label. To finish our plot, we're going to use the main parameter in order to add a title. By now, you should understand how to create a bar chart using the ggplot2 library and the R programming language. You should also know how to adjust the bar chart's color, title, and axis labels. Thank you for watching this video. Hello, and welcome. In this video, we will show you how to create histograms using the ggplot2 library and the R programming language. ggplot2 is a specialized library for creating aesthetically pleasing data visualizations. Since it's an external library, you need to install it if you haven't already done so. Afterwards, simply run the library method in order to use ggplot2 in your code. Histograms are used to visualize the frequency of numerical values. It looks like a bar plot, but it displays quantitative data rather than qualitative. To demonstrate this, we're going to use the built-in MT cars dataset, which holds 11 variables that describe automobiles from 1973 to 1974. Consider the horsepower column from our dataset. A bar plot would count the frequency of each individual number, which isn't meaningful since the individual numbers don't represent categories. A histogram would divide up the data into bins, and then count the number of times a data point falls into each bin. The bars represent these counts, and as you can see, consecutive bars are not separated by spaces. Depending on the plot's vertical scale, a histogram can also display the variable's probability distribution, in which case the total area would add up to 1. Just like with the bar plot, we're going to use the qplot function. We'll use the horsepower column from the MT cars dataset, and we'll assign histogram as the geometry type. When we run this, we get a warning about the number of bins. We can improve the smoothness of the histogram by addressing this problem. To do so, we can set the bin width parameter to a number of our choosing. So in our case, the number range is broken up to bins of size 25. Data points that fall in the same bin are counted together, and you can see that this smoothed out the histogram significantly. Larger bin widths will result in more smoothing, but you may start to lose some of the important details of the distribution. Another problem is that some of the bins are difficult to differentiate. Consider the data between 210 and 260 horsepower. While this range contains two separate bins, the lack of spacing makes it look like one large bin. We can fix this by using the color argument, which will change the color of the borders. Notice how easy it is to differentiate the consecutive bins in the plot. If you'd like, you can specify the range of the x-axis you'd like to visualize. Although keep in mind that R will automatically fit the best values given the nature of the data. In our case, we use the xlim parameter to set the range from 50 to 350. This effectively cuts down the length of the x-axis. We can also change our axis names. We'll set the x-axis to horsepower and the y-axis to number of cars. If you'd like to remove the fill color completely, you can specify the alpha parameter like we've done here. And if you'd like to add a title, simply use the main parameter with the title of your choosing. By now, you should understand how to create a histogram in the R programming language. You should also know how to adjust the smoothness, color, and axis labels. Thank you for watching this video.
Welcome to Pie Charts. In this video, you will learn how to create pie charts using the ggplot2 library and the R programming language. You will also learn about the relationship between stacked bar charts and pie charts, and how to customize chart themes. Pie charts display the distribution of a single categorical variable. You use the function coord polar to produce a pie chart, which is just a stacked bar plot in polar coordinates. Before you learn how this pie chart was created, let's start with creating a grouped bar chart and a stacked bar chart, and then create a pie chart from a stacked bar chart by applying the polar coordinates. This bar chart uses the MT cars dataset and plots the categorical data in the column sil, which represents the number of cylinders in the car. To create a grouped bar chart, you first convert the column sil to a factor. Using as factor on a column makes it easier to work with categorical data, because it converts the column to levels. In this case, cars typically have 4, 6, or 8 cylinders, so the values have 3 levels or categories. Notice that this example uses the tidyverse way to create a new variable using the mutate function. You can also do this using the base R language by using the $sign. The next step is to plot the chart using the ggplot function. Recall that geom_bar creates a bar chart. To create a grouped bar chart, set the position argument to Dodge. This creates a different bar for each factor level or subgroup of sil factor. You must also set the x and fill arguments to the categorical variable, which is sil factor in this example. A stacked bar chart is very similar to the grouped bar chart. The difference is that the subgroups are displayed on top of rather than beside of each other. To create a stacked bar chart, there are 2 things you must change. There is no variable on the x-axis, so you can create an empty one by setting the x argument to an empty string. Also, you need to change the position argument from Dodge to stack. Stacked bar charts and pie charts both show the distribution of the different categories in categorical variables. The difference is that pie charts are visualized as a circle instead of bars. So, to create a pie chart using ggplot, you transform the stacked bar chart into polar coordinates, which essentially means converting it to a circle. You can use coord polar to do this. This example sets the theta argument of the coord polar method to y. The theta is the angle which determines how big each of the sections of the pie chart should be, and y is the count of each category of the cylinder's variable. You can also customize how the chart looks by using the different themes built into ggplot. This example uses theme minimal. You can search the help documentation with $theme minimal for more built-in themes. Additionally, you can change the color palette using the scale fill brewer function. This example uses the color scheme Dark 2 from Color Brewer, an online tool designed to help you select good color schemes for maps and other graphics. This function also changes the fill aesthetics, which means the color of the pie sections in this case. In this video, you learned that stacked bar charts and pie charts both show the distribution of the different categories in categorical variables, but pie charts are visualized as a circle instead of bars. You also learned that grouped bar charts, stacked bar charts, and pie charts all start with converting a variable into a factor and then plotting the data using ggplot. And to transform a stacked bar chart to polar coordinates, a circle, use the coord polar function.
Hello and welcome. In this video, we will show you how to create a scatter plot using the ggplot2 library and the R programming language. ggplot2 is a specialized library for creating aesthetically pleasing data visualizations. Since it's an external library, you need to install it if you haven't already done so. Afterwards, simply run the library method in order to use ggplot2 in your code. The code snippet here shows the syntax for a basic scatter plot using the qplot function. We're also using the built-in mtcars dataset, which tracks 11 variables for automobiles from 1973 to 1974. mpg stands for miles per gallon, and wt stands for weight. Each point in the output represents the miles per gallon and weight of one individual automobile. So you can start to see how these two variables relate to each other across the points of the dataset. The qplot method will create simple scatter plots, but if you need more customization, you'll have to turn to the ggplot method. Notice how the syntax is a bit different from before. One important difference is the addition of the geom_point property, which will change the shape of the dots within the graph, like so. Different values for this parameter will result in different shapes. If you set the shape parameter to 19, like in the code here, you'll revert back to the solid circles from before. We can introduce a third variable to our scatter plot, in addition to miles per gallon and weight. The automobiles can be categorized by the number of cylinders, so we're going to use the shape of each point to represent this. We'll first need to create a factor from the cylinder variable, and then we'll use the ggplot function to create the scatter plot. Let's take a look at the output. Notice that this code uses cyl factor in conjunction with the shape parameter to achieve the desired effect. You can see how 4-cylinder cars are represented as circles, 6-cylinder cars are represented as triangles, and 8-cylinder cars are represented as squares. If you'd like to adjust the color of the points, you can do so by adding the color parameter to the geom_point method. As you can see in the output, all of the points in the scatter plot are blue. Color can also be used to represent a third variable, just like shape did before. To do so, you need to specify the color property of the ggplot function. Once again, we're going to use the cylinder variable. You can see in the output that each point is now colored depending on the cylinder count. The legend on the right indicates what each color represents. The previous example interpreted the cylinder count numerically, but it makes more sense to think of the cylinder variable as categorical. So once again, we'll specify the color parameter, but this time we'll use the cyl factor variable. In the output, You can see that the legend indicates a unique color for each cylinder category. Take a look here for a side-by-side comparison. The left plot uses the cylinder data's numeric range, and the right plot uses the cylinder factor, treating the values as separate categories. Using the factor approach creates a much more aesthetically pleasing visual. You'll notice that the legend's label simply reads Sil factor, which is the name of our variable. We can adjust this by using the labs function and specifying a custom name. Notice in the output that we've changed the label to cylinders. To make our plot a bit more descriptive, we can rename the axes using the xlab and ylab functions. In addition, we can specify the plot's title with ggtitle. You can see how these changes would look when applied to the scatterplot. By now, you should understand how to create a scatterplot using the ggplot2 library and the R programming language. You should also know how to adjust the shapes and colors of the individual points. Thank you for watching this video.
Welcome to Line Plots. In this video, you will learn how to plot basic line plots, change the axis labels and colors of plots, and plot multiple line plots. Line plots help you visualize time series data. Throughout this lesson, you will see examples of line plots that use the EU stock markets time series dataset, which comes with the ggplot2 package. To see more details about the data, enter $EU stock markets. This dataset contains 1,860 rows and 4 variables, so to display only the first 6 rows in the dataset, use the head function. This dataset is an MTS or multivariate time series object. Because ggplot cannot plot time series objects, you first convert it to a data frame and then extract the date information using the time function. Notice that the dataset now has a date column. Later in this video, you will learn a simpler way to convert the dataset so it can be used more easily with tidyverse. The main function to create line plots is geom_line. To create a line plot, you first use the ggplot function to specify variables for the x and y axis. In this example with the EU stock markets dataset, the x-axis is the date, and the y-axis is the SMI, which is the daily closing price for the stock market index SMI for Switzerland. And then to create the line, you add the geom_line function. By default, the x and y axis labels will be the name of the variables you specified when creating the plot. However, the variable names are not often descriptive enough. For example, if someone were to glance at this graph, they may not understand what the SMI means. So, to change the axis labels, you can add the labs function and specify a new name for the y-axis labels. Now, with more descriptive labels, it is clear what this graph is telling us. It is often helpful to see multiple lines on the same plot so you can compare multiple variables over time. To add another line to the plot, you can add another geom_line function. For example, in this plot, there is a line for every stock index. However, there are several drawbacks to using this method. The y-axis label and scales may not make sense for all the variables. Also, you must manually call geom_line and set the color for every new line. You may also have to do a lot of customization to the plot for it to make sense. Notice also that the y-axis in the plot gets labeled with the name of the y variable in the first geom_line function. Let us look at another way to create a multiple line plot using the same data. If you look at the original EU stock markets dataset, you will see that the market stock indexes are arranged by columns instead of rows. This is a common problem that can be solved by tidying the data so it is aligned in rows instead. This makes it simpler to create multiple line plots. To easily tidy up the time series object, you can use the function tidy, which is included in the Broom library. Broom is included in tidyverse, so you do not need to install anything. But but you may have to load Broom. By default, the names of the columns become index, series, and value. You can use rename to change the column names. Now, you can see that the dataset was transformed to 3 columns. There is the date column, which was automatically extracted from the time series object, like in the example you saw earlier in the video. There is the stock index column that reflects the name of each column in the original dataset. Finally, there is the price column that includes the values in the original dataset. For example, in the original data frame, the first row corresponds to the first 4 rows in the transformed dataset. With this tidied dataset, it is simple to create a multiple line plot because you do not need to add geom_line for every new line you want to plot. To create the line plot, set the X as the date, Y as price, and then set the color equal to the variable you tidied up. In this example, the variable is stock_index. All the line colors as well as the legend are automatically set, so you do not need to manually set them. In this video, you learned that line plots visualize time series data. You also learned to create a line plot by specifying an X and Y axis using the geom_line function, and then modify the X and Y axis labels and the line colors. And finally, you learned 2 ways to create multiple line plots.
Hello, and welcome. In this video, we're going to show you how to create a box plot in the R programming language. A box plot summarizes the distribution of sorted numerical data. The first quartile is the point 25% of the way through the sorted data. In other words, a quarter of the data points are less than this value. Similarly, 75% of the points are less than the third quartile value. The interquartile range is simply the difference between the first and third quartile. The median is effectively the second quartile, so 50% of the data falls below the median. The lower and upper whiskers indicate values outside the interquartile range. And then we have the mean, or the average, of all the data points. Let's look at an example to see how this works. The dataset has 8 values, so to find the median, we'll add the 4th and 5th elements and divide by 2. Notice how half the elements are less than the median and half are greater. We can perform a similar kind of calculation to get the first and third quartiles. Notice that 2 out of the 8 elements are less than the first quartile, and 6 out of the 8 elements are less than the third quartile, and the lower and upper whiskers simply extend to the minimum and maximum values. For our box plot, we're going to create a set of pseudo-random data points from the normal distribution. In order to reproduce the results, we're going to fix the seed value for the random number generator. So the data will appear random, but it will be the same every time the code is run. We'll then create 2 sets of data, A and B, each with 200 samples. Set A is sampled from the normal distribution with mean 1, standard deviation 2. Set B has mean 0, standard deviation 1. We'll place these sets into a data frame, making sure to separate them by label. You can take a look at the data frame here. The head function shows the first 6 elements, and the tail function shows the last 6. Notice how the numbers are grouped together by their original set. We're going to be using the ggplot2 and plotly packages. ggplot2 allows you to create highly customizable, aesthetically pleasing data visualizations. Plotly provides online graphing, analytics, and statistics tools for individuals in collaboration, as well as a scientific graphing library. Since these are external, you must install them if you haven't done so, and then run the library command to use them in your code. In order to create a box plot with the datasets, we're going to use the code here. We'll run the ggplot method with our data frame as input, setting the x-axis to display the labels and the y-axis to display the range of numbers. To get a box plot as output, we need to add the geom_boxplot method at the end. And finally, the ggplotly method will display the resulting graph. In the whiskers, values beyond 1.5 times the interquartile range are considered outliers. These are represented as dots. Let's practice with the real-world MT Cars dataset, which holds data about automobiles from 1973 to 1974. Since the dataset is built into R, you can start referencing it in your code without any import statements. We're going to work with the first two variables in the top row, miles per gallon and number of cylinders. Let's first create a box plot using qplot. Qplot is a basic function in the ggplot2 package that's simple to use, but still capable of creating expressive plots. The x-axis will hold the number of cylinders. Since the number of cylinders is more of a category than a numerical attribute, we'll apply the factor function. The cars are either 4-cylinder, 6-cylinder, or 8-cylinder. For the y-axis, we'll use the miles per gallon data. The dataset we're using is MT Cars, and for the geometry, we need to specify that we're creating a box plot. And you can see we get a box plot for each cylinder category. You can even start to see the relationship between cylinder count and miles per gallon. We can also use the ggplot function, which is more customizable. The second parameter, AES, denotes a list of aesthetic mappings between variables in the data and the visual properties. Once again, we're going to see how cylinder count relates to the miles per gallon value. After adding the geom_boxplot method, we can take a look at the box plot in the output. By now, you should understand the structure of a box plot, as well as how to create one in the R programming language. Thank you for watching this video.
Welcome to Customize Plots. In this video, you will learn how to customize titles and labels, text labels, and add line and text annotations to plots. It is important to add labels and titles to your plots. Often, default labels are lacking in descriptive information, so it is better to customize the labels yourself so they convey the intended meaning to those who will consume your data visualizations. You can use the labs function to change the x-axis label, y-axis label, the legend title, the entire plot title, the plot subtitle, and the plot captions. You do not have to add all of these labels, but it is a good idea to make sure that at least the x and y-axis and the title are informative. Additionally, if you only want to update the x-axis, y-axis, or title and subtitle labels, you can use these functions. This is a scatter plot using the default labels. Notice that there is no title, and the x-axis, y-axis labels, and legend label are not very informative to people who are not familiar with the dataset. What is WT and MPG? What is this plot about? You can use labs to edit these labels and make this plot better. You can change the x-axis label and the y-axis label. The color parameter changes the legend title. You can also add a more informative plot title and add a subtitle to provide more information about the dataset. The resulting plot is much more informative. Another helpful function to use in plots is geom_text. You use this function to add text labels to data points. This example again uses the mileage and weight of cars, except that we now want to display the name of the car that corresponds with each data point on the plot. In MT Cars, the row name contains the name of the cars. You can use geom_text with the row names function to label each point with the name of the car. So in the AES of geom_text, set the label parameter equal to row names MT Cars. In the resulting plot, you can see that the car names appear as expected. However, a lot of the text is overlapping, some words are cut off, and it looks messy. You can remove the overlapping text by setting the check_overlap parameter of geom_text to true. Also, setting the hjust parameter to inward makes sure all the text is positioned within the plot. In the resulting plot, notice that although some points are removed, the overall takeaway from this plot is more clearly revealed. So, you can now see that automatic cars have low mileage and greater weight, while manual cars have better mileage and lighter weight. You can create custom annotations to emphasize important elements of your plot. For example, there may be an outlier on your scatter plot that you want to label or outline, or a spike in your line plot that you want to highlight. You can use custom annotations to emphasize these areas. There are several functions you can use to create custom annotations. geom_vline creates a vertical line. geom_hline creates a horizontal line. geom_abline adds a line with specified slope and intercept. And geom_rect draws rectangles. You can also use the annotate function, which provides even more customization. You pass in a geom, such as point or text, and then draw these customized elements on the plot. Using this is an alternative to functions like geom_text and geom_label can shorten the code length. For example, consider this histogram of the miles per gallon variable. To add a vertical line to show the median, use the geom_vline function. Next, annotate the line using annotate. To add text, set geom to text and set label to the desired text. Set X and Y to position where the text will go. And finally, set hjust or horizontal justification to 0, which makes the text completely left justified at the X position. As you can see, there are many ways to customize plots. But remember, you may not want to label everything to the point that your plot becomes overwhelming and the labels are hindering the visualization instead of enhancing it. Sometimes simple is better. In this video, you learned to use labs to add title and labels and geom_text to add text labels to data. You also learned to customize annotations with functions like geom_vline and annotate. Finally, you learned that adding labels and annotations can enhance plots, but sometimes simple is better. Welcome to Themes and Faceting. In this video, you will learn about faceting, a technique for displaying additional categorical variables on a plot. You will also learn how to add and customize themes in your plot, as well as use additional themes available in the GG Themes package. Facets divide a plot into subplots based on the values of discrete or categorical variables. Facets are a good way to explore the data further. Assume you have data about cars. You could plot data for all the cars, but what if you wanted to look at attributes for each type of car? You can use facets to do this. In ggplot, you create facets by adding the function facetWrap and passing it to a tilde character and the variable you are faceting. Let us look at an example. Displayed here is the distribution of miles per gallon of all the cars in the MT Cars dataset. Now, what if you want to break it up by the number of cylinders each car has? You can add facetWrap on the sil variable, which contains the number of cylinders. Now you can see the distributions of miles per gallon for each number of cylinders. From this faceted histogram, you can see that the cars with the least number of cylinders have a wider range of miles per gallon, and the cars with the most cylinders have the least miles per gallon. Using facetWrap makes creating these plots simple. If you used base R plotting, you would have to filter the data yourself and create a new plot for each number of cylinders. You can apply faceting to all the other plots you have learned about, like bar plots, box plots, scatter plots, and so on. You have seen how ggplot2 makes faceting simple by just adding one function. In line with this idea of making visualization simpler, you can change the themes of your plots simply by adding a different theme function. ggplot2 comes with 8 built-in themes. The default is theme gray. Even if you do not add a theme function, your plot will have this theme. But there are several other themes you can use when creating your graphs. Theme BW is a variation on theme gray that uses a white background and thin gray grid lines. Theme minimal has no background annotations. Theme classic has X and Y axis lines but no grid lines. Theme void is a completely empty theme. Theme line draw has only black lines of various widths on white backgrounds. Theme light is similar to theme line draw, but with light gray lines and axes. And theme dark is similar to theme light with similar line sizes, but with a dark background. Play around with the different themes and see which one you like better. In addition to these built-in themes, you can customize your own. There are many different aspects of the plots that you can customize, like the axis, the legend, and the entire plot. To see all the options, look at the documentation with $theme. For each element you customize, you may need to use theme element functions like element rect, element line, or element text. There is also the function element blank that can completely remove an element if you do not want it. Again, if you look at the documentation for theme, it will describe which function you need to use for each setting. This is the default setting for plots. Now, if you want to change the background, use plot.background and the theme element, element rect. The color refers to the color of the background borderline, and the fill is the color of the background. You can also change the plot title using element text. This example makes it bold and blue. If you wanted to change the color of the X and Y axis lines, you can use element line and set the color. This example also uses element blank to remove the axis tick marks. Customizing your own theme gives you a lot of freedom, but the process may be tedious. A helpful package that includes more themes and color scales is the GG Themes package. To use it, you must first install and load it because it is not included in the ggplot2 package. Next, we will go over some examples, but there are lots of theme options, so feel free to explore the documentation. This is a scatter plot that uses the default ggplot theme and color. Storing the base plot in a variable will make it easy to try different themes. This example stores a ggplot object in a variable named p. To view the plot, call the variable. Using the GG Themes package, you can change the plot to follow the economist theme and colors by simply adding the theme economist and scale color economist functions to the base plot p. Here is another example that uses a clean theme and a color palette that is colorblind safe. And these are just a couple of examples. You can try different themes and color scale combinations on your own using the GG Themes documentation. In this video, you learned that you could use faceting to visualize each level of a discrete or categorical variable in a plot. You also learned that ggplot has several built-in themes, but you can also customize them to create your own themes or use the themes in the GG Themes package for more options.
Hello and welcome. In this video, we're going to show you how to create maps in the R programming language. There are a number of packages available for working with maps in R, such as GG Maps, R Google Maps, or the built-in Maps library. We're going to focus on the Leaflet library, which allows you to create interactive maps. Make sure to install it if you haven't already done so, and then load it using the library function. Leaflet is a powerful library capable of producing complex visuals, like this street map of Times Square. But even though it's a powerful tool, it's generally very simple to use. Just to give you more of an idea of Leaflet's capabilities, here are two more examples of Leaflet maps. In this case, we have two maps of the Eiffel Tower with different stylizations. To begin, we'll use the Leaflet function, which returns an object that represents an empty world map. Next, we'll call the add tiles function to publish a tile layer on the map. This allows us to zoom in and see the countries and cities in detail. Notice that we're using the special operator highlighted here. This is the pipe operator from the McGritter package. It passes the item on its left into the first parameter of the function on its right, and then returns the result. So this code will send the output of Leaflet to the first parameter of add tiles, and this result is returned to the map variable. You can also display a specific location with a marker, like we've done with Times Square on this map. To do so, use the add markers function and specify the longitude and latitude of your location. To add a caption to a specific location, you can use the pop-up argument. So now it's clear that this marker denotes the location of Times Square. You can create maps with different styles, like the watercolor style you see here. In our case, we're using the add provider tiles function with the argument stammen.watercolor. There are a variety of different styles to choose from, so there are a lot of opportunities to customize your map. Let's now use a dataset in order to add markers to a map. In this example, we're going to use the built-in quakes dataset, which provides the locations of 1,000 earthquakes near Fiji since 1964. For each earthquake, the dataset holds the longitude, latitude, depth, magnitude, and number of stations. So once again, we'll add markers onto a map. But this time, we'll make sure to provide the longitude and latitude of all the points that we want to plot. You can see that we have created the markers, but now the map is starting to look a little too cluttered. We can improve the clarity by grouping the markers into clusters. The cluster options parameter will group the markers by region and display the number of markers in each region. Another option is to display circles for each point. These circles can be rescaled with the whole map when you zoom in or out. Notice that we're using the add circles function rather than the add circle markers function from earlier. If you want to highlight an area of interest, you can use the add rectangles function. The arguments are the coordinates of 2 points, which serve as the rectangle's delimiters. We mentioned at the beginning that Leaflet is a powerful library that provides a lot of functionality. We've only scratched the surface, but Leaflet allows you to add different colors, legends, lines, and shapes. So once you get used to the interface, you'll be able to use Leaflet to its full potential. By now, you should understand how to create basic maps using the Leaflet library and the R programming language. You should also know how to adjust the map's color, as well as how to add captions and markers. Thank you for watching this video.
Welcome to Introduction to Dashboards and Shiny. In this video, you will learn the importance of dashboards in your data storytelling, the components that make up a dashboard, and the role of Shiny, an R package, in creating dashboards. An interactive data application, or dashboard, can help improve business performance by providing key performance indicators, or KPIs, to stakeholders. There are many benefits to using dashboards to visualize data. With real-time visuals on a dashboard, understanding the moving parts of a business becomes easy. Based on the report type and data, you can create suitable graphs and charts in one central location, thereby providing an easy way for stakeholders to quickly access the data and understand what is going right or wrong and what needs to be improved. Also, seeing the big picture in one place can help businesses make informed decisions. thereby improving performance and reducing hours spent on analyzing the data. In general, the best dashboards answer critical business questions. A dashboard consists of 4 components. The first is Analyze. In this component, you manipulate and summarize data using a backend library. In the Visualize component, you create graphs using the Graphing library. Next is Interact. Here, you use front-end libraries to accept user inputs. And finally, the Serve component listens to user requests and returns web pages using a web server. Shiny is an R package for building interactive web applications that can help you with effective data storytelling. With Shiny, prototyping an application is fast because it is all developed in R. Using Shiny, you can easily build dashboards, host standalone apps on a web page, or embed them in R Markdown documents. In this module, you will learn the basics of the Shiny package by exploring a dashboard example. A Shiny app consists of 2 parts, the server and the user interface, or UI. The server powers the app and holds the app logic. It tells the user interface which contents to show when the user interacts with the application. The server that runs the application can be hosted on either your own computer or on a remote server. The user interacts with the UI when they run the app through a web browser. The UI has a layout that describes the locations and types of input and output fields for the app. The user interacts with the input fields, which can include text, files, checkboxes, sliders, drop-downs, and more. Output fields display the results of the analysis and can include graphs, tables, text, images, and other visualizations. For example, assume you want to know the number of data science courses released in 2021, split by programming language. You will enter the year in the text input field of the UI. This information is sent as a request to the server, and the input is analyzed on the back end. Then the server returns the results to the UI, and the visualization displays in the corresponding output field. Shiny is an external library, so you need to install it before you can use it. Use the install.packages command to install the package. Now check the installation by running a demo app that is included with the package. If the installation went well and the example app starts running, it should look like this. Close the screen to stop the app. You can find a cheat sheet about Shiny in the reading list to help your development process. In this video, you learned that the best dashboards answer critical business questions, and that an interactive dashboard is made up of 4 components. You also learned that you could use the Shiny package to build interactive dashboard apps, and that the UI and the server work together to generate visualizations based on user input. Welcome to Shiny Basics. In this video, you will learn 2 standards for creating a simple Shiny application. You will also learn how the application is structured, the parts that make up the user interface, and where to write the application logic. To recap, there are 2 main parts that make up a Shiny application. The first part is the user interface, or UI, which is a web document that displays the application to the user. It is made up of HTML components that you create using Shiny functions. The second part is the server. This is where the application logic sits. Let us create a minimal Shiny application. This is the basic template for creating any Shiny application. This application has an empty UI and an empty server. This minimal implementation forms the base of the application and will help you understand how to structure and run a Shiny application. This script is called app.r, but you can name it anything you want. In the last line of code, call Shiny app and pass in the empty UI and server variables. Note that the run command changes to run app with the presence of the Shiny app function in your code. You can now run the app by clicking Run App. The empty application then displays. At this point, the console will have some output. When you click on the Run App button, the Run App function runs. The link to the app will display below it. You can stop the app by selecting the Stop button. Note that you should not place the Run App function inside the Shiny code. Another way to write a Shiny application is to separate the UI and server code into two separate files. As your Shiny applications get more complex, this is the preferred way to write them. You write the server-side application logic code in a file named server.r and the UI-specific code in a file named ui.r. Note that you do not have to include a call to Shiny app at the end of either the server.r or ui.r file. You must place the ui.r and server.r files into a single folder. RStudio knows that it is a Shiny application when it sees the two files together. You use the panel functions to group UI elements together into a single panel. For example, if you want to have text input and numeric input boxes on the side, you can group these elements into a sidebar panel. Here is a list of the available panels. Panel functions return HTML div tags with some class attributes defined in the bootstrap. The highlighted functions will be covered in the next video. You use the layout functions to organize panels containing UI elements in the application layout. Here are a few examples. The fluid row function creates a fluid page layout, which consists of rows that in turn include columns. Rows ensure its elements appear on the same line if the browser has adequate width. Columns define how much horizontal space within a 12-unit wide grid its element should occupy. Fluid pages scale their components in real time to fill the entire browser width. The flow layout function places elements in a left-to-right, top-to-bottom arrangement. The sidebar layout function arranges elements in a layout with a sidebar and main area. The split layout function lays out elements horizontally, dividing the available horizontal space into equal parts by default. And the vertical layout function creates a container that includes one or more rows of content. Control widgets are web elements that users can interact with. They allow users to send input to the server, which in turn performs the logic. As the user updates the widget values, the output corresponding to the input will be updated as well. The Shiny package has numerous pre-built widget functions, which not only make it easier to create widgets, but also makes them look better. Some examples include date input, file input, slider input, and more. The server performs the logic whenever input widgets change, and then sends the result back to the respective UI output elements. Let us say you have an application that calculates the square of a number. You will need numeric input and output UI elements. With the numeric input widget in the UI, you can send input to the server. The server will compute the square of the input, then it will send it back to the UI output element as shown. To learn more about using Shiny, you can find more resources in the reading list. In this video, you learned that there are two standards for creating Shiny application files: a single file or two files named server.r and ui.r located in a single folder. You also learned the parts that make up the UI, including HTML tags, layouts, and widgets, as well as how the UI elements interact with the application logic. Welcome to Create a Simple Shiny App. In this video, you will learn how to create a Shiny application with a simple user interface or UI layout and the server logic required to update the UI. In the following example, you will see how to build this shiny dashboard. This dashboard uses the built-in Faithful dataset to create a plot with a configurable number of bins. The dataset contains information about the waiting times between eruptions and the duration of the eruption for the Old Faithful Geyser in Yellowstone National Park, which is in the state of Wyoming in the U.S. This dashboard has 2 sections. Can you match this layout with one of the application layouts? Yes, it is a sidebar layout. The sidebar layout function defines 2 sections, a side panel and a main panel. Let us see how this layout matches with the application layout in the example. First, on the top there is a title for the application. Then the slider input widget appears in the side panel. The plot output appears in the main panel. Application logic will connect the elements behind the scenes in the server code. You can get a basic layout of an application by selecting File, Shiny Web App, and then choosing Application File Structure. To create this dashboard, start by importing the Shiny library. Then create an empty layout using the Fluid Page function. This example uses the toFiles method of writing the application, so all these lines of code will go into the UI.R file. And now click the Run App button to make sure the empty application runs. In the Fluid Page function, add a title to the application using the Title Panel function. If you run the application, the title provided should display in the browser window. The next step is to design the application layout. This example uses the sidebar layout function to define panels for holding the input widgets and the output graph. Run the application. You can see now that the sidebar is displayed with a distinct background color, and you can now use it to add inputs. The main panel occupies about 2/3 of the horizontal width and typically contains outputs. In this case, it is the plot. Now add the slider input widget to the sidebar panel. For this purpose, we will use the slider input function. Bins is the ID of the input, which the server will use to perform the application logic. Number of bins is the label for the slider. The minimum value that can be selected is set as 1, the maximum value that can be selected is set as 50, and the default slider value is set to 30. When you run the application, you should see the slider input widget inside the slider panel. The next step is to design the main panel. The main panel holds the output plot. This example uses the plot output function to create the plot element. Distplot is the plot output variable that the server reads the plot from. Now that you have defined the application layout, the next step is to write the server logic. The flow goes like this. Retrieve the input from the slider. Get the dataset, which is named Faithful in this example. Perform the application logic on the data using the slider input. Generate the plot using the data from the result of the application logic. And finally, send the plot back to the UI output element. Let us walk through the code for the server-side logic. The function has 2 parameters, input and output. From the input parameter, you can extract the bins that the user inputs by using input $bins. Then the distribution is plotted as a histogram with the requested number of bins. This example uses the Faithful dataset feature, weighting, for distributing the numbers between the min and max. Since Faithful is a built-in dataset, you can access it without importing anything. The render plot function renders a reactive plot. Assign it to the output slot using the ID you provided in the UI, in this case, distplot. When you run the app, you should see the shiny application. In this video, you learned how to create the UI for a simple shiny app with a sidebar layout. You also learned how to retrieve inputs from the UI and develop the server-side logic, as well as how to put the UI and server files together to complete the app. Welcome to Explore Shiny Components. In this video, you will learn how to add user interface components to a sidebar panel, add charts to the main panel, define a panel with multiple tabs, and define the server logic to draw charts on a tabbed panel in a Shiny application. This video demonstrates how to build this interactive Shiny dashboard, which uses the MT-CARS dataset to generate plots for observing the data trend, correlation, and inner data subdivision. Using this dashboard, you can interact with the input controls to change variables, and then toggle between the tabs to see the data on different plots. The following example shows how to add an application title with an image, add a sidebar panel with drop-down input, slider input, and text describing the variables, and display the output graphs on tabs. To begin, create two files, UI.R and server.R. The next step is to design the user interface, so you will write this code in the UI.R file. Import the required packages for developing the user interface, Shiny and tidyverse. For this use case, you must specify the variables in the dataset that are categorical. Next is the design of the application layout. You need to add a title panel to hold the title of the application. To add an image to the title, add the image to a folder named www, then set the title to a div that contains both the image and the text. Next, define the sidebar layout with a sidebar panel and main panel to accommodate the input variable and graph components. This is the structure of the sidebar. Let us build the components one by one. Start by providing a title to the sidebar using the H3 heading tag. Next, add two controls for choosing the input variables for the graphs. One for the continuous variable and the other for the categorical variable. The var select input function creates a list of choices from the dataset column names. This function accepts the input ID that will be used to access the value, the display label for the control, the data frame from which the column names will be retrieved, and the initial default value. Then add a slider input control for controlling number of histogram bins. Finally, use HTML heading and paragraph tags to provide a guide for mapping the dataset variable names with the data glossary. As per the design, you need a main panel containing 3 tabs for dividing the output into multiple independently viewable sections. Tab 1 will have 2 plots for observing the data trend. Tab 2 will have a plot for observing the correlation between continuous variables. And Tab 3 will have a plot for observing inner data subdivision. This is the code for defining a tabbed panel with the 3 tabs for displaying the graphs. The tab set panel function creates a tab set panel that can then be passed to the main panel of the layout. The tab panel function creates a tab panel that is then passed to the tab set panel. Tab panel accepts arguments such as the tab title and the value to be set when the tab set panel reports that the tab is selected. In this example, this is plot output, which is identified by a unique ID. And the user interface is now complete. So the final step is to define the server logic in the server.r file. Import the required packages, construct the plot, and render the plots using the renderPlot function. Make sure to map the plot output to the appropriate plot ID defined in the UI. Now run the app. You can toggle between the tabs, change bins, and pass new variables to the graphs as shown here. In this video, you learned to add web components like images, list boxes, sliders, and HTML to a user interface. Create a tabbed panel using Tab Panel. Organize multiple plots on a tabbed panel, and render plots using server-side logic. Welcome to Deploy the Shiny app. In this video, you will learn the different ways to deploy Shiny applications. You will then learn how to configure and set up shinyapps.io for use with RStudio and then publish an app. There are 3 ways to deploy a Shiny app. The first is to use shinyapps.io. With this deployment method, you do not need to run your own server because shinyapps.io provides one for you. Also, there is no hardware, installation, or annual purchase contract required to use shinyapps.io. It is easy to use, secure, and scalable. When you first publish an app, both the code and data will be copied to the server. With Shiny Server, you can host your apps in a controlled environment, like inside your organization, so your Shiny app and whatever data it needs will never leave your control. You can also use Shiny Server to make your apps available across the internet whenever you choose. Shiny Server will host each app at its own web address and automatically start the app when a user visits the address. When the user leaves, Shiny Server will automatically stop the app. It is an open-source back-end program. With RStudio Connect, you can share Shiny applications, R Markdown reports, dashboards, plots, Jupyter notebooks, and more in one convenient place with push-button publishing from the RStudio Integrated Development Environment. In this video, you will use shinyapps.io to deploy an app. shinyapps.io is a platform as a service, or PaaS, for hosting Shiny applications. The RS Connect package deploys applications to the shinyapps.io service. You must install the RS Connect package before you can use it. Now, you can load the package in the R session using library RS Connect. To create an account, go to www.shinyapp.io. Click Sign Up and then use Sign In using your preferred method. On the Getting Started screen, shinyapps.io automatically generates a token and secret for you. Click on the Tokens menu as highlighted from the Shiny Apps dashboard and retrieve your token. Click the Show Secret button to show the secret. Click the Copy to Clipboard button to copy the account details to the clipboard. You will use this information later when configuring the account. To publish the application, click the publishing icon in the RStudio IDE. Select Publish Application to start the publishing process. First, you need to connect RStudio to the shinyapps.io account and authorize it to publish content. Choose shinyapps.io and then paste the credentials that you copied here. Now click Publish Application. Make sure your Shiny Apps account got connected, as highlighted here, and then click Publish. This deploys the Shiny application, and the browser will automatically open your newly deployed application. You can also use the Deploy App command from the RS Connect package to deploy your application. You can make and deploy changes easily after the first deployment. In this video, you learned that there are 3 ways to deploy a Shiny app: shinyapps.io, Shiny Server, and RStudio Connect. You also learned how to publish a Shiny app from RStudio to shinyapps.io by configuring a shinyapps.io account, setting up RStudio to deploy a Shiny app to shinyapps.io, and publishing to shinyapps.io using either the Publish to Server command or the Deploy App command from the RS Connect package. Welcome to R Markdown. In this video, you will learn how to identify the components of an R Markdown file, learn the purpose of knitting, and see an example of creating a report with R Markdown. Creating dashboards is sometimes very involved and requires lots of steps to deploy. What if you wanted to generate a single document from the data to share with your team instead? R Markdown is a great way to do so. R Markdown is a file format for making dynamic, rich, and reproducible documents with R. R Markdown files have the extension .rmd. R Markdown files have three main components: a YAML header that is surrounded by triple hyphen tags, text combined with formatting tags called Markdown, and R code chunks. Note that code chunks must be enclosed with triple backtick tags. Using these three components, you can easily create reports with the click of a button. RStudio automatically runs code, generates the embedded graphs and tables, and displays the results. You can convert Markdown files to HTML, PDF, Microsoft Word, HTML5, or even presentations. Markdown is easy to use, and the Markdown formatting that you develop in the original .rmd file is preserved during the conversion process. This means that you can build the R Markdown file once and then share the converted document in a variety of formats. To create these different outputs in RStudio, you must knit the R Markdown file by clicking the Knit button. The R Markdown file contains code to produce graphs and charts. Knitting runs all the code in the code chunks, combines it with all the Markdown you write, and then formats it into a report. So anyone who has the .rmd file can create the same report. Remember that you must re-knit the file every time the code changes. Now, let's look at an example of creating a Markdown file. In RStudio, choose R Markdown from the New File drop-down menu. Provide a title and author name for the report, and then click OK. When RStudio creates a new R Markdown file, it includes some sample content to provide you with a starting point. Click the Knit button to generate the report. In this example, the output is an HTML file. This is the report generated from the sample code. Now let us see how to create a simple report for the MT cars dataset. This report will have three sections: an introduction, the exploratory data analysis, and a conclusion. The report uses the MT cars dataset to explore motor trend car road tests. Specifically, it focuses on the mileages, the number of cylinders, and the weight of cars. The top part of the R Markdown file is YAML code. This part often contains information like the title, output, format, and author. The file also has several code chunks, like these. These sections contain R code that produce output based on the analysis, such as text output, tables, or graphs. RStudio reads the code chunks from top to bottom, so it is a best practice to import any libraries you need in the first chunk. Also in this first chunk, you should use the ops_chunk $set variable to define the settings for all code chunks that follow it. For example, if you set echo equals false, it will apply to every code chunk in this file. You can run individual code chunks by clicking the green arrow. You can also add text and format it by using Markdown tags. For example, add the hash symbol to define a heading, an asterisk for italics, and so on. You can also add and customize graphs by adding these sections to the Markdown document as highlighted. Click the Knit button to start creating the report. And the final report will look like this. This example produces HTML output. But, as mentioned earlier, there are other outputs you can use, like PDF. Note, some outputs require the installation of additional packages. For example, to output a PDF file, you must first install the LaTeX package. In this video, you learned that R Markdown files contain 3 components: a YAML header, text and markdown, and R code chunks. You also learned that knitting runs all code in the code chunks and generates a reproducible report in HTML, PDF, Microsoft Word, HTML5, or presentations. And finally, you saw an example of creating a simple HTML file using the mtcars dataset.
Hello, and welcome to this Capstone course. Congratulations for making it this far. My name is Jeff Grossman, and I'm pleased to be one of your instructors for this very much hands-on Capstone course.
And my name is Yan Luo. I'm also very glad to be your instructor. As a starting point of almost all data science projects, you need to collect the data as much and relevant as possible. In this project, you will be collecting data from various sources. After raw data has been collected, you need to improve their data quality by performing data wrangling. Then you can start exploring your processed data.
I'll be your guide as we explore some really interesting real-world datasets together. You'll get to practice your SQL skills as we query the data and gather insights. You'll gain further insights into the data by applying some basic statistical analysis. And finally, you'll enhance your understanding of the data by visualizing it. Through visualization, you'll be able to see directly how variables might be related to each other, and we'll drill down into finer levels of detail by splitting the data into groups defined by categorical variables or factors in your data. So, for example, we'll see how factors like the season or the time of day can bring out patterns in real-world data. We'll be exploring 2 of my favorite kinds of data, namely time series and geospatial data.
Now you have obtained some preliminary findings from the data. It's time to make some predictions. You will be guided to build, evaluate, and refine some predictive models for discovering more exciting insights. To combine visual and predictive analysis, you will be building an R-Shiny dashboard to tell your stories in a very interactive way. After all the exciting and excellent work you have done so far, it's time to present them to your peers. The final task of this Capstone project is to create a presentation which will be developed into stories of all your analysis and the findings.
Thank you for joining us, and I hope we inspire you to continue your journey into the world of data.
Welcome to weather and bike-sharing demand data collection. In this project, you will need to collect relevant data from various sources to analyze and predict a city's bike-sharing demand. You will use 3 main data collection methods, including using Open Weather REST API to request weather data, web scraping information about global bike-sharing systems from Wikipedia web pages, and downloading and aggregating tabular data from cloud storage. Open Weather APIs are popular for obtaining weather-related data. You can query current weather from over 200,000 cities, as well as weather forecasting queries. Like many REST APIs, its results are in JSON or XML formats, making them easy to read. For example, an RList object. More importantly, you can start using Open Weather APIs immediately for free. To obtain a list of active bike-sharing systems worldwide, you need to request a wiki web page about global bike-sharing systems, and then extract and convert the bike-sharing system HTML table into an R data frame and save it as a CSV file for further processing and analysis. Welcome to Data Wrangling. By now, you've collected the required bike-sharing data as data frames saved in CSV files. However, some data may be inconsistent, incorrectly formatted, or have missing values or unexpected noises, all of which may significantly downgrade the analysis performance. So you need to perform data wrangling before further analyzing the data. Let's start processing the web-scraped data. One typical challenge of web scraping is that data extracted from HTML pages may contain unnecessary or inconsistently formatted information. Some typical noises include arbitrary textual annotations in numeric fields, such as indicating that the number 1000 was updated from 1050. Unexpected reference links, such as the reference link 123 added to the string bike sharing system. Inconsistent data formats due to the lack of input validations from crowdsourcing websites such as Wikipedia. For example, yes or Y for the logical value true, or the same date value written in different data formats. Extracted data fields containing HTML style tags, such as marking the string bike sharing system blue, or special characters appearing due to the improper character encoding or decoding. Many of these related inconsistencies and noises can be eliminated using regular expressions. Specifically, in this project, you will be asked to standardize the column names of the datasets to improve readability. For example, converting all data column names to uppercase. Remove undesired reference links, such as removing the reference link 123. And extract the numeric value by removing its textual annotations. For example, extract the value 1000 by removing its annotation, updated from 1050. For collected tabular data, you need to perform these standard data wrangling tasks to improve quality. Detect and handle missing values that may affect the model's predictive ability. Since regression models cannot process categorical variables directly, you need to convert them into indicator variables. And columns with large values may adversely influence or bias the predictive models and degrade model accuracy. So you need to normalize these numeric columns to transfer them into a similar range. Welcome to Exploratory Data Analysis, or EDA. At this stage of the project, you've gained some valuable working knowledge of data collection and data wrangling. Now it's time to apply your knowledge of SQL and data visualization to perform exploratory data analysis, or EDA. You will need to perform EDA using SQL to query loaded databases and answer some key questions. You will also need to use tidyverse and ggplot to analyze and visualize tabular datasets. For EDA with SQL, first you will be guided to create database tables. With the successful data loading in that lab, you will be ready to run SQL queries using RODBC to find valuable statistics such as total bike sharing records or operational hours, filter data based on city or date, as well as find patterns such as bike sharing seasonality or similarities among bike sharing systems across the world. Visualization is a powerful tool for better understanding your data and finding patterns within it. In this project, you will be guided to perform visualization tasks, such as understanding the distributions of your data using histograms, finding correlations between important features using scatter plots, and spotting outliers and irregular behavior in your features using box plots. Welcome to Regression Models. Okay, you've performed exploratory and visual analysis on the bike sharing demand datasets and obtained some preliminary insights on the attributes. Now it's time to build, evaluate, and refine several predictive models to find the best performing model for predicting the hourly bike sharing count. You will be using two groups of predictors. The first group includes weather-related predictors, such as temperature, wind speed, and rainfall. As you can imagine, weather conditions can significantly affect bike-sharing decisions. The second group includes date and time-related predictors, such as the hours of the day and whether it's a weekday, weekend, or vacation. You will then be using these two types of predictors to build several regression models to predict hourly bike-sharing counts. Since your regression models will have so many predictor variables, you need to identify which predictor variables have large coefficients. Variables with large coefficients attribute more in the model. You will also need to try different methods to improve the predictive performance of your regression models. As the relationships between predictors and responses may not always be linear, you can add polynomial terms to handle nonlinear relationships. In a linear regression model, predictors may interact and affect the response. To capture such interaction effects, you could add some interaction terms. Adding those terms will make your model more complicated, more difficult to explain, and likely to suffer from overfitting. However, you can add regularization terms to your models to overcome these issues. Welcome to building a dashboard with R Shiny. So far, you've built regression models to predict hourly bike-sharing demand using weather, date, and time predictor variables, and the model performance looks promising. Now, you want to integrate the regression model and build an interactive R Shiny dashboard. The dashboard allows users to review and explore the weather forecasting data, predicted hourly bike-sharing demand, and other relevant information. First, you will build a leaflet-based interactive map that can show which cities may have large bike-sharing demand for the next 5 days, so that you can plan logistics accordingly. For example, transporting some bikes from low-demand cities to high-demand cities. On the map, you can add circle markers with different sizes and colors and pop-up labels on each city's location. The color and size of the marker reflects the level of that city's predicted bike demand for the next 5 days. Now, you will add the ability to drill down to a specific city using a drop-down list. If all is selected, then you just show the overview map. If a specific city is selected, you need to drill down and show the city's details. Next, you will use ggplot to render more detailed plots that show bike-sharing prediction, temperature, and humidity trends when users drill down to a city. For example, users may want to know a selected city's temperature trend for the next 5 days, which can be visualized using a line chart. Bike-sharing demand prediction is another important trend line for a selected city. This data is also displayed in a line chart, but you can add some interaction so that users can click to see bike-sharing demand, date, and time details. From previous analysis, you know that bike-sharing demand highly depends on humidity, so you can display this correlation using a scatter plot for the selected city. While finding and cleaning data is an important first step in data analysis, a concept can be lost if you are not able to organize and represent the findings effectively to your audience. In this video, you will learn how to represent your findings by focusing on specific elements to create a successful data findings report. After the data has been collected, cleaned, and organized, the work of interpretation begins. You are now able to obtain a complete view of the data and hopefully answer the questions that were formed before starting the analysis. Now you typically begin to compose a findings report that explains what was learned. Depending on the stakeholders and how they received the information, the report could vary in form. This could include a paper-style report, a slideshow presentation, or maybe even both. The findings report is a crucial part of data analysis as it conveys what was discovered. When beginning this process, the collected data and information may seem a little overwhelming. The best way to get through this block is to begin by creating an outline. By completing an outline, you can then get a complete picture and begin to write in a precise but simple manner. While there are many different formats for creating a data-driven presentation, we have created a simple outline that is easy to follow, yet effective. When creating your outline, always remember to structure it towards your audience and create a presentation that is appropriate for your situation. You first begin with your cover page. This beginning section will have the title of your presentation, your name, and then the date. The next section in your outline will be an executive summary and then the table of contents. The table of contents will contain the sections and subsections of your report in order to give your audience an overview of the contents. This also enables readers to go directly to a specific section that may be more important to them. Continue your presentation with the introduction, methodology, results, discussion, conclusion, and finally, the appendix. Note that the depth and length for each element may vary depending on the audience and format of report. The first step in creating your report is properly creating an executive summary. This summary will briefly explain the details of the project and should be considered a standalone document. This information is taken from the main points of your report, and while it is acceptable to repeat information, no new information is presented. The next section after the table of contents is the introduction. The introduction explains the nature of the analysis, states the problem, and gives the questions that were to be answered by performing the analysis. The next section is methodology. Methodology explains the data sources that were used in the analysis and outlines the plan for the collected data. For example, was the cluster or regression method used to analyze the data? Next, we have the results section. This section goes into the detail of the data collection, how it was organized, and how it was analyzed. This portion would also contain the charts and graphs that would substantiate the results and call attention to more complex or crucial findings. By providing this interpretation of data, you are able to give a detailed explanation to the audience and convey how it relates to the problem that was stated in the introduction. Next, discuss the report findings and implications. For this section, you would engage the audience with a discussion of your implications that were drawn from the research. For example, let's say you were conducting research for top programming languages for college graduates. Would you find they need to learn multiple languages to remain competitive in the job market, or would one language always reign supreme? We have now reached the conclusion of the report findings. This final section should reiterate the problem given in the introduction and gives an overall summary of the findings. It would also state the outcome of the analysis and if any other steps would be taken in the future. And last, we have the appendix. This section would contain information that really didn't fit in the main body of the report, but you deemed it was still important enough to include. This type of information could include locations where the raw data was collected, or other details such as resources, acknowledgments, or references. In this video, we learned about the important elements in creating a successful data findings report. In the next video, we will learn the best practices when presenting your findings. While finding and cleaning data is an important first step in data analysis, a concept can be lost if you are not able to organize and represent the findings effectively to your audience. In this video, you will learn how to represent your findings by focusing on specific elements to create a successful data findings report. After the data has been collected, cleaned, and organized, the work of interpretation begins. You are now able to obtain a complete view of the data and hopefully answer the questions that were formed before starting the analysis. Now you typically begin to compose a findings report that explains what was learned. Depending on the stakeholders and how they received the information, the report could vary in form. This could include a paper-style report, a slideshow presentation, or maybe even both. The findings report is a crucial part of data analysis as it conveys what was discovered. When beginning this process, the collected data and information may seem a little overwhelming. The best way to get through this block is to begin by creating an outline. By completing an outline, you can then get a complete picture and begin to write in a precise but simple manner. While there are many different formats for creating a data-driven presentation, we have created a simple outline that is easy to follow, yet effective. When creating your outline, always remember to structure it towards your audience and create a presentation that is appropriate for your situation. You first begin with your cover page. This beginning section will have the title of your presentation, your name, and then the date. The next section in your outline will be an executive summary and then the table of contents. The table of contents will contain the sections and subsections of your report in order to give your audience an overview of the contents. This also enables readers to go directly to a specific section that may be more important to them. Continue your presentation with the introduction, methodology, results, discussion, conclusion, and finally, the appendix. Note that the depth and length for each element may vary depending on the audience and format of report. The first step in creating your report is properly creating an executive summary. This summary will briefly explain the details of the project and should be considered a standalone document. This information is taken from the main points of your report, and while it is acceptable to repeat information, no new information is presented. The next section after the table of contents is the introduction. The introduction explains the nature of the analysis, states the problem, and gives the questions that were to be answered by performing the analysis. The next section is methodology. Methodology explains the data sources that were used in the analysis and outlines the plan for the collected data. For example, was the cluster or regression method used to analyze the data? Next, we have the results section. This section goes into the detail of the data collection, how it was organized, and how it was analyzed. This portion would also contain the charts and graphs that would substantiate the results and call attention to more complex or crucial findings. By providing this interpretation of data, you are able to give a detailed explanation to the audience and convey how it relates to the problem that was stated in the introduction. Next, discuss the report findings and implications. For this section, you would engage the audience with a discussion of your implications that were drawn from the research. For example, let's say you were conducting research for top programming languages for college graduates. Would you find they need to learn multiple languages to remain competitive in the job market, or would one language always reign supreme? We have now reached the conclusion of the report findings. This final section should reiterate the problem given in the introduction and gives an overall summary of the findings. It would also state the outcome of the analysis and if any other steps would be taken in the future. And last, we have the appendix. This section would contain information that really didn't fit in the main body of the report, but you deemed it was still important enough to include. This type of information could include locations where the raw data was collected, or other details such as resources, acknowledgments, or references. In this video, we learned about the important elements in creating a successful data findings report. In the next video, we will learn the best practices when presenting your findings.